Good morning, ladies and gentlemen. Our uh, opening ceremony will start in a few minutes. So the organizing committee would like to invite delegates, professor scientists to enter the conference hall and kindly take your seats. Thank you. So, distinguished guests, ladies and gentlemen, to continue the series of conferences of the 21st Gongkong to Vietnam in 2025, Gongkong to Vietnam IC Center and Simon's Astrophysics Group at IC organized the scientific group workshops entitled the 2025 SAGI Astrophysics Workshops held at the International Center for Interdisciplinary Science and Education here in Quy Nhơn City, province. So building on the success of the 2022 and 2023 workshops, the 2025 editions will once again bring together leading experts to share the latest research findings on dust polarization and complementary technique to study dust, gas, magnetic field, and other related topics. And as we begin today, it's a distinct honor to welcome some of very special guests who have joined us from Binh Province. So the organizing committee would like to welcome and present Dr. Nguyễn Hữu Hà, Deputy Director of the Department of Science and Technology, Binh Province. We would like to welcome and present Mr. Võ Đình Kha, Deputy Director of the Department of Foreign Affairs, Binh Province. From the scientific and local community side, the organizing committee would like to present and welcome Professor Hoàng Chí Thìm from Korea Astronomy and Space Science Institute, the chair of the workshop. Associate Professor Phạm Ngọc Điệp from Vietnam National Space Center. Dr. Lê Ngọc Trẫm from Leiden University, the Netherlands. Dr. Shi Wei Young from Academia Sinica Institute of Astronomy and Astrophysics, Taiwan. And we also want to welcome all of the participation of more than 50 scientists, researchers, and students who are joining both remote and on-site today. So on behalf of the organizing committee, we would like to extend our warmest welcome to all of you. We wish that you all have inspiring talks, engaging research, and successful workshops ahead. To start with, we would like to welcome to the stage Associate Professor Phạm Ngọc Điệp to deliver the opening remarks. So would you please?
Good morning, everyone. A very warm welcome to Quy Nhơn, to the beautiful IC's conference center, and most importantly to the 2025 SAGI Astrophysics Workshop. Dear distinguished guests, Mr. Võ Đình Kha, Deputy Director of the Foreign Affairs of Bình Định Province, and Dr. Nguyễn Hữu Hà, Deputy Director, the Department of Science and Technology of Bình Định. It's our honor to have your presence here. You see that it's not very normal to have the very close support from the local government to the scientific activities in many places all around the world, like in Quy Nhơn. It's really warm. Every time we are here, we have the presence of the local government to be with us for the opening ceremony. For those who come to Quy Nhơn for the first time, you may know that the International Center for Interdisciplinary Science and Education, ICS, was founded by Professor Giang Trần Thanh Vân and and his wife, Professor Lê Kim Ngọc. Professor Yang Chen Thanh, he himself is a well-known particle physicist, and Professor Lê Kim Ngọc is a professor in biology. So they founded this center more than 10 years ago in 2013. And currently, each year, ECs organize more than 10, maybe 15 conferences and schools. And out of that, several of them, maybe 1/3 of them are on astronomy and astrophysics. This center is also supported Quy Nhơn, the local government, with the representatives here to build next door a science exploration center for public outreach and education, where we may have the opportunity to visit. They have 3 exhibition rooms, a planetarium, and an observatory. The observatory hosts a 0.6 meter diameter optical telescope, which is the biggest telescope in Vietnam. So you see the image of the center on the left-hand side. And this center was designed by a famous French architect, Mr. Milo, who also designed the National Museum of Singapore. So before we delve into the exciting science that awaits us, I'd like to take a moment to reflect on the journey that brings us together. Our host, the sponsor of this workshop, the Simons Astrophysics Group at ECs, was established with the generous support of Simons Foundation. And the initiatives were thanks to these 3 Vietnamese scientists, Professor Thiêm Hoàng, Dr. Nguyễn Trọng Hiền from NASA, and Dr. Nguyễn Lương Quang from American University in Paris. So from the inception of SAGI, it has been dedicated to foster a vibrant hub for cutting-edge astronomical research and international collaboration right here in Vietnam. And SAGI aims to connect local and regional scientists with the global community, stimulate new research directions, and nurture the next generation of astrophysicists. This workshop is a continuation of a successful series building on the momentum of previous workshops, such as those focused on new frontiers of astrophysics in the golden era of dust polarimetry organized in 2022, and the dust polarimetry and applications in astrophysics in 2023, 2 years ago. So we've tried to create a platform where focus and intensive directions can lead to significant scientific progress and collaboration. This year, the workshop bring together experts in the fields of star formation and dust physics, the 2 areas that are profoundly interconnected. And on top of that, the general aim is to explore the latest observational results, theoretical models, and computational techniques in astrophysics in general, hoping for identify synergies, address outstanding challenges, and spark new avenues for research. So, as you know very well, the event of this type doesn't organize itself. It requires immense dedication and incredible amount of work from the SOC and LOC, and also from the staff at ISICE here. So in this regard, I want to extend a special and heartfelt thanks to Professor Thiêm Hoàng as the chair of the Scientific Organizing Committee and the de facto chair of Local Organizing Committee. He has been the driving force behind this workshop. His scientific leadership has shaped an outstanding program, and his meticulous attention to local arrangements ensures that our time here will be both productive and enjoyable. Thiêm, on behalf of us, thank you for your extraordinary efforts to organize this workshop series. Finally, a workshop is truly defined by its participants. I want to sincerely thank each and every one of you. Those presenting contributed talks and invited talks and attendees for making the journey to very long way to be here with us. Your expertise, your questions, and your willingness to engage are what will make the coming day a success. I encourage all of you, in particular the young students, to actively participate, challenge, and discuss. Let's make the most of this opportunity to learn from each other and push the boundaries of our understanding. I wish you all a highly stimulating, productive, and enjoyable workshop. Thank you, and let the science begin.
Thank you, Associate Professor Phạm Ngọc Điệp, for this speech. So this is also the end of the opening ceremony. So before we enter the first section, we would like to invite all of you to move to the front of our center to have a group picture, and then we will have a tea break. And we will be back at around 10. So your bags and luggage can be fully safe to put in the right at your seat.
Can you hear me? Alex, maybe
Hello?
how are you doing? Ngan here.
I hear you very, very poorly. Hello! I'm so happy to see you. How are you?
Just still I'm in Vietnam, but soon in the next month I will come.
I don't hear you. I hardly hear you anything. So you should speak in the microphone.
Yeah, I'm doing okay. But
I'm so happy that you're doing okay.
so I'm moving to Kasi in next month.
Oh, that's absolutely great. That's absolutely great. Yeah, will you work with Thiem?
Yeah, we his
Oh, that's terrific. He is a great scientist. I envy you.
to be prepared for your talk. Maybe can you try to share your presentation? I will let.
Yeah, I can. No, but it says unable to start video. You should enable me.
I mean the host allow you to.
Yeah, a host should allow because if I press video, it says unable to start video. You should allow me. I don't know how it's to allow me. Maybe you should ask someone how to allow.
I mean can you share the screen the slides from your side? So it
But I cannot have video. I will share.
Yeah, we can see your slide.
yeah, we see it now.
Okay. Then it sounds great.
Can you maybe move to the next slide?
So do you see?
Yeah, we see it.
Okay, wonderful. Okay. So, but I still cannot share video. I cannot have video. It's okay for me. If people do not see me, it's okay.
Okay, can you see our screen? Yeah.
Yes, no, well, I see, well, the show a part of the screen, not the whole screen.
People,
Minutes before coming back from the coffee break. See you soon.
Hi, Alex. Can you hear me?
Yeah, I can hear you very well.
I can read the Vietnamese, but I cannot read the Russian on your poster.
Okay, but there is some Vietnamese which I cannot read either.
Where did you get that poster? This
Well, it's on the internet.
from internet. It's very interesting.
Well, the idea that I like, I'd like to, have more contacts with Vietnam,
Right.
and I would be very happy to co-supervise students from Vietnam, and actually, experience with you was so exciting for me that I would like to have more such experiences. Maybe it's unique and not repeatable, but still, I try to have more Vietnamese students.
Wonderful. So
Therefore, I show my email so people can contact me, and there could be discussions. Maybe we can have joint work in magnetic fields, turbulence, polarization, etc. So people can see my research interests looking at this other websites. So this is what I'm interested.
do you mind to turn on your video? Because in the audience, I think there are many students and they haven't met you before.
Yeah, but I can do it. It says to me that host enable your video.
Okay. So the host, so Bao, who is the host of the Zoom? So can you enable him to turn on the video? Yeah. Okay.
Should I try?
He's now testing, so please wait.
Okay. I can stop share, and in this case, I can try to enable video.
So I think you should turn on your video because
Okay. In this case, I stop sharing and try to get video. It's still unable to start video. You cannot start video because it is disabled by the host.
okay, so that is a host problem.
It's okay. I don't want to. Later you can show my beautiful photo and everyone can enjoy watching me. But it's okay. Let me share. It's more important to have. Okay, so now I share and I'm starting my talk, okay? Hello, okay or not?
Alex, can you hear me?
Yes?
Okay, so good evening from right? Good morning again.
Well, it's a good night for me. Unfortunately, I will not be able to hear most of the talks because, okay, start my video, okay.
Yeah. Ah,
Oh, here I am.
works beautiful.
Look and enjoy.
Okay, so let's start our first scientific session. Focus on the interstellar medium, star formation, and stellar feedback. And we have the first talk, online talk from Professor Alex Lazarian. So please, Alex.
Okay, wonderful. It's my pleasure. I apologize I could not come to Vietnam this time. I really enjoy visiting Vietnam, and hopefully the other conference, if you have in the center, I will be present. So I start my talk expressing my interest in cooperating with Vietnamese scientists, in particular in co-supervising Vietnamese students. So, I also would like to advertise the magnetic field conference that will be held in Madison in July, and you are welcome to participate in this conference. The registration is open. Now, my talk will be about surprising properties of subalfinic turbulence. In particular, I will be talking about the dependence of the properties of turbulence on the nature of driving. What you see here at the first slide, you see a visualization of velocities. This is upper row, and the visualization of magnetic field in subalfinic turbulence for velocity driving. And you see that these patterns are rather different. So I will describe this difference and its origin. Well, turbulence can be scary, but I will try to be elementary. I will try to be simple. So still fasten your seat belts and we continue. So first of all, if we are talking about turbulence, we should understand that it is chaos, but at the same time it's order. So it is chaotic order, so sounds strange, right? But if you look at this drawing by Da Vinci, Leonardo da Vinci was very nice in describing nature. And you see that indeed there is a lot of chaos, but still you can see order. So this order is what we are studying in turbulence. So we are focusing on this ordered part, which helps us to understand what is going in turbulent flows. The first understanding, quantitative understanding of turbulence was provided by Richardson. And Richardson was describing this by a poem. Big walls have little wells which feed on their velocity, and little walls have lesser wells, and so on to viscosity. And this was how he was characterizing atmospheric turbulence. In general, Richardson was a very interesting person. He was a pacifist who refused to join the forces during the First World War. And he, in fact, was not publishing some of his results, worried that his results on turbulence could be used for chemical warfare. In the present unstable world, this is a very interesting example of scientists approaching his social, problems. Okay, but could we quantify this poem by Richardson? We can have in this case the picture of Kolmogorov. In Kolmogorov turbulence, we have the injection of turbulence at velocity VL at large scale L. And this energy is cascading through these eddies, wells, up to the viscosity. During this cascading, the quantity VL cubed over L is constant because it follows from these two equations. And then we get the famous Kolmogorov relation. Velocity scales scale to 1/3. And this corresponds to the spectrum because spectrum is useful characteristics. Usually people talk about spectrum, and this corresponds to the K 5/3. K is essentially 1 over L. And here at the lower panel, you see that you have large eddies for which viscosity is not important. They decay into smaller eddies for which viscosity is still not important. It goes on and goes on till viscous dissipation when viscosity becomes important. This is hydrodynamic turbulence. In astrophysics, we have an elephant in a room, and this is magnetic field. And magnetic fields significantly change the properties of turbulence. So magnetic turbulence is different from hydrodynamic turbulence in many respects. Nevertheless, if we look at the spectra of magnetized turbulence available from observations, we surprisingly see that electron density spectrum follows Kolmogorov 5/3. And also recently, my students found that the velocity in multiphase media also following this 5/3 spectrum. So this is by itself an interesting fact, but I will not dwell upon it. There are some reasons for this peculiarity. MHD turbulence is important for many processes, and here this diagram shows that it affects cosmic rays, affects dynamo, reconnection, and in general it defines properties of ISM and galaxies. Here what you see is the modification of velocity motions by magnetic field. As I said, magnetic field is important, and you see that these contours of velocities are aligned with the magnetic field. This is the case of subalfinic turbulence, which is the subject of my talk. So when we have subalfinic turbulence, we can introduce a useful number, and this is Alfvén Mach number. And Alfvén Mach number is the ratio of the injection velocity to the Alfvén velocity. So if Alfvén velocity is larger than injection velocity, it means that magnetic field is strong. And this corresponds to the subalfinic turbulence. The lower panel, as you see, shows different settings. Subalfinic, for example, corresponding to Alfvén Mach number 0.3, essentially visualization shows that magnetic fields are nearly parallel. If we increase Alfvén Mach number, it's still subalfinic 0.7. The magnetic field lines, there's again visualization of magnetic field lines, becoming more chaotic. And when we come to Alfvén Mach number 1.5, we are getting completely chaotic picture. So we will be talking about subalfinic turbulence. The discussion of subalfinic and superalfinic turbulence can be found in the book that my former student Barry Rezniak wrote with me in 2019. So you can find many things which will not be covered in this talk in that book. So if you look at this book, you will see that there are some particular predictions for the spectrum of subalfinic turbulence. So we can have a spectrum at close to the injection scale, which scales as k perpendicular, this perpendicular wave number, which characterize perpendicular motions, k minus 2, and then Kolmogorov 5/3, starting with some larger wave numbers. And the default for subalfinic cascade was always kinetic energy equals to magnetic energy. So this is somehow default because people were thinking, what are magnetic turbulence? These are fluctuations, and for example, for alfinic fluctuations, we have this equipartition for slow fluctuation also. So that's very natural. However, some simulations showed that this is not somehow true. So in simulations, for example, by Federath, it was found that magnetic energy may be smaller than the kinetic energy. So then this created equation. What's going on? And, you know, there is usually a human nature way of explaining what we don't know. Just refer this to something we also don't know. Compressibility in turbulence is not well studied, and therefore researchers without much thinking attributed it this difference of magnetic and kinetic energy to compressibility. So they were saying, okay, there are some scaling, for example, Goldberg-Strait has scaling, but they were obtained for incompressible turbulence. So, but now we have compressible turbulence, and that's the solution. So this motivated me to study this problem. Is the compressibility is the source of the disparity between kinetic and magnetic energy? The case of compressibility was earlier already involved, 25 years ago, in relation to the decay of MHD turbulence. Unexpectedly, people observed that MHD turbulence decays fast, as fast as hydrodynamic turbulence. And they did not expect this. They expected that magnetic fields will be oscillating and this will be long decay. The whole idea of support of molecular clouds by MHD turbulence was based on that. And people again said, oh, this is compressibility. But Jungyen Cho and me found that it was not compressibility, and this is the property of incompressible MHD turbulence. Let's discuss some physics which is relevant. And this is physics related to well-known effect of Bernoulli. Bernoulli effect happens when, for example, you have wind over the ocean or pond, and it creates waves. Why is that happening? It's happening because we have the constant sum of static pressure, dynamic pressure, and hydrostatic pressure. Well, hydrostatic pressure in MHD turbulence we ignore, so we have dynamic pressure and static pressure. So what do we have with the Bernoulli effect when we have two tubes of different diameter? We have higher pressure in the thicker tube, and lower pressure when the tube is thinner. And the velocities are the opposite. They are smaller when in the higher, thicker tube, and become larger in the thinner tube. This is a very simple effect, but we'll employ it considering what's happening in MHD turbulence. So this is the same, essentially, cartoon, but we show here the magnetic field lines, which create this different cross-section of your flow. And so, what if the cross-section of your flux tube is large, the pressure will be of the fluid will be large. And when the cross-section is smaller, the pressure will decrease. And what does it mean that pressure decreases? Pressure decreases, it means that it should be compensated by magnetic field pressure. And this is what is shown. Magnetic fields are concentrating, and this increases magnetic field pressure. So if we do some math, as I'm showing here, we can have this delta P equals rho VL squared. This is just the Bernoulli effect. But delta P is proportional B delta B. If we divide both parts by B, we get a very interesting relation. Delta B parallel over B equals not delta V over V alpha, as usually assumed, but delta V over V alpha squared. And we also find that kinetic energy will be dominant compared to magnetic energy. And this is easy to show, because kinetic energy is rho VL squared. But magnetic energy, according to this formula that I showed earlier, it will be dB squared, rho VL squared, kinetic energy, times VL over VA. And as we discussed, in subalphanic turbulence, VL over VA is less than unity. And therefore, we can have an interesting situation that in incompressible situation, in subalphonic turbulence, we may have turbulent energy much turbulent magnetic energy much smaller than turbulent kinetic energy. What was assumed here? It was assumed that we are driving turbulence through velocity fluctuations, and this is the key. Okay. Well, I'm not going to scare you by derivations, but I would just like to tell you that we predicted that also spectral slope of fluctuations in the case of velocity driving will be different. So velocity fluctuations will be following this k minus 2, and magnetic fluctuations will be following k minus 1. And you see the differences between velocities and magnetic field in the visualization. You see that there is more structure in velocity in magnetic field. And this corresponds to a shallow spectrum, k minus 1. So if we calculate the velocity spectra of velocities and magnetic field in the case of velocity driving, we see that indeed we in numerical simulations confirm k minus 2 for velocities and k minus 1 for magnetic field. And the spectra show differences corresponding to the dominance of kinetic energy compared to magnetic energy. But when your fluctuations become smaller, so you get to the transalphonic turbulence, so alpha and Mach number becomes of the order of unity, the two spectra coincide. So then we return to what we already know. Well, there is also a way to show that there's fluctuations of perpendicular magnetic field and parallel magnetic field will be of the same order. This follows from the conditions of magnetic field solenoidality, but I don't want to torment you by discussing this moment. It's just accept that it's possible to prove that perpendicular fluctuations and parallel fluctuations are of the same order. So, as we discussed, these parallel fluctuations and perpendicular are of the same order, which follows from solenoidality condition for magnetic field. And therefore, we can have these relations between the turbulent magnetic energy and kinetic turbulent energy. And also, if we divide both parts, so delta B squared and this part over B squared, and taking square root of this, we get an interesting result. Delta B over B equals not VL over VA, usual relation, but VL over VA squared. This was, as already discussed by earlier authors who attributed this to compressibility. I stress again, and this is important, that this is result fundamental, it's a result of incompressible MHD turbulence. And here it is. We see here delta B over, and this is alpha and Mach number as given by VL over VA. And this line corresponds to this predicted relation. And you see a close correspondence of our incompressible simulations. I always was talking about the velocity driving, because this is a typical way of driving turbulence in MHD compressible simulations, and also in compressible simulations frequently. So, but what about magnetic driving? If we have magnetic driving, we do not have this Bernoulli effect, and as a result, we have a correspondence between the magnetic energy and kinetic energy. We have equipartition. So this is an important result, that everything depends on the driving of turbulence. Again, when we were publishing our paper, the referee was again saying that you cannot say that compressibility is not relevant. And at that time, we didn't have this plot. This plot was produced by Jingyan Cho. This is our joint base and paper. And we show that here that if we have magnetic driving, then we do not have excess of kinetic energy over magnetic energy of turbulence. So if we see something, we have some excess of magnetic energy, not excess of kinetic energy. So everything that I said is good, but then the question is, what do astronomers make of it? Is it possible to have some measurements which would find whether the turbulence is driven through velocity or magnetic fluctuations? Because, for example, magnetorotational instability is driving through magnetic fluctuations. So yeah, it is possible to distinguish these two situations, and this is shown through synthetic observations for magnetically velocity-driven fluctuations. The contours, which are on the left side of the correlation functions, are different in these two cases. And also, if we calculate velocity and magnetic field correlation functions, they are different. So it is possible to find out what is the driving of the turbulence.
Alex, can you?
Yeah.
You have 10 more minutes. Please save time for questions. Right.
I'm finishing. This is essentially the last slide. So, okay, we have this physical fact. How does this change the physics? How change our approach to astrophysical problems? First of all, this is modifying our formula for Davis-Chandrasekhar Fermi. This is approach for obtaining magnetic field. In fact, we suggested a universal formula for obtaining magnetic fields, which does not depend on which way we are obtaining which way the turbulence is driven. And this is this formula for B perpendicular. And it has not fluctuations delta phi, as in the usual Davis-Chandrasekhar Fermi formula, but MA. And this, in this case, it does not depend. But I can discuss this formula at that question time. It also has a lot of implications for propagation of heat and cosmic rays, for driving galactic winds, star formation, etc., etc. So in all of these applications, we have dependence of alpha and Mach number, and it is important whether we should use alpha and Mach number defined as delta B over B or delta V over V alpha. So again, this is something I can discuss at length if there is interest at the question time. So this is my summary slide. What I wanted to make a point is that driving of turbulence matters for the properties of subalphanic turbulence. We have subdominance of magnetic field fluctuations if we have velocity driving. So magnetic energy in this case is kinetic energy times number less than 1, alpha and Mach number squared. But this is only for velocity driving. If we have the magnetic driving, we have the equality of this kinetic energy and magnetic turbulent energy. The nature of this turbulent driving can be obtained from observations, and I appeal to the audience to use the techniques that we suggested for this purpose and to determine what is driving turbulence in, let's say, interstellar media. Thank you.
Thank you very much, Alex. So the session opens for questions or comments. A question from Tiam.
Yeah, thank you, Alex. It's very nice talk. So I have one question about the source of velocity driving or magnetic driving. So I mean, in the galactic environments, do we know like in what environments the velocity driving is dominant over magnetic driving? Does it depend on the local environments or the large scale environments?
This is a very good question. You know, we can speculate. We can speculate and say that, okay, supernova move, you know, matter, and this is velocity driving, while magnetorotational instability gets fluctuations in terms of a magnetic field, for turbulence which arises from you know, streaming of cosmic rays, also have fluctuations of magnetic field as the driver. The most important, I think, point is that we don't need to speculate. We can take observational data, analyze magnetic fluctuations, and analyze velocity fluctuations. Create the structure functions, and at least with our synthetic observations, we see a very significant difference in the case of magnetically driven turbulence and velocity-driven turbulence. Therefore, I believe that identifying the nature of turbulence in interstellar media presents an observational challenge rather than so I prefer not speculate when we expect one or another. Let's see.
Other questions? Could you go back to the previous slide? I have a simple question. Can you explain the factor F3 in the calculation of the modify DCF?
Well, in DCF, this factor is absent and it's considered empirical, can be empirically found from numerical simulations. Potentially, if we are applying DCF to subalfinic turbulence, and DCF is created for subalfinic turbulence, we should take into account the effects of direction of magnetic fields is in respect to the line of sight. In our paper from 2000, I think, we calculated this such factors for the for taking into account that the turbulence is a mixture of different modes, Alfvén modes, slow modes, and fast modes. But if we apply, but we were focusing on the application to small patches of the sky. If we apply this technique to larger patches of the sky, in this case, where we have the scale equal to the injection scale, this dependence of gamma is much less important. It can be 1/2, for example, close to 1/2. What is important in this formula is that you use not the line width as usual in usual DCF, but use all sonic Mach number. MS is sonic Mach number. Yes, if you know line width, you can also find sonic Mach number. But the advantage of this approach is that you can obtain sonic Mach number even if you don't know line width. Sonic Mach number, for example, can be obtained for channel maps, for which line width does not make sense. So you can use this formula for channel maps and still obtain magnetic field strength. So, and as I said, this is also universal formula which does not depend on which way we have the driving. There are ways of independent obtaining both sonic and Alfvén Mach numbers. If you write me email, I can provide more papers on that.
Okay, so thank you very much. Let's thanks Alex again. So we have to move to the next talk. Thank you very much, Alex.
Thank you.
So good night if you leave. Okay, so the next talk will be talk about a general theory of grain alignment and disruption, which is given by our chair. Okay, so you have 40 minutes.
Okay, yeah. All right, so hi everyone. So let me begin the talk in person. I think the first talk in person. So you know our interstellar medium includes gas, dust, magnetic fields, and turbulence. So we already heard about the turbulence from the talk by Alex, and so my talk will focus on dust and how we use the dust to study magnetic fields. And of course, dust is also interesting itself. So I will focus on the fundamental physics of dust and how we use the dust to study the universe. Okay. Yeah, okay, so good. So this is the cartoon I describe about our cosmic ecosystem. So in our cosmic ecosystem, this is a cycle of converting gas, dust into astronomical objects. And in order to convert gas and dust in astronomical objects like stars, planets, black holes, we need to follow the astrophysical processes. And the astrophysical processes are determined by two fundamental forces, gravity and electromagnetic forces. So one of the, you see here the gravity and magnetic fields. So dust is a very important choice of magnetic fields. And the bottom, the technique, how we can choose magnetic fields using dust is through the alignment of dust grains with magnetic fields. So my talk will focus on the long journey of understanding alignment from the early theory, radiative torque alignment, or RAT, which we developed together with Alex in 2007. And then after 9 years from the original RAT theory, we proposed a unified theory named MRAT. So MRAT stands for Magnetically Enhanced Radiative Torque. It was published in 2016. And just this year, I proposed a general MRAT theory. So every 9 years. So after the second paper in 2016, I thought that, well, maybe the alignment theory is complete. So I should move on to some other topics. But after 9 years, I realized that, oh, the theory is far from complete. So this year, I propose a general MRAT theory. So hopefully it can help us to understand the alignment and also disruption of dust grains in the whole cosmic ecosystem. So if you can see here that RAT and MRAT theory only covers 1/2 of our cosmic ecosystem, from the interstellar medium to star-forming region. The other half, including the region with strong stellar feedbacks, like the surrounding black holes, supernova, evo star, and even jets. So with the general MRAT theory, hopefully we can understand the alignment disruption of dust grains in the whole universe. That is my ambition. Okay, so this is an outline of my talk. So first, why do we care about dust in general and also magnetic fields? So because the audience here has many students, so I think maybe for many students, this is the first time you hear about dust and magnetic fields in the universe. Of course, dust is quite common in our daily life, but in the universe, maybe this is the first time. And then why granular alignment and disruption are important for understanding astrophysics, especially for studying magnetic fields. And then I will focus on the fundamental physics of granular alignment and rotational disruption, so including the evolving history of the process of development from the RAD theory to MRAD and general MRAD. Of course, one of the key idea for working on astrophysics is we need to test with observational data. All theories become useless unless the theory is tested with observation. So I will describe our efforts developing computational tools to connect the alignment theory with observation. And finally, I will summarize my talk. Okay, so first of all, why magnetic fields are important in cosmic ecosystem. So as I already mentioned to you, fundamentally, the universe is governed by 4 fundamental forces, including the strong force, weak force, gravity, and electromagnetic force. So in astronomy, the 2 later forces, gravity and magnetic fields, are dominant. So there are so many theories proposing that how magnetic fields are important for the evolution of interstellar medium, to the formation of molecular clouds and stars, to formation of planets, and also for influencing stellar feedback and galactic feedback. So we need to now understand or to observationally test the important role of magnetic fields. And how about dust? So our universe, is really vast. And on Earth, in order to study the universe, astronomers, we need to rely on some indirect method. So we look at the sky using the indirect signal, electromagnetic signal that we observe with the naked eyes or with telescopes. And so here's a Milky Way in naked eyes. So you can see that in the Milky Way here, there are many bright regions and also dark region. So the bright region here contains less amount of dust, and the dark clouds contain a lot of dust. So dust basically block starlight, and that's why it makes the sky not so homogeneous. So it's beautiful. And it's in optical, but in near infrared and mid infrared, so you see now the sky becomes very, very beautiful. So thus allow us to see the beautiful nature of the universe. And in far infrared, you see this is the whole galaxy in far infrared. And in the region with planets, new planets are being formed. You can see that it has a ring and gap structure here. So in almost in the wide range of wavelengths, dust is relevant. So I would say that dust is one of is open the widest window into the universe. So it's a very essential tool for astronomers. But dust also play very key roles. For example, so first of all, where does dust come from? So dust is a solid material. So dust formed from condensation of gas. So in the later stage of stellar evolution, or AGB or red giant stars, so the stars are injecting material or gas into the surrounding environment. So gas will cool and condense to form dust. Dust also formed from supernova. So supernova can also produce dust here. And then when dust is injected into the interstellar medium, they follow and they play very important roles in different processes into, for example, it is determine the gas heating and cooling, and the gas heating and cooling, it determine the formation of molecular clouds, followed by the collapse of clouds to form stars. And dust is very, very important in different processes. Yeah, so we know that dust is there. We can observe a dust emission or extinction. How we can use those signals to learn about the fundamental processes in astrophysics. So we need to now really master the physics behind the dust. So dust basically interact with radiation from stars, or dust can interact with gas. So first of all, the interaction between dust and radiation. That's very important. So for example, we know that radiation has three fundamental quantities. So radiation has energy or photon energy. So when dust grains absorb some radiation, so dust receive the energy from photons. So dust can be heated to higher temperature. And then when dust is heated to higher temperature, it will re-emit radiation in longer wavelengths, in 5 infrared. So using these fundamental properties, we learn about how we trace back from the signal we observe to the fundamental properties of the dust and also local environment. And dust now also interact with radiation in terms of photons, in terms of momentums. Photons have a momentum. So when dust receives some momentum from photons, so the dust grains can be accelerated. Okay, so the radiation now can accelerate dust grains to, so the radiation pressure now help launch stellar winds and galactic winds. And another effect is dust grains, in some cold region, dust grains can be covered with ice mantles. And within the ice mantle, many chemical reactions are taking place. So the ice mantle here receive a photon energy, and then ice warm up, and many new chemical reaction takes place. So it can form complex organic molecules, even the building block applies, and those molecules will be dissolved when the ice mantle are heated to higher temperature. So that is a fundamental processes. But photons also have not only energy, momentum, but photons also have a spin. Okay? So for example, the interaction between dust grains with photon spins can spin up the dust grains. So for example, if the dust grain is spherical and a beam of radiation contain many photons, and photons can have a left-handed spin or right-handed spins. If the spherical grains receive only the right-handed photon spins, so the dust grain can spin up along the right direction, but in the interstellar medium, the dust grains are not spherical. So if the radiation is unpolarized, that means it has the same amount of left-handed and right-handed photons. Those spherical grains are not spun up. But in the case that dust grains are helical or non-spherical like this, okay? So even the radiation is polarized because of the helical shape of dust grains. The interaction between the helical grain with left-handed and right-handed photons are very different. So that means after a scattering event, the dust grains can receive a slightly more momentum from left-handed photon than right-handed photons. So as a result, the dust grains can be spun up. But that is the explanation in terms of quantum mechanics. But dust grains are quite big in the size, like 0.1 micron. So one dust particles contain million atoms. So we cannot use the quantum mechanics to describe the behavior of dust grains with interaction with radiation. So the classical mechanics seem to be very useful, and it also provides accurate description about the interaction between dust and radiation. So in 2007, we proposed a very simple model for a helical dust grains. So the helical dust grain here is consisted of one massive body and a mirror. So this becomes a helical grains. So if we have a beam of radiation coming from the left, so photons will be reflected from the mirror and it will produce a momentum or radiative force. So this force is acting off the center of mass. So that means the force here will induce a radiative torque to the center of mass here. So this is a simple model, but it can capture fundamentally the interaction between helical grains and radiation and describe how radiative torques are produced. Yeah, so because of the radiative torques, dust grains can be spun up to a very fast rotation. And one of the consequences of radiative torque spin up is if the radiation field is very strong, so the rotation rate of dust grains can become really, really large. For example, if the dust grain is located next to a massive star or a supernova, so the rotation rate can exceed 1 billion rounds per second. And when the dust grain is spinning very fast, the matter inside the dust grain is now experiencing some centrifugal force. So the centrifugal force tend to tear the material apart. But within the dust grain, because atoms are bonded together by chemical force or van der Waals forces. So if the centrifugal force exceeds the binding force that hold dust grain together, and then now the dust grain disrupts into different fragments. So we can estimate the critical size for dust grains that can be disrupted using this simple formula. So U here is the strength of radiation field, and S max is the maximum tensile strength. Okay, so the tensile strength of material was not very new parameter. Even back in 16th centuries, Galileo and Da Vinci, they already study about the strength of matter and tensile strength. But using this mechanism to understand the dust evolution by radiative torques was recently noticed. For example, in 1972, Edward Purcell, who studied also the alignment of dust grains, so he noticed that the dust grains, when they spin very fast, dust grain experience centrifugal force. But he's concluded that for interstellar dust grains, centrifugal force is not enough to disrupt grains. And later on, Bruce Wren, when they studied the dust in our solar system, they recognized that some dust grains can be disrupted by centrifugal force, but they didn't provide a very quantitative description about the disruption and critical size for disruption. Okay, now the implication. So usually we know that the dust grains evolve due to the thermal evaporation or due to the grain-grain collision. So those are two well-known mechanisms that describe grain destruction in the universe. But now we discovered a new effect. So the dust evolution now is driven by grain spinning. Okay? So when grains are spinning very fast, they are disrupted. So that now near the radiation source, the grain size on average vary with the local condition. Outer region here, the radiation intensity is lower, so we expect that grains are larger. In the vicinity of the source, due to strong radiation, grains are spinning faster, so smaller grains are dominant. In terms of the dust composition, due to disruption, so initially if grains are located in very cold and low intensity, low radiation region, so all grains are mixed together with different composition, silicate, carbonaceous. But when they are exposed to strong radiation, now the disruption now tend to split grains of different composition apart. So initially we have a composition like this, but due to disruption now we have a separate silicate and carbonaceous grain. So this is the evolution in terms of composition. And there's also the evolution in terms of grain shape. So when grains are spinning faster, the centrifugal force are stronger. So, you know, due to the rotation, the grains now become oblate shape. Okay, so the elongation actually increase with the rotation rate. Of course, if the rotation is faster, and then the whole grains will be disrupted. So the elongation now here increase with the rotation rate, and that means it increase with radiation field. Now, let me move on to using dust to study magnetic fields. So even from the early 1949, Ho and Hühner to scientists from the United States. So they independently discovered that the light from stars is polarized in optical. So the segments here show the polarization vectors from star, and this is a galactic plan. And it seems that in the galactic plans, all the polarization vectors are parallel. And at the time, they quickly recognized that the starlight becomes polarized because when stars initially unpolarized, but stars light is passing through the interstellar medium consisting of gas and dust. Because gas is very quickly interacting with optical radiation. So dust grains are dominantly interacting with radiation, and the dust grains is a main agent that causes the polarization of starlight. So the dust grain is like a polarizer here. Okay. So initially the light is unpolarized. Electric field is oscillating in z direction and also the direction. But after passing through the ISM, the light is oscillating only along the direction. So it becomes polarized. So using the polarization of starlight now, we can trace the magnetic fields in the interstellar medium. And recently in 2015, the Planck satellite discovered the polarization in far infrared. So this is the whole galaxies, but it is seen in polarized dust emission. You can see the texture here are also parallel to galactic plan, but in the high latitude here, the texture seem to be changing. So the thermal dust polarization here can also tell us about magnetic fields. Yeah. Okay, so now grain alignment. Yeah, so dust grains must be aligned in order to produce the polarization of starlight. And for example, if the dust grains in the interstellar medium are elongated and they are aligned with the minor axis parallel to the magnetic field, the magnetic fields are in the direction. So the light from stars is polarized with the polarization vector along the minor axis. Why? Because initially the starlight is unpolarized, so the electric field is the same along the long axis and minor axis, short axis. But due to the absorption of many dust grains, so the absorption is stronger along the long axis than along the minor axis. So the light that passing through the ISM has electric field dominantly oscillating along the minor axis. That means it is a direction of polarization. For dust emission, the dust emission is opposite to absorption. So the emission is dominantly with electric field along the long axis. And along the short axis, the electric field is much weaker. So the dust emission has a polarization vector along the long axis. And you see that it is perpendicular to magnetic fields. So by observing starlight polarization, we can directly obtain magnetic fields. But if we observe the dust polarization in long wavelengths, we have to rotate polarization vector by 90 degrees to get the magnetic field. Yeah, so now we have many facilities, many advanced telescopes to observe magnetic fields using dust polarization. Okay, you can see here ALMA, as in future we have a near future we have SKA and all other telescope here. So with this fleet of telescopes, we can observe magnetic fields from multiple scales, very large scale to small scale. And here is the whole universe seen in dust polarization. So it's the magnetic fields in filaments, star-forming region, in massive star-forming region, in galaxies, and even when the universe is still young, at redshift z equal 2.6. So magnetic fields are very everywhere. But the open question now, what are the true 3D structures of magnetic fields? So the dust polarization we observe only provides 2 dimensions. So the opening question is, what is the real 3D structure of magnetic fields? And the 3D magnetic field structures are very essential for us to accurately understanding the cosmic ecosystem. For example, for understanding the cosmic ray transport, the formation of stars, planets, these and outflows, black hole growth and feedback, modeling for galactic foreground for CMB mode. So deriving 3D magnetic field structures is very important. And recently, we propose new techniques that can allow us to derive 3D magnetic field structure using the dust polarization fraction combined with the alignment theory. So if we can accurately predict the alignment degree, and we combine with the polarization level that we observe, and then we can derive a 3D magnetic fields. But it's very challenging to develop an accurate alignment theory. Okay, so other effects of the alignment. So grain alignment can also affect the dust evolution in terms of grain growth. So when we mention about the evolution of grain shape driven by rotation, it is due to the centrifugal force. And here, grain alignment can cause the grain evolution in shape because of grain growth process. So grain growth is a process in which tiny grains can grow in size. So initially they are very small in nanometer, and then they grow by accumulating more gas and dust and become big enough, like a micron size, even pebble size, or even some the seed for planets. So all the current theory for grain growth does not take into account the effect of grain alignment. So if grain alignment, it determines now some direction, the accretion is more efficient than the other. For example, in this case, the gas accretion, if grains are not aligned, so the gas accrete to the dust grains isotropically or equally in all direction. So the grains will grow in the size, but the shape doesn't change. But if the grain alignment is taken into account, so the accretion is dominantly along some direction of alignment, and then it will produce elongated shape like it. So in this picture of grain evolution, the grain growth not only increase the size, but it also increases the elongation of dust grain. Okay, that is something. 10 more minutes? Okay, thank you. Okay, so now let me touch into the fundamental physics of alignment. So how dust grains can align with magnetic fields? So it's like you have a compass needle, and you have the compass needle can interact with magnetic fields because the compass needle have some intrinsic magnetic moment. So you can think of dust grains like some compass needle. Okay, so so dust grains actually they contain iron atoms. Okay, so the iron atoms, for each iron atom, it has a 4 unpaired electron spins. Okay, so one iron atom is very quantum compass needle. And when this iron atom is incorporated into the dust grain, so the dust grains become a compass needle. So the dust grains become a paramagnetic material. If the dust grain is at rest, because of some thermal fluctuation inside dust grains. So all the quantum magnetic moments have a random orientation. So the net magnetic moment is 0. But when the dust grains are spinning, so that means the dust grains have some macroscopic angular momentum. And though angular momentum are shared with electron spins, so electron spins will become aligned along the spinning axis. So the spinning dust grains induce a magnetic moment for the dust grain. And now the magnetic moment can interact with ambient magnetic fields, and it results into the coupling between dust grains and magnetic field. And how about alignment? Yeah, so the alignment here is we have a now 3-body system: the dust grains, radiation, and magnetic field. Okay, so it's quite a complicated problem, but we can simplify it. So in the dust grains here, when it is interacting with radiation, it gets some radiative torques. And due to the interaction between magnetic moment and magnetic fields, the angular momentum is precessing around magnetic field here. Okay, so the radiative torques can be decomposed into the spin-up component along angular momentum and the alignment component perpendicular to angular momentum. So the spin-up try to spin up the grains, and the aligning component here try to change the orientation of J and B. So for some models, the alignment torque here can bring the J to be aligned with B. So that results in the alignment of angular momentum with magnetic field. So this is the picture for the RAT theory. Okay. So the alignment of grains with magnetic field is purely determined by radiative torques. And here how you can see the alignment. So initially grains have a random orientation here. And when we exert radiative torques to dust grains, the grain orientation change. That means the angle between J and B is changed. At the same time, the angular momentum also changed. So you can see that the grains will be driven to Z attractive point. We call it high J attractive point and Z attractive point and low J attractive point. So this low J attractive point has an angular momentum comparable to the thermal angular momentum. And in this case, this low J attractor can be stable because we don't take into account gas randomization. Of course, high J attractor point is stable because it has a higher angular momentum. So the gas randomization do not affect it. So in some other model for radiative torques, we only have a low J attractor and there's no high J attractor. This is a repeller. So depending on the grain shape, size, the low J attractor is quite universal, but high J is very uncommon. And this has us a problem on explaining why the alignment of dust grains seem to be quite universal and quite efficient in our galaxy. And this is the shortcoming of the RAT theory. Okay, so in 2016, we proposed a MRAT theory. So basically, it's a combination of radiative torques and magnetic relaxation. So the effect of magnetic relaxation is that it induces a magnetic torque. So the torque component here tend to reduce the angle between angular momentum and magnetic field. So in addition to radiative torques, now we have one additional magnetic torque component that can align angular momentum with magnetic field. So you can see that we have a high J attractor point here and low J attractor. Okay. So the magnetic relaxation help to increase the fraction of grains with high J attractor, and high J attractor become quite universal. It becomes independent of grain shape and size as long as they have a high level of iron inclusion. Yeah, so now we take into account the collisional excitation. So in the case of no gas randomization, low J attractor can be stable. But when we take into account gas random collision, okay, this attractor is not stable because because the gas randomization try to randomize the orientation of grains here. So grains located at this attractor, they will be randomized. And then when they are randomized into the phase space, they will move in all random direction. And if there is a hydro attractor, so the grains are quite smart. They will randomize, and then they will ending up in the more stable point here. You can see that grains will eventually be driven to hydro attractor. And then the alignment degree increase over time because of the transport of grains from low J to high J attractor. You can see here. So the alignment degree increase over time, and then it will become perfect. Okay. So the MRAD, including gas collision, it can help to drive grains to perfect alignment. Yeah, so here we developed the numerical course to connect theory to observation. I think Chum will be talking more about the Daspo Pi code, and Zhang will be talking about our new Polaris code. I will skip it. And then now I talk about the general MRAD. Here. Okay, so we consider now the general astrophysical condition. So for astrophysical condition, we now using some parameter. So we characterize the astrophysical condition by the parameter U divided by NT. So U is a radiation pressure, NT is a gas pressure. So this quantity can tell us about the local condition and how it is important for alignment. So, for example, for the region where gas pressure dominates over radiation pressure, so we call it collision-dominated region. So the alignment can be perfect, and the perfect alignment can happen over several damping times here, perfect alignment. But if the high J attractor is not present, okay, so grains have a cyclic trajectory. And when the grains are rotating very slowly, they have a random rotation. So if high J attractor is not present, so the alignment degree is 0. So the perfect alignment only happens when we have a high J attractor. But in the region when we have a strong radiation, yeah, so when the radiation pressure dominates over gas pressure, so you can see that even when we have a high J attractor here, only a fraction of grains can be aligned at high J. But the majority of grains are trapped at low J attractor because radiation dominates over gas collision. So grains are confined or are trapped at low J attractor. Okay. So only grains, grains can be aligned with high J attractor. So if we increase the radiation intensity, you can see it's more obvious here. So for example, this is a radiation U divided by NT equals 49, but in this case it's 2000. Okay, so you can see that low J attractor here are more broad than here. So relative torques try to confine grains in the low J attractor. So this effect we call it rat trapping. So it's the opposite to what we believe before. In strong radiation field, the alignment degree now is lower than in lower density region because of relative torque trapping. And because of trapping, grains at low J cannot be transported to high J by gas collision. So this is something really opposite to what we usually think about the MRAD mechanism. But this is something really interesting. And then we can test the prediction using dust pollution observation in strong radiation field environment. Okay, so let me go to the, So this is the general MRAD theory. So we cannot apply the MRAD theory developed for one interstellar medium to the whole universe. But we now need to carefully consider the local environments. In the collision-dominated region, the alignment can be perfect. Okay, and this is a ISM and star forming region. But in the radiation-dominated region, for warm and hot dust, like in debris disks, in kilonova, supernova, and Evo star. So we have an effect, rat chopping, and the alignment is imperfect. And disruption is also imperfect. So we have two different environments in which we have to carefully consider the different effects. Okay, is a summary of my talk. And so hopefully we can better understanding the dust alignment evolution in the universe based on the general MRAR theory. Thank you very much.
Yeah, thank you very much, dear. Yeah. So, any question or comments? Yeah.
Yeah, thanks for the comprehensive talk. I have a question about the magnetic relaxation. How is it different from the discussed Barnett relaxation and the nuclear relaxation in the 2007 theory?
Yeah, so that is, yeah, sorry. Yeah, so basically the paper in 2016, we discussed about the effect of magnetic relaxation. And in that paper, we discussed the typical environment is interstellar medium. So that means the radiation field is weak. And now with this formula, in 2016, actually, we don't have the term FIR here. So in the 2016, the FIR here is the infrared damping parameter. So FIR is proportional to the radiation strength. So if FIR is less than 1, so it returns to the our 2016 paper. But now in this work, we take into account the FIR, so that you see the critical magnetic relaxation required for high J attractor must increase in order to produce high J. So here you see, so this is a 2016 paper. Okay? So high J attractor are universal when delta M is larger than 10. You can see here. But
how does the infrared flux affect the relaxations?
Oh,
it
it doesn't affect magnetic relaxation, but the high J attractor here are the result of competition between magnetic relaxation and radiative torque.
Oh, okay.
Yeah, so you can see here, example.
Be brief. There is another question, online question. Yeah.
Okay, so here you see the radiative torque and magnetic relaxation. Of course, if radiative torques alone can produce high J, and then we don't need magnetic relaxation. But if radiative torques do not produce high J, and then in that case, we need magnetic relaxation to be faster than radiative torque disalignments. So imagine that radiative torques can have a high J or no high J. So in the case of no high J by radiative torques, magnetic relaxation act to create high J. And then stronger radiation, radiative torques are stronger. So magnetic relaxation must be faster. And then we have to increase magnetic relaxation to produce high J in strong radiation field. So that is it.
Yeah. Pravas, an online question.
Yes, sir. Am I audible? Hello? Hello, sir. Am I audible?
Yeah, we can hear you.
Okay, sir. Thanks, sir, for a very nice talk describing the full picture of drain alignment and disruption. My question is, it's a simple question that in the beginning of the slide that about the starlight polarization, it's mentioning that my question is that sometimes the background stars they can have some intrinsic polarization also. So when we measure the polarization, how can we conclude that the measured polarization is actually from the aligned dust grains? Because the background starlight can also have some, in case, some intrinsic polarization also.
Okay, that is very interesting. So, of course, um, some stars may have an intrinsic polarization, but there are many stars. We know that they are not magnetic stars. So for stars that have a intrinsic polarization, they may be magnetic stars also. But for the majority of stars, standard star, we know they have a very low level of intrinsic polarization. So if we observe stars that have a polarization level of few percent, it is unlikely due to the intrinsic polarization level.
Okay, sir. In case we have some high polarization,
For most of stars, the intrinsic polarization level is quite low, especially in optical. So starlight is thermal emission, not a signature polarization. So thermal emission from black body object. We know from physics that the polarization is negligible. That is the nature of thermal emission from black bodies.
okay.
The polarization we observe is not due to the intrinsic nature, but due to the environment that the light is passing through.
Okay.
Okay, sir. Thanks.
Our speaker again.
Thank you.
Okay. I myself have a question, but we have Tim here for the whole week, so we can talk to him during the meals or coffee breaks. So let's go to the next talk. The last talk of this session will be given by Dr. Lê Ngọc Chấm. He's going to talk about grain alignment and dust polarization theories, myth observations. Okay, so we are a little bit behind schedule. So, okay.
Okay, can we start? It's a bit late, but it's okay. Okay, so good morning, maybe afternoon, evening, everyone. So I'm Cham. I'm right now the postdoc researcher at Leiden University, and also I'm the guest researcher at Max Planck Institute of Radio Astronomy in Bonn. So I just continue the story of Tim about the grain alignment. So I'm talking about a little bit about the theory of grain alignment and how we can apply the grain alignment in real world data application. Okay, and so first, what's the motivation? Why do we care about dust polarimetry? So we know that the dust in ISM is about 1% of mass, but very important because that we can determine the structure of the interstellar medium, the physical process of interstellar medium, even though can form the star, and from the star we can form the planet like the Earth, and so on, right? And usually that enhance also the ADN, like the cosmic like organic complex molecules, and the source of heating, cooling also, and it's sort of very difficult to constrain. That's something else. And as you know, in the modern theory, modern physics, right now we want to understand the universe. And in understand the universe, we measure something we call the cosmic microwave background CMB. But unfortunately, the CMB, it really dominates the band of wavelength we are working on, really contaminated by the foreground dust polarization. So we are the enemy of the CMB community. They want to kill us. But so we try to help the CMB community to have the better control of cosmic ray, that's called CMB. Okay, I didn't talk any things about the magnetic field of dust polarimetry. During the workshop, we will have a lot of talks about that. But in principle, we can use dust polarimetry to infer a cosmic magnetic field. Let's say let's say we have the simple case where we have the dust grain aligned with the ambient magnetic field perfectly. So we have the unpolarized background star through this dusty cloud, and we have the absorption, we have the extension, we have the polarized, in this case, parallel to the ambient magnetic field. So which is called the starlight polarization or extension polarization in the near UV, optical and near infrared. In this other case, the dust will absorb, will emit at longer wavelength as a thermal emission, and that thermal emission also polarized. In this case, the polarization is perpendicular to the ambient magnetic field. So from that, we can infer back the magnetic field indirectly and also the strength. And we were talking about that. I'm not talking about that, but others. But how the alignment physics, how does grain align with ambient magnetic field? So Tim talk about that. So I think I saved time for our lunch. So know about that. But that's a very, very interesting macro physics where we have the free electron in the paramagnetic material or superparamagnetic material. And each electron has a tiny magnetic moment in the vector here. So if we rotate it, you know in physics that all of them will align in one direction in the perfect case. And they will develop the net magnetic moment, and then they will coupling with the ambient magnetic field. So the story of the grain alignment is not straightforward, and back and forth, back and forth. So that's a very nice slide from Tim. So we start everything from the 50s of the last century by paramagnetic relaxation by Davis Princeton or DG mechanism. And then developed through like Brousseau, Fizer, Alex, Bruce Grant, and also we back to from the beginning, after 80 years something, and then we have now we have the relative top alignment theory or RAT paradigm. So that's the picture. If you want to know the picture of RAT alignment theory, we have the non-spherical dust grain, we have the incident radiation field, we rotate it, and we magnetize dust grain, and then we coupling with ambient magnetic field. And the process, the dynamic of dust grain, exactly like the spin toy when you play when a kid. So I have this here. You want to play, I can show you how to do it in here. So, and here I just show you one, the experiment for the rat rotation. So a long time ago, maybe 20 years ago. So they shot the laser, optical laser to the chamber. They have the dust grain in here, and they see every 40 seconds, in this case, they see the dust grain rotate. And then when they plot the rotation rate or the angular velocity as a function of radiation intensity, they see the linear relation. So more radiation intensity, dust grain, particle, dust grain rotate faster. And again, the theory from Tim, they with Alex, they call the analytical model, AMO. They have the wireless mirror attached to central dust grain. They shine computerly radiation to it, and they calculate the rotation of the dust grain or angular momentum of the dust grain. So you, maybe it's better here. So you here at the thermal of the dust grain weighted to the thermal angular momentum at gas temperature as a function of psi here between magnetic field and the angular momentum J. And they found of the most grain, they drop at here where we have the low angular velocity momentum, have a low J attractor. And a lot of grains attract here at the point A and point P called the hydra attractor, which is more solid. And after that, Herenen with Tim and Alex and other people, they use they generate, how do you say, the computer-like or astronomical-like dust grain, and they calculate again how much dust grain drop at hydra attractor. Okay, and in the typical interstellar medium here, they show us a function of angle between magnetic field and angular momentum here, and they found a minimum, the average of about 50% of dust grain rotate at hydra attractor, meaning that the rotation is kind of robust and universe. And if somehow you include or you give the iron inside the dust grain, you translate the magnetic property of dust grain from paramagnetic to superparamagnetic material. In this case, the coupling between the rotation of dust grain and magnetic field become stronger. And in some case, 100% of dust grain can rotate hydra attractor. And here again, it's just experiment in the physical review letter. So they have the chamber, they levitate the dust grain, they shine the laser again, the optical laser, to that non-spherical, and then they measure the angular velocity again. And now it's a function of gas pressure, which in they measure it's a function of randomization, because you know that rotating dust grain, they will transfer the momentum to the gas and they become slowing down. And you show when they increase the gas pressure, the angular velocity going down. And when you compare the theory from the relative torque, you see that kind of perfect match, talking about the slope, if not actual value, but still very nicely. So what happened? So Tim mentioned already, when you spin the non-spherical too fast, you develop the centrifugal force, and that force tries to break a material again, apart, sorry. And with Tim, we try to do some calculations. So the y-axis is the angular velocity as a function of grain size. So when grain size increasing, the angular velocity increasing. At some point, if the material is not compact enough, characterized by they call the maximum tensile strength here, and that velocity will be higher than the maximum angular velocity that grain can achieve. Okay, by that time you can break the material apart. So in this case, the relative torque alignment, relative torque disruption, and it really depends on the structure of the dust grain. If it very ideal like the carbon, no, sorry, like the dynamite here, we cannot break anything by rotation. But if the dust grain is kind of composite structure, we can break it to smaller size. Your question, maybe you might ask, do we have the porosity dust grain in interstellar medium something? The question is yes. So show you here on the top left, is the dust grain collected from our atmosphere, the top, the stratospheric layer of our atmosphere. So I don't know how they capture it. On the here is from the lab. So they have material, you shine the laser, you dissolve material atom, and then they cooling down, they attach to each other, they form aggregate dust grain, and you see kind of structure. And here, that's the proposed dust grain come from the quantum calculation from the computer. And here is the 3D print. I took that picture at the Bochum University in Germany, where they have the group working on the dust structure. Here you see they have something, and it's composite-ish in the interstellar medium. So, and we come up in the team's idea as well. So we came up when we have the composite dust grain exposed to a very strong radiation field, we rotate too fast, and we can break it by torque disruption. So, and the combination between the rad alignment theory and disruption, we call the rad paradigm right now. And if you remember from the beginning, we start the theory of grain alignment from the DG alignment or paramagnetic alignment to rad. It doesn't mean that DG mechanism is wrong. It's just we had a company. So that really depends on the grain size. So let's say that depends on grain size. A align here is the minimum grain size that rad will be effective align dust grain. Okay. Because you see if that the Q here in the rad, the derivative torque efficiency is reduced very significantly toward the to smaller grain size. Sorry, and if the grain is so very small, the derivative torque is inefficient. Okay, it really efficient when grain size greater than alignment size by rad. Lower than that, we have another mechanism. Really the DG magnetic or paramagnetic super or paramagnetic relaxation. And if the dust grain is kind of nanoparticles, we have another mechanism. Okay, Tim said, explain about the resonance relaxation. Also, we have the gold alignment is there. So I don't cover this part in here. So first thing, let's calculate a little bit about the degree of grain alignment to see how efficient the grain alignment would be. In principle, it's a complicated process. So again, we have the internal alignment between the angular momentum J with the principle, the rotating axis of dust grain, the minor axis of the non-spherical dust grain. They can characterized by the QX. So you need to calculate that. And for the external alignment, it's the coupling between the angular momentum J and the magnetic field B. And the net alignment degree is the cross section of the product between the two. So here I show you my calculation of the DG alignment efficiency as a function of grain size. So that's the internal alignment that doesn't depend on the grain size. It doesn't on the physical parameters of environment like the gas temperature, dust temperature, and magnetic field, so on. And we have the external alignment, and here you have the net degree. And if you increase the magnetic field strength, you align more large grain by the DG mechanism. And that's for the external alignment. So Tim show again. So again, now is the degree of the rod alignment as a function of the magnetic susceptibility of the dust grain. So if you have a lot of iron inclusion in dust grain, you come up with something like MRAD theory, okay, where almost the alignment is perfect. It's 1 meaning 100%. And it really, really depends on the angle between the radiation field and the magnetic field. And if you have the MRAD, doesn't matter. Okay, if the rod theory, it matters. So we have something with the grains lower than alignment size and something with higher than alignment size. Okay, and how we can calculate the grain alignment. So we parameterize more or less. We call alignment function. So again, if grains is smaller than alignment size, we don't have rod theory here. We have the, for example, DG mechanism. And if grain size is bigger than ALI, we have the rod theory. Okay, we can parameterize by something called the alignment function. Okay, and F-min and F-max are corresponding to the minimum alignment efficiency and maximum alignment efficiency of dust grain. Okay, and they have so many in literature. They have so many forms of it. Some of it. One of which I name it. My personal name. I call the FA. So some from Tim 2015, from Wang Song Guillet 18, also from Heseng Lee. She's here in 2020. You see the form a little bit different, but almost show you how alignment efficiency changed from the smaller grain size to larger grain size. And then from that, we know a little bit, not too much, but a little bit about the theory and how we can apply to the data, to the observational data. No way, except we need to develop the numerical or simulation, okay? So in this talk, I'm talking about the dust polarization pi. So I mean a Python base. This is simple model. And Yang, I don't know when, but maybe tomorrow, after tomorrow, she will talk about more complicated with the Polaris plus here. So what we can do, so for example, here I show you the multiple wavelength spectrum of both a starlight polarization on the left and the thermal dust polarization on the right, multiple wavelength, okay? And we can work right now, the model can work in the diffuse molecular cloud star forming region in starlight spore. And we will release a new version with the protostars and also the planetary disk. And we have the installable package. You just go to that website and you follow the step to install, very easily to install in your computer. And we have the manual website for you to follow step by step. And also, we can give you the prediction for extinction curve as well, also the SCD. So here show you the example of the SCD in the combination between the pH and also actual dust, and you see a lot of pH feature here, and that the thermal dust from actual dust, and combine you have the total spectrum here. So we can provide you 3 different quantities to compare to observation. And if you don't want to install everything, we have another option for you. We design the interactive website or tool here. You can go to that website, you can change parameter, and then you can plot the spectrum of thermal dust, of starlight and thermal dust, and also you can download the ASCII file to your computer and you can plot by your own, okay? I think it's useful to see when you write in the proposal. I mean, it's good to just go to website and click, and then we have some number. Okay, so what next thing, how model can do the job? So first thing, let me back to my age, so that the observation of starlight polarization in the 1990s by the Wolf telescope or the Hubble. So in the Wisconsin, I think, satellite. And so all the dot here, actually all the side of light side measure starlight polarization. And most of spectrum follow, you see very nicely the smooth curve here, follow the Sexkowski curve proposed in the 80s in the last century. But the problem that we have some satellite, about 7 out of 28, they don't follow, for example, here they don't follow the Sexkowski curve. In the UV and far UV band, you see the excess of the polarization degree is higher than the Sexkowski, the Sexkowski curve. In this case, they call the super Sexkowski curve. Okay. So what does it mean? And then let's take 2 examples. So we take 2 examples, 2 light side. The first light side called the HD to the background star, the HD 37903. And the second one is the HD 3614. So the first case we see the Sexkowski curve. Okay. In the second case, we see the super Sexkowski curve. And now we plotted the wave number reverse of the wavelength. So the circle, the dot, are observations. On top, from the WHOOP and Hubble telescope observation, and here is the extinction curve observation, okay, by the FM and CCM model. And our model can do the job, can fit simultaneously both starlight polarization and extinction curve to the data. So the dot here, that's the Markov chain Monte Carlo fitting from our dashboard PI to the data. Okay, both simultaneously. And we can, you can see, not perfect, but our model can reproduce quite nicely the Sexkowski curve and also the extinction curve in this case. And also we can, not here, we can reproduce the super Sexkowski curve and also extinction curve in the second case. So when then we infer the grand side distribution, so we add up the grand side distribution from Astrodust proposed by Hensley, Brandon, and Brent recently, the same form, which will vary the parameter, okay? And in the case of Sexkowski curve, our constraint of grand side distribution exactly the same as the one from Astrodust, from the Brandley and Brent. But for the second case where we have the super Sexkowski curve, we see the difference, where we need to have higher small grains than the diffuse grain size distribution in order to reproduce the super Sexkowski curve, which is expected, right? Because I explained to you, we need to have the DG alignment in order to explain the super Sexkowski curve. And then when we come back to the calculation of the DG mechanism, above, again, on top, about the Sexkowski curve, and the bottom for the super Sexkowski curve. And to reproduce the Sexkowski curve, we just need the typical interstellar medium radiation field, the typical diffuse grain size distribution, and the gas temperature more or less the same as the dust temperature. Okay. But in order to have the super Sexkowski curve, we need to have stronger radiation field. We have more small grains. We have higher gas temperature in order to make the DG mechanism more efficient, because we have the distribution energy to the heat. And also we need to have the stronger magnetic field, for example, this case 70 microns compared to 30 microns, but not really. I think that's just a question mark here. We need to check. So next thing about the thermal dust polarization, I show you observation from that Planck. The background is the degree of polarization, and you see it's not uniform. It's somewhere it's high, somewhere it's low, but the maximum about 20% of the degree of polarization in thermal dust. Yeah, we'll talk about that, but with ALMA, we can see that for here, again, here the Planck, the maximum about 15 to 20 degrees. But for the ALMA, it can go up to 30, 40% of the thermal dust polarization. And if you look at to the degree of polarization with the Planck toward the nearby star forming region, so if you look at the black line here, that's the mean. You see as the radiation increase or the dust temperature increase, the degree of polarization increase first and then decrease. That's opposite to the relative torque alignment prediction. Because again, when we have the more radiation field, we expect that the grain alignment is more efficient and we have higher degree of polarization. And here we see the opposite. Again, if we look at the multiple wavelength of thermal dust polarization, in some case, we see the monotonic increasing of the degree of polarization as a function of wavelength. For example, in the BNKL, Orion, OMC1 here, and KHW in the OMC S1 as well. But in some cases where we have the multiple wavelength, we see the drop, we see the V-shape of the spectrum. The degree of polarization decrease first and then increase. So that's called the V-shape of the spectrum. So how we can explain those things? And if our model works, it should explain those. So first thing, back to the simple things about the gas randomization. Is that very beautiful work by Ngọc. She's here as well. So she looked at the Musca filaments using Planck data, and she selected this area where we don't have any embedded source activity inside. And the background show you the degree of polarization at 850 micron as a function of distance from the left to the filament to the right. And she used the model to compare to observation, and the best observation show you by the color lines on top of the data. And you can see the model can reproduce quite nicely the depolarization by the gas randomization in the middle and spike of the filament. And here, that is the beautiful work by Hesung as well. And again, she calculate the degree of polarization as function of radiation intensity or gas temperature or dust temperature. And in the case of only rad alignment theory, we see the monotonic increasing of degree polarization. But when we turn on the disruption, we destroy the large dust grain, we repopulate the small grains. So we reduce the degree of polarization toward the higher dust temperature. And where that drop really depends on the structure of the dust grain. And when you compare to the Planck data, you can see kind of nicely, we can explain the phenomena where we see the decrease of the thermal dust polarization toward the longer, toward the higher dust temperature region. And only problem with the Planck is that the spatial resolution is 40 arc-minute, which means a lot of things can happen within the beam. So we need to have the higher resolution data to test. And of course, we have Sophia Hot Plus with the higher resolution in about tens of arc-second. And we look at the kind of ideal target in the Ophiuchus A when we have the one massive or intermediate mass and we have the nearby cloud. And on top at the dust temperature, close to the star, we have the higher dust temperature, and further away, we have the lower dust temperature. The bottom is for the gas density, closer to that because the feedback, so they push material away, so the gas becomes denser further away from the source and diffuse a kind of a diffuse close to the star here. But when you look at the relation between the polarization degree at 154 micron in infrared right now, the function of wavelength, sorry, function of dust temperature, and the data show you in the background color. And you see the same thing now. First thing, the degree of polarization increasing and then decreasing. And the same model, the same methodology, and if we use both rad alignment theory and disruption, we can explain both the increasing trend and decreasing trend from the observational data with a higher resolution than Planck. And that's a very, very, I think for us, is the good evidence for the Radley mechanism. But that average everything. If it works, it should work for pixel by pixel, again, for the beautiful work by Ngọc. She's here, and she used the data from Sophia Hot Plus at far infrared. So observation show you in the left-hand side, that's the OMC1, Orion, OMC1. And you see that the degree at the far infrared, you see here is the higher and here is lower. And she used our model, no, yes, calculate pixel by pixel basics. And if she consider the relative torque alignment with the variation of the magnetic field within the beam, it's in the middle. And when you compare to the observation to the left, you see more or less can reproduce this area, not the A2 region here, the Champions ionized region here, or the BNKL. So if she use both or all the rad alignment theory, disruption, and also the magnetic field variation on the right-hand side, you can see the march to the observation is much better. So where we have the diffuse gas here, not diffuse, but a low gas density, we have the higher radiation, we destroy large dust grains, so we have the lower degree polarization, and we compare to observation, is much better and also close to the star forming region here. And not just single wavelength. If we work on multiple wavelength again, so I show you the OMC one again. So for the fun fact, every single telescope we build on Earth, the first target we observe is Orion. Okay, so that's why Orion everywhere. So that again, so that's we use the data from the SOFIA Hot Plus in 4 bands infrared, and also the 2 band from submillimeter. And I would like to thank Chin Hee Hong, she's here as well, for sharing with us the submillimeter data from the JCNT-2 with the visual, the visual consortium. Yeah. So we create or construct the multiple wavelength thermal dust polarization towards 12 different random line of sight here. So that show you the random line of sight, the dot. Right now, the observational data from far infrared to submillimeter data, and the solid line are our best model. The conclusion here is our model is completely wrong in some cases. Okay. So for example, in this case, where it's
10 minutes.
Okay. Yeah. So you see our model, the best model is something like this, and the data show you again the V shape of the spectrum. Okay. And our model couldn't reproduce the shape here and also this one. So right now, everything I told you before may be completely wrong, unless we prove that our model is able to reproduce those kind of data. Okay. When we look at the literature, the group in Heidelberg, in Germany, they use the near-infrared and some others. They construct a 3D structure toward Orion molecular Orion filaments, and compared to California filaments. The difference here along a line of sight to Orion A filaments, we need to have multiple layers of dust instead of one layer. So our model here just use one layer dust model. The failure of our model may be due to the fact that we just cannot consider enough dust layer along a line of sight. Okay, and then we improve our model. We add one more layer in the model, the hot dust coupling with the cold dust along a line of sight. Okay, and that's our best model right now. And if you look at the same region right now, our model are able to reproduce the V shape of the spectrum here. So here for the hot dust in the short wavelength, and here is the cold dust for the longer wavelength. And now if we're coupling the starlight polarization and thermal dust polarization, the ideal targets will be starless core. Okay, I show you in one example of starless core. They have the Pi 109 in the Pi Nebula. So the optical polarimetry is here. Closer to the center, we have the near-infrared polarimetry, and on top, the middle of the starless core, we have the submillimeter tracer cold dust in here. And if you look at the trend between the degree polarization in starlight to the left-hand side, the function of AV visual extension from outside to inside. And that's for the optical, that's for the near-infrared. And if you look at on the right-hand side, you have the relation in the submillimeter. You see they vary. And that's our model, the best model, for the starless core 3D space now. So on the top, again, so that the optical polarimetry look to the left axis, and that the near-infrared polarimetry, and that for the submillimeter polarimetry looking on the right. And what you can see here in the first panel, top panel, we fixed the grain shape. We just vary the maximum of grain size in the distribution. And we can see that our model can nicely reproduce both optical and near-infrared polarimetry, except the submillimeter. We see a lot of outliers point here. We cannot reproduce the data here. So if we keep the maximum grain size constant, we vary the shape, we increase the shape of the dust grain more elongated. Now we can see that we can reproduce much nicer to the observational data. Okay. But we fail to explain the near-infrared wavelength here, near-infrared polarimetry here. So the conclusion is here, from outside to inside of starless core, the dust grain must be larger in size and be bigger or more elongated in shape in order to reproduce both starlight polarization and thermal dust polarization. Okay, that's for us the evidence of the how to say the anisotropic brane growth. Usually, but my bias speaking because the introduced by team here basically. But we don't know which picture is correct. The top picture or the second picture. The top picture is that we have a very solid compact dust grain, or the C13 aggregate dust grain. We have the porosity toward a higher wavelength. Okay, so we need to use the James Webb telescope and also more evidence. And it just show you why that anisotropy grain growth. So if grain align and they collide to each other, they coagulate to each other, they will form more elongated and bigger in the dense region. So that's our evidence for this mechanism proposed by team here. So in order to answer which mechanism, the compact structure of the dust grain, now we're working with one student here in Vietnam, I think she's here, here as well. So we mix ice mantle with the silicate core, okay? So show you here the red curve here, that the capacity, the absorption efficiency weighted by grain size for the actual dust in the solid curve, and the black curve here when we mix the ice mantle on top of the dust grain. So we see some ice feature here when we coated the material. We have some 3 micron, 6 micron feature of dust grain. So now it's just ongoing project. Now she will predict the SCD, project the SCD and something compared to transparent, and then to see whether or not we have the ice mantle in this. And also, when we have enough confidence about the starlight polarization and thermal dust polarization, we need to go in the middle, the mid-infrared, where we see the interplay between the thermal dust polarization and also the starlight polarization. That's very hard. And there will be the student from the Algeria working with me at Leiden. She will come in maybe in a few weeks. We will work on the mid-infrared, and we have the atlas, a lot of the literature of a lot of line of sight, measuring about 10 micron or 20 micron of line of sight. And here's one example from the, Brandon and Bruce to show that the model with the actual dust are able to reproduce both. And we need to do it again, decompose between the starlight and thermal dust polarization for much more data. Next thing, Bao doesn't like me to show here, but from the thermal dust, from the dust polarimetry, we can infer the 3D magnetic field. It's not 2D, but we can do it 3D. So I don't have time to explain here. So what we do, we put the output of dust POPI to the network. We use a little bit machine learning here, and then we can predict the 3D magnetic field, also the dust polarimetry at once by training. And the goal is that in future, if you have the data, even though single wavelength or multiple wavelength, you can put our pre-trained model here. You can get out of the information of 3D magnetic field and also the dust probability like shape, size, and other things. What we done so far, we are lazy enough. So I can show you the test case. So on the left-hand side is that the true or the maximum grain size from the model we generate and we put in the machine learning. And the y-axis is the predicted of the maximum grain size from the CNN or from NN. And we see the 1-to-1 ratio line here. What we expect, because we know the true value, right? Because the input from the model and that is predicted from the machine learning, and we see the 1-to-1. So it's good. And the same thing, so that the inclination angle of magnetic field with a line of sight, we know the value because it's the input parameter in the input data to our machine learning. And the y-axis here is the predicted. We also see 1-to-1 ratio, which is very good, but we see a lot of scatter inside here. So we need to improve. I think Bao told me that the correction or correctness is about 70%, 80% something. So we need to improve a little bit to make better correlation in here. So my conclusion is here. Do we completely understand the dust polarization? No, not yet. No, at all. We just started understanding things, not too much. So, but we show that the simple Python model dust POPI with the state-of-the-art alignment theory can be a promising tool for understanding data from single disk observation. Yang Sang tell you a little bit about the simulation with Polaris can work perfectly with ALMA. And we need to have the more statistical evidence or confidence to confirm everything. So we have some students in Vietnam and like Minh and Quang Anh. We will talk a little bit about that. And we have more other students. And we need to have more observations. We will, in the future, we have the UV polarimetry, we have the mid-infrared, I don't know which one, we have the far-infrared, we have the sub-millimeter, and so we have the millimeter wavelength. We have the more data coming up in the next decade. Also, we need to combine the dust polarization spectrum extension, SCD. We've done a little bit, but we need to have more. And also, we need to do the theory again. So with TIM, we're working on that. For example, alignment and disruption for the fluffy or aggregate grains, especially in AGB envelopes or red style envelope. We are working on that. And also the rotation and disruption by mechanical torque. It's not radiation field, but the gas flow right now. We are working on that. And also for the carbon gases, which is diamagnetic material, they feel nothing about magnetic field and how we can align the carbon gases. So with TIM, we have the paper, theoretical paper on that, but only one is not enough. We need to have more. And also the complex composition for the lab measurement. So our colleagues in in Toulouse, they have do the measurement for the optical properties. So we need to do it. And in order to, the last slide, in order to brainstorm together, we have the Great Pole Consortium. So I am PI with team in here, and we have theorists like Alex. We have the observer like PG Anderson, like Enrique and other people. So we combine both theorists, modeler, and observer. And also the aim is to study the stellar and thermal dust polarization to constrain the physics of sub-millimeter, submicron, and micron size dust strain. And so we aim to study the anomalous microwave emission and polarization, for example, with the SKA, the future for the nanodust, so smaller size right now. And also we want to do the single disk and interferometry observation, and that is open consortium. Okay, if you are interested, you can contact either team or me, so we can have the consortium to work together, and hopefully we can have something new in the this industry. So that's the end of our presentation. Thank you very much.
Yeah. Thank you very much, Chung. Yeah. Is there any question or comment both from the room and from online? Maybe let's lady first.
Okay, thank you for the nice talk. I'm Jie. So I have two questions. In case of the Orion data, if there is two layers, is it possible to distinguish the polarization fraction in separate layers?
That's a very good question. Right now, we don't know.
Yeah.
We don't know which layer is which. Okay, in order to have the V-shape, something like that, we need to have the hot dust component and cold dust component. But we don't know the in front and the back, no idea. Yeah.
And in case of a Starry score, in sub-millimeter observations, polarization fraction is larger than expectation. So is it caused by because of the optical observation and sub-millimeter observation can trace different size dust grains, or I'm thinking the Starry score has a low temperature, so it is not affected by the dust disruption because of the low temperature.
Yeah, your second point correctly. In the Starry score, we don't have disruption effect because we don't have the how to say, the inner radiation field. We just have the radiation field from outside. Here, attenuated, like typical interstellar medium, attenuated into the center of the core. So the radiation field is not strong enough to destroy anything here. So everything here toward to the center, from the outside to center, you just have the randomization effect, where we have the low radiation field, but we have the high gas density. So you make degree polarization lower. We just like the rhythm randomization and depolarization effect. It's not disruption here. And the second point is correct. Yes, maybe it's super tiny here. But when the best model compared to optical, the maximum of grain size here is about 0.2 micron. For the near infrared, a little bit deeper in the side, the maximum is around 0.3 micron. And if you go to the middle, it should be 1 micron. So we have the evidence that if you go to higher visual extension, you need to have the higher maximum grain size. And also the shape is bigger, from 1 to 4 small egg to very elongated egg. The ratio is about 3.
Okay, thank you.
Yeah, the next question is from Tim.
So here one more thing is, so you assume the magnetic fields are in the plane of the sky. So the magnetic field doesn't change the orientation from the outer to inner region, right?
No.
Okay. Yeah, so but I think for stylus cores, we expect that the magnetic fields would have an hourglass shape. So the polarization, I mean, the magnetic field geometry would be changing from the outer to inner.
Yeah. So I mean, correctly. I mean, absolutely.
Mhm.
And the things right now, the first thing we need to try in a simple case where we have a uniform magnetic field. And the next thing we need to know, if we know for sure the geometry of the magnetic field, we can incorporate in our modeling here to see what's going on. And yes, we expect that toward the center we have the randomization or the variation of magnetic field, so we can lower the degree of polarization.
Okay. Yeah, I have another question. So when you show the absorption feature of IC grains, so that what is the grain size here? Do you assume?
So the number is here. So the core grain size 0.1 micron.
Oh, the core is 0.1.
Yeah. And the mantle here we mix about the ice mantle. We assume that we vary, but the mass fraction to the core is about 20%.
Yeah. Okay. So I think it would be nice if you can show several plots with different grain sizes. So yeah. So we can see how grain size affect the absorption feature. So like a large grains make the light profile more asymmetric. So based on the asymmetry of the light profile, we can measure the grain size.
Yeah.
So here the light profile is quite symmetric because the grains are small. But if you increase the grain size, it becomes asymmetric.
Yeah, I think Quinn here, if she can say something, comment something. But if we have this, if we mix the ice mantle with the lower volume mass fraction here, we don't see that feature of the ice because it's too thin. If we have a little bit thicker ice, we will see these features here, the 6 micron, right? But we see the very strong 3 micron picture of the ice here, and we see a little bit here on the optical and nothing in the infrared or submillimeter. Sorry.
Okay, yeah, the last question before we go for lunch.
Thank you. So thank you for your nice talks. So can you come back to the slide that you estimate the maximum grain size in the stylus core? So my question is, do you have any estimation about the maximum gas density inside the stylus, inside the center of the stylus core? Because from my understanding, so the theoretical study expect that if the gas density is around larger than 10 to 8, so grain of micron size can form. But inside this stylus core, I a little bit confused of how micron size can be formed and fixed with the observation. So do you have any comments on how grain can grow very fast inside the stylus core?
Great. So here we assume the power law of the gas volume density, the Horner law, and we constrain the maximum of volume density at the center of core based on the AV. So if you see the color bar here, is the AV from observation. So okay, we have the profile of gas volume density. We calculate the AV, map the AV, and we compare to the observation. We see what is the profile of gas density compared to the observation. And in this case of the pipe 109, the maximum is about 10 power 5 particle per cubic centimeter, not too high.
Yeah.
So that means the attenuation is not very, not strong, but it's not really strong.
Yeah, and the second question is when you explain about the super Sokoki law, so you explain that the gas temperature must be larger than the dirt temperature, so that more small grain can be analyzed and explain the super Sokoki law. But for my understanding, that if the gas temperature is high, so the gas damping time scale also very short, and it can make very small grain very hard to be aligned with the magnetic field. So can you comment about this point?
You're right. Why the first thing why we need to have why we can explain the super Sokoki curve that we need to have the very efficient DC alignment on top of that. Okay. In order to have the efficient DC alignment theory, alignment efficiency, we need to have the high gas temperature to make the how to say the dissipation of energy from the rotation to the heat more faster. And when we cannot have too much gas, the ratio between gas temperature and dust temperature need not to be very high. Otherwise, the gas randomization, the damping time scale will become lower than again. So that how would have the lower limit and upper limit of the gas temperature here.
Thank you.
And also we need to have the strong magnetic field, but not for sure. We need to quantify more.
Thank you.
Okay, so thanks a lot, Chum. And let's thank all the speakers of this morning session. And no, I think we have to, we have to finish. And so we will have lunch break from now, and we will be back at 1:30. The lunch is downstairs.
Okay, so hi everyone, welcome back to our workshop. So the first talk in the afternoon section will be delivered by Professor Phạm Ngọc Điệp. Professor Điệp will be talking about the project named Balatpo. And I think Balatpo project was initiated a few years ago, I think during the COVID-19 period. So we were thinking about some potential project that we can collaborate with between Vietnamese overseas and Vietnamese researcher in the country. So far we have several papers published under the umbrella Balatpo. So today Professor Điệp will be talking about this project. So let's welcome Dr. Điệp.
Thank you very much for a very nice introduction.
Yeah, so you will have about 35 minutes speaking and 5 minutes for Q&A.
I think I have only 30 minutes.
Oh, 30 minutes only?
Yeah.
Oh, I see. So you shortened your talk. I see. So sorry about that. Okay. Okay. So please go ahead. So 25 plus 5.
Yeah, sorry, some technical issues. Okay, how can I? Okay. Okay. Looks good. Okay. Yep. For those who don't know me yet, I'm from Hanoi, from the Center for Astrophysics and Science Exploration from Vietnam National Space Center, which is one of the institutions of the Vietnam Academy of Science and Technology. And as Tim mentioned, I'm going to talk about our small project. Hopefully it will be growing bigger, and it's Balatpo. Here is the list of important collaborators, and Pravas and Sadhana will have specific. We'll talk about specific studies within this the framework of this collaboration. Stands for Vietnam Astrophysics Research Network. Here we try to connect people, in particular young researchers, to work together between the inside Vietnam and outside Vietnam. First of all, I would like to emphasize again the importance of 3 objects which we are working with on this project. Filaments, it means filamentary molecular clouds, and diffuse and dust grains. So filaments are natural product during the evolution of molecular cloud, and they are ubiquitous in the interstellar medium. They are the size of core formation, and eventually new stars are being born from that. The stability, evolution, and fragmentation of filaments are key questions in astrophysics. Here I show you an example of real-world filamentary cloud and filaments as products from simulation. The second factor is magnetic fields, and we heard a lot from the talk of our morning speakers. And B fields are thought to play essential roles in guiding gas flows, providing support against gravitational collapse, and magnetic fields also influence turbulence as demonstrated in Alex's talk, and magnetic fields also affect the formation of disks and outflows. The problem here is to characterize the morphology and strength of magnetic fields, in particular as mentioned by Thiam and Chum, that the morphology in 3D is also very important to test our theories. Last but not least are the dust grains, and they are not just obscuration, and they are key for the ISM chemistry. As mentioned by Thiam this morning, they are important for heating and cooling in the ISM. And dust grains are crucial for us because the non-spherical dust grains emit polarized thermal radiation. And from that, we can trace the orientation of magnetic fields, and polarized light also used to probe dust grain properties and the alignment physics. The problem is how to connect the observations of polarization to the underlying magnetic field structure and the complex physics of grain alignment. We see this morning that the dust physics is extremely complex. The complexity is coming from the interplay between the processes, the physical processes, not from the physics itself. We understand the physics, but the interplay between them is complex. So Ballard-Pohl, this is a series of work, and our goal is to systematically investigate the properties of magnetic fields in the diverse interstellar filaments. And the second goal is to test and constrain theories of dust grain and dust grain alignment and disruption. I hope by now you understand very well these processes, and to understand how dust properties, including size and composition, evolve in these environments. Our approach, we use the dust polarization observations from leading facilities available in the field. James Clerk Maxwell Telescope, SOFIA, a flying telescope, and Planck. So we target a range of filaments, quiescent in the case of Musca, massive infrared dark molecular dark clouds in the case of G11, G34, and active star-forming regions in the cases of OMC1, Sapiens Main, and IC 146. And then we combined observational analysis with theoretical model based on the RAD paradigm. So in this talk, I will try to overview the problems we address and our method and some first results. And I try to set the stage for more detailed talks on specific studies, which will follow also in this afternoon session given by Pravas and Sadhana. So the problems, the first one is the polarization hole. So this problem is the the decrease of polarization fraction as function of intensity or density. This is, I mean, popular in many sources that we observe. So the question related to this problem is that we want to understand whether the loss of polarization is due to the grain alignment efficiency or due to magnetic field tangling or the dust grains themselves change the properties. This is a typical case of the polarization hole. And then we want to test the radiative torque alignment and the radiative torque disruption. Yeah. I will not repeat again, but the prediction from the RAD-A is that in stronger radiation field, the dust will be better aligned, and then the polarized emission is stronger. And if the radiation is strong enough, then dust rain can be disrupted, and then the prediction is that the polarization fraction will decrease when we go to very high temperature or radiation field. The next test we want to test is MRAD, magnetically enhanced rad. This is due to the in observations we found some very high polarization fraction, like in this case for G11. There are several pixels that have a very high polarization fraction, which is greater than 15 to 20%. Usually it's populated around 10% or less than 10%. Then we want to study the magnetic field morphology and strengths in a diverse environment conditions. And for example, to understand whether the magnetic fields are parallel or perpendicular to the main axis of the filaments, and how is the magnetic field compared to the turbulence and gravity in terms of so-called Affinic Mach number and mass to flux ratio. And the last purpose is to test to understand the dust grain evolution in this environment. So the question here is, can polarization data provide constraints on the grain growth, which is through the maximum grain size in different environments. So the observational methods, which is already mentioned by Professor Thiam and Dr. Chung, it's for us in our case is illustrated in by the pink arrows here, which is the polarized emission, thermal dust emission from the aligned dust grains. And so we just need to measure the polarization fraction and then polarization orientation, and then we rotate by 90 degrees to have the orientation of the magnetic fields. And then here for this kind of observations, the polarization fraction and the polarization angles are the key observables. So in this, so far we have 5 objects in our hands and being analyzed. And with JCMT, we have G44 and IC5146 and Serpent's main. And JCMT is working at 2 wavelengths, but in this case, we are working on at 850 micron, and which is the emission which traces the colder, denser dust. And for this, it's good to study the coarse and dense filament spines. And for Sophia Hawk Plus, we've been working on 214 microns, and which traces the worm dust sensitive to the intermediate mass, intermediate density regions and outflows. For the case of G11 and Orion molecular cloud 1. And for Planck, with the low spatial resolution, it's useful for all sky survey, and which traces larger scales, diffuse ISM and entire filament structures. Usually the filament is long, so it takes time to survey all the filaments, and it's good for Planck to make a survey. So here are our targets. Yeah, they are. It is a diverse set of targets. For G11 or normally called snake filaments, early stage massive filaments. So, and Musca is a recent nearby isothermal filament. So the first 2 papers are led by Ngọc, who is here, and then we a third object is also included in the second paper, which is the active high mass star forming region with strong feedback, OMC1, and G34 is an infrared dark cloud with embedded source, embedded cause IC5146, which is a filamental cloud without bright embedded sources. And Serpent Mains is a active cluster forming cloud. So we want to have a diversity to allow us to test theories under various physical conditions. Here are the images of these filamentary molecular clouds. So how we can reach our goal? We use the analytical methods. The first one is just look at the maps. We look at the maps of the intensity, polarization fraction, polarization angle, and get the information directly from these maps. And usually for the polarization fraction, we do the debiasing, namely we subtract the noise component of the polarization fractions. And then we look at the correlations of the polarization as function of intensity, column density, and dust temperature. Then we try to use dust physics to explain these correlations. The second one to be considered is the magnetic field tangling. The information can be get from polarization angle dispersion. We have the polarization angles, and then we can calculate the polarization dispersion, and it is denoted as S and or sigma theta. This parameter quantifies the local BQ disorder. The larger this parameter, the more tangled the field is. So the polarization percentage versus S will tell us whether the depolarization is due to field tangling or not. If we have the P versus S is a constant, then we can say that P does not depend on the field tangling. And then we also have the product of the polarization percentage multiplied by the polarization angle dispersion. And this is the average grain alignment efficiency, because if this value is high, it means the alignment efficiency is high along the life sites. Then we have the predictions from the RAD theory. We have the alignment size, which is mentioned by Chum. This is the smallest size of dust particles, which can be aligned by radiated torque. And then we have the disruption size, which is a minimum size of grains that can be disrupted by the radiation. And the last one is magnetic relaxation strength, which is the parameter which quantifies the efficiency of magnetic relaxation versus the gas damping. And the last parameter depends on the magnetic field strength. And then, as mentioned by Alex, we also use the DCF, Davis-Chandrasekhar Fermi method to calculate the magnetic field strength, usually in the plane of the sky, because as function of it is inferred from the gas density, velocity dispersion, and the angle dispersion. So I'm show you some first results regarding the morphology of the magnetic fields. So across multiple filaments, B fields tend to be perpendicular to the dense spine of the filaments. That's the general trend. And there are also some evidences for B fields parallel to the striations fitting into the filaments. And this is a very nice case where we see that the denser we are going to, the direction between the magnetic fields and the filament spine is increasing to closer to the 90 degree, which means perpendicular to the filament spine. So regarding the strengths, and in dense parts of filaments, the strength of magnetic fields is going from 100 to several 100 microgauss in the case of G11 and up to 1 milligauss in the case of Seppens main. And filaments are often found to be subcritical. Namely, the mass to flux ratio is smaller than 1, and subaphanic means the MA is smaller than 1. Which indicates that B fields are dynamically important in these molecular clouds, and they can resist the gravitational collapse or dominate over the turbulence. In particular, in the case of G1 or Seppens main. Here I show the two maps of the B field strength and aphanic Mach numbers. Regarding the polarization host, in the case of G34, for example, from the analysis of the product of P multiplied by S, which suggests that the depolarization in this object is the decrease of the net alignment efficiency. And in the case of G11, the depolarization is explained well by RAD A, and which is the loss of alignment in denser and less irradiated regions. Then we can calculate the ALI, which is increased. The values increases towards the denser regions. This is one example of ALI being calculated for G34. And usually we observe the anti-correlation between P versus ALI, which supports the prediction from RAD-A theory. And as mentioned by Chung this morning, we also found evidences for the presence of radiation disruption at high temperature, where the polarization degrees decrease. And we also calculate the magnetic relaxation strength, and usually in these filaments, the values of this parameter is greater than 10. So it means with the inclusion of irons, we can explain the high polarization degree in these super paramagnetic materials. And in the simple case of Musca, we found that to reproduce the data, we need to have the maximum grain size, which is high. So this is greater than the maximum size allowed in the interstellar medium. It means there is evidence for the grain growth in many regions. Okay, so we need to have the dust grain size which is greater than, usually it's the maximum is 0.2 micron. So within this project, we try to provide a consistent framework, and the RAD paradigm provides a very powerful and consistent framework to explain the diverse observations of polarization emission. And with the collection of targets, it's complementary studies, because for example, for the case of Musca, it's the ideal lab for testing RAD-A, and for high intensity emission radiation source, it's a good place to test the RAD-D. And then the outer parts of G11, G34 are good for MRAD. And depolarization is complex. It is the mixture of many processes. And diffuse are found to be dynamically significant in shaping the filament evolution and star formation. Okay, I will skip talking about the future, and maybe I stop here for the summary. Maybe you can read that. Yeah. So our purpose is to systematically investigate the magnetic fields and dust physics in the interstellar filaments, and I show you some first results, and stay tuned for more details talk on specific Balakon studies.
Okay, so thank you, Professor Diop. Very nice talk. Okay, so we have 3 minutes for Q&A. So who wants to ask the first question? Yeah, Chihi.
Thank you for the nice talk. So in case of depolarization is so complex, so is there no way to distinguish which factor is the most important for the depolarization?
Yeah. So that's why we need to work with many targets. for simple case like in the case of Muscat, it's quite linear. So the polarization fraction going from outside to inside the filament spine, you see the decrease, and then it can be reproduced basically using the Rabe prediction. And then, especially in the case of OMC, it's much more complex, and then we need to include a lot of things to explain the observations. And for example, without Rabe, it cannot be reproduced the observation. That's why we need to work on several objects, and in each object we have some processes present in that object, so we try to distinguish the polarization sources.
Yeah, I think I would like to add one thing. So there's only one phenomenon, which is polarization hole. But this phenomenon happens for different objects, different environments. So it would be quite surprising if a single mechanism can reproduce such a polarization hole in different environments. So the fact that here we found for different environments, different mechanism is dominant in reproducing the polarization hole. So it's in some sense it is quite reasonable. Because in the star forming region like OMC, we expect that the magnetic field tangling is very important. And then the magnetic field tangling, of course, is important in depolarizing the signal we observe. And that we can only explain the depolarization by including the B-field tangling. But the B-field tangling is not enough. We need also disruption. So
in case of magnetic tangling,
yeah.
So it is caused by the observational things. So beam size or there are.
Oh yeah, the beam,
emission
the beam size. Yeah, so the effect of beam size averaging is also important. But here, I think the B-field tangling we consider here is due to the spatial fluctuation. Yeah. Okay. Any other question? Okay, so we run out of time. So thank you again, Dr. Yap. Okay, so we now have a two online presentation. So the first one will be given by Dr. Sadhana Singh. So Sadhana, can you hear me? Okay, good. So you have 30 minutes, but you can only be able to speak for 25 minutes. So leaving 5 minutes for Q&A. Can you unmute? No, sir.
Okay.
Okay, good. Go ahead.
Okay. So, first of all, good afternoon to everyone. I am Sadhana Singh from India. So, I am presenting an investigation of magnetic field and grain alignments by choosing an open star cluster, by choosing open star clusters and a study towards the Serpens main molecular cloud. So the content is divided into two projects. So first project is to study the Serpens main molecular cloud through GCMT polarization data. And in second project, I will discuss about the optical polarimetric study of open star clusters. So as we know that the interstellar medium is the medium between the stars within a galaxy, and it is the raw material from which stars form and into which stars eject material when they die. So there are different structures within the interstellar medium, and one of those is molecular clouds, which is the birthplaces of stars. And as revealed by Herschel's observations, molecular cloud consists of filamentary structures, and star-forming cores are embedded within the filamentary structures. And interstellar dust grains are the solid-state component of interstellar medium, and their presence is detected via the interaction with the starlight. For example, some phenomena like extinction, reflection, polarization, and emission from the dust grains, and they are clumped of many submicron meter size grains, and they can have different sizes, abundances, depending upon the where they are present, in which environment they are present. So the first information about interstellar polarization was discovered by Hilton and Hall in 1949. So in their data sets, they have found three findings. That first one, that the correlation between polarization and interstellar reddening, and the variation of polarization and extension with wavelength was different. And then another was that the polarization vectors of many stars have shown approximate parallelism. So that means through these findings, it was concluded that it is not the individual star that is creating the polarization, while the medium between the observer and the star, that is responsible for the polarization, and that is termed as interstellar polarization. So in the medium there are gas and dust. So how we can get the polarized light when a radiation is traveling through the medium? So for that, there means individual dust particles should be optically anisotropic, and there should be a net alignment of axis of anisotropy. So if for example, if we see the alignment here, so this is means when the grain rotates about its principal axis, so that is called the internal alignment. And when all the grains have a common axis of rotation, then that is called the external alignment. So there are different theories for the grain alignment, out of which radiative alignment torque theory is the best matched and the most accepted theory, because it explains most of the observational findings till now, as you can see from this table. And it so grain alignment happens because of the interaction of when anisotropic radiation of wavelength less than the diameter of the grains interacts with the irregular grains, and then the grain alignment happens through the RAT theory. So overall, the picture which I write for the interstellar medium polarization is like this. Grains are aligned with respect to the magnetic field. Here in RAT, means in all the mostly all the mechanism, it is that grains are aligned with their short axis parallel to the magnetic field. However, through this RAT grain alignment theory, the grain alignment is also a function of the angle between radiation direction and magnetic field direction. So when there is a 90-degree the angle between the radiation and magnetic field, then there can be a wrong alignment also. By wrong alignment, I mean when the short axis of grains is perpendicular to the magnetic field. So in general, the alignment is with respect to the magnetic field, means short axis is parallel to the magnetic field. So when the unpolarized light comes through and interacts with the aligned dust grains, then they faces the electric field vector that is perpendicular and parallel to the short axis, faces different extension cross-sectional area, and hence a different extension efficiency. And finally, here we get the polarized light. So for this, it's in the case of optical or the absorption case. So here we can get the B field orientation directly from the polarization angle. While in case of emissions, dust particles emit along their long axis. So here, in order to get the B field, we have to rotate the polarization angle by 90 degree for in the case of emission or the longer wavelength. So the information which we can extract from polarimetric observations are the properties of ISM dust grains, their shape, sizes, and compositions, the geometry of magnetic field, grain alignment, and the polarizing efficiency. And the foreground dust concentration or the interstellar environment. So these all are the information which we can extract through the polarimetric observations or the ISM polarization. So coming to the first project, so probing magnetic field and grain alignment in serpentine maze through JCMT polarization data. So this is a project under this Ballet Pole project. So serpentine maze is an active star forming region. So mainly gas and dust are concentrated in these two parts, the northwest and southeast subcluster part of this cloud. And according to the study by Lee et al., they identified 6 filaments in the serpentine maze. They have shown in this intensity map of Stokes eye. So we have used the 850 micron polarization data of JCMT telescope for this. Coming to the magnetic field analysis. So here I have shown the magnetic field morphology. So for showing the morphology, I kept the segment length the same for all the polarization vectors. So here we can see that mostly the orientation is towards this east-west direction, while in this higher denser region, the orientation is changing. Also, according to the detailed study by Cohen et al., it was found that the orientation of magnetic field changes from being parallel to perpendicular to the filament while going from less denser towards the denser region of filaments. So for estimating magnetic plane of sky component of magnetic field strength, we have used classical DSF method and the modified DSF method. So classical DSF method is based on the assumptions that magnetic field are being distorted due to propagation of incompressible transverse magnetohydrodynamics waves or the Alfvén waves, and this distortion causes the spread on the spread in the polarization angle. So this is the final equation that I have used, and however in later studies it was found that classical DSF method overestimates the field strength, especially towards the low towards the low MS or the Mannix number. So then we have used the modified DSF method, that is Tassis ST method. So they have considered both modes, incompressible as well as compressible modes, and then this is the final equation that I have used for this method. So here the NH2 is the volume density, which is in per centimeter cube. Delta V is the FWHM of non-thermal velocity component in kilometer per second, and sigma theta is the angle dispersion in degree. So for to derive the field strength through these methods, we need the map of volume density, angle dispersion, and non-thermal velocity dispersion. So for this volume density, we have used the column density map from these papers, and then by using this dividing by the depth, we have calculated the volume density. And for the angle dispersion, we have used the unsharp masking method described in Pallet 2017 paper. So for this, we considered pixel, and then around that pixel, we considered the 2 beam size box, and then we calculated the mean angle within that box and assign it to the central pixel, and then within that box we calculated the RMS of angle dispersion and assigned it to that pixel. So similarly, then we again moved the box and calculated it for the whole region. So using this, we derived the map of sigma theta or the angle dispersion. For velocity dispersion, we used 13 CO data from Bergalia et al. 2013, and we fitted the Gaussian curve to the velocity spectrum and calculated the FWHM of thermal component, FWHM of the total velocity component, and then we subtracted the thermal component, and then we got the FWHM of non-thermal velocity component. So now these maps were taken from different, this one is from our study, while these are taken from other papers. raw data taken from other papers. So these are different resolutions or different pixel size. So in order to use these maps to this equation, first we have to smooth these maps to a single resolution. So after doing that, we have used these maps in that equation and then derived the modified DSF, um, uh, derived the magnetic field through modified DSF and classical DSF method. So we have seen that relatively higher value of magnetic field are coming when we use classical DSF method. And also there is a broad distribution in the classical DSF method. So and also we noticed that the difference in both the methods is getting higher towards the low value of sigma theta, and low value of sigma theta is indirectly correlated with the turbulence or the Alfvén-Mach number. So then, as we know that towards this low sonic Mach number, this ST method works well, and also this is the recent method that was considering all the drawbacks from the earlier method. So we used this method for further estimation. So using estimated magnetic field, we derive the mass to flux ratio, that is the relative importance of gravity with respect to the magnetic field. So here in the cloud, we have seen the region is mostly subcritical, means the magnetic field is enough strong to hold the regions of the cloud against the gravitational collapse. While there are some regions in which the lambda is greater than 1, that is the supercritical region in which the gravitational collapse will be happening, or this is much higher than this magnetic pressure. And for the Alfvén-Mach number, we have also derived the Alfvén-Mach number to see the importance of turbulence with respect to the magnetic field. So we have seen that the value of Alfvén-Mach number is less than 1 for mostly whole the region, that shows that the turbulence is not dominated in this case. Coming to the dust physics part, so here as discussed in earlier talks, Dr. Deep talk, that we means in each region we are getting the for the polarization rule, that is here we have fitted the non-biased polarization with the intensity with Rice and Mean model, and we derived alpha at 0.68. We show that the grain alignment efficiency is grain alignment is reducing towards the higher density region. And here we can see how the polarization varies with the column density of the cloud. Here it is shown for different regions of the cloud. So in each region we can see a decrease in polarization as we go towards the higher column density region. So this is this result is well supported by the RAT theory of grain alignment, because towards the higher denser region, the aligning radiation becomes weaker, and that's why the grain alignment is less in that towards the higher density region, and that is reflected in the polarization behavior. Another prediction of RAT theory is the increase of polarization with the dust temperature. So here we can see the clear increase for some filaments, while for some other filaments the data is very much scattered. So this is the running mean. Running mean is plotted here, but here we notice that after temperature, after grain temperature 17 Kelvin, there is a decrease in polarization. And this is for this northwest region of lower part. So here we have seen that this result is related to this part of this region, so in which there is a higher temperature within that region. So we have checked and we found that there is a presence of a protostar Serpens SMM1 in that particular region, which causes an increase in the grain temperature in the highest denser region. And so to check what means why we are getting the decrease in polarization with the dust temperature, so there can be two reasons: the effect of magnetic field tangling or the rotational disruption. So for the seeing the effect of magnetic field tangling, so we have used the polarization angle dispersion formula, polarization angle dispersion function, which basically so that how polarization angles are correlated spatially. So we used this formula and then we derived the S polarization angle dispersion. Here we have plotted how is there any change between polarization with respect to this angle dispersion function. But here we found that we didn't find any change in polarization with polarization angle dispersion function. And also P crosses we saw the averaged grain alignment efficiency. So so that is also the behavior of P crosses with TD is very similar to the behavior of P with TD. So that the magnetic field tangling is not effective in this particular case. So it is means for this decrease in polarization with temperature, the magnetic field tangling is not effective. So the another is RAT. So this was discussed in earlier talks that grains towards means nearby the protostar where the radiation field is much stronger, so the grains can be disrupted into smaller grains. So there is a limit on the size distribution of grains. For example, now Emax has reduced to a disruption, so there is a narrower size distribution, and that causes the decrease in polarization with after this temperature. So that's maybe the reason for the decrease in decrease in polarization after this temperature. Now we have also derived the value of alignment sizes, the minimum size of grains that are aligned using the formula from Hong et al. 2021. So here we have seen that the alignment sizes increases with the increase in air total intensity, or if we go towards the higher denser region, the alignment sizes increases. So that is well explained with the RAT that towards the higher density region, so the radiation strength is becoming weaker. So because of that, now the alignment, the grains which are aligned, only the larger grains gets aligned with that particular radiation strength. So that and of course with the increase in the alignment sizes, polarization decrease because of the now narrower size distributions of aligned grains. So we also test the MRT mechanism, that is the combined effect of magnetic relaxation plus RAT mechanism. So which can be seen with this delta parameter. So we have calculated using this equation delta by considering 3% iron abundance in clusters. So we have found that delta is greater than 10 in all the regions. For whole Serpens cloud, it is Serpens main cloud, delta is greater than 10. So we saw that there is a very efficient magnetic relaxation, and hence the MRAT plays role. And so with the increase in delta, as expected, the polarization also increases. So, so these are some of the results from the project one. So these are the conclusions which I already discussed in that talk. So coming to the second part of the project, so optical polarimetric study of open star clusters. So these are the some of the information which we can get through the optical polarization study. So I have chosen open star cluster because they are spread within an area. So so we can see the change in the polarization parameters within all the within that area. So here I am showing some results from these 4 open star clusters which are towards the galactic anti-center direction. So I observed these clusters using 1 meter ARIES telescope, which has a polarimeter unit of M-pole, the ARIES imaging polarimeter, which consists of a half-wave plate and a Wollaston prism. So it is a dual beam polarimeter. So here this is the magnetic field orientation for these regions. So we have seen that this mostly the orientation is along with this galactic magnetic field. So this dotted line shows in each plot is shows the direction of galactic magnetic field in that particular region. So we have seen that mostly the orientation is parallel to the galactic magnetic field, while for one cluster we have seen that all the vectors are tilted from the galactic magnetic field direction. We saw that there has been a perturbation, and now there has been a recent perturbation, but the Dustians have not found enough time to relax and further orient the further orient the dust grains along the galactic magnetic field direction. And this is the RGB image of 7380, where this R corresponds to Y22 micron, which comes basically from the heated tiny grains, and G is from the Y12 micron data, which is mostly due to the PAH emissions, and B is corresponding to red. So here in that region, so this is basically this cluster is located in an H2 region, and this star, which is a type, which is DH7. So this star is considered to trigger the star formation in this cloud. So also we expect that polarization should increase with the distance because of the increase in the columnar dust grains, but the dust grains are generally not uniformly distributed. They are distributed in layers. So to infer the layers and the distance of the layer, we have here we have shown how the polarization varies with the distance. Also, to inform the information about dust grains, we can also get from the extension also. So, and these data I have taken from this from the recent Gaia data. So here we can see there is an increase in the polarization at 1.2 kpc distance, and increase in polarization is also correlated with the increase in extension at the same distance, so which shows that there may be a presence of dust layer in foreground to these clusters. So for these two clusters, we have found the indication of dust layer, but for cluster LEC1 and NGC1817, we didn't found any major dust layer foreground to the cluster. The information about interstellar and intrinsic polarization we can get by using the Sierkowski empirical relation. So I have observed these clusters in different bands, in 4 bands B, V, R, and I. Then I fitted each star with this Sierkowski empirical relation, where P max is maximum polarization and lambda max is the wavelength corresponding to which we are getting maximum polarization, and it is a function of characteristic particle size distribution of dust grains. So here I fitted this relation, and then I differentiated between interstellar and intrinsic polarization based on 3 parameters: sigma 1, epsilon bar, and lambda max. Sigma 1 is the unit weight error of fits. For example, if the fitting is not good and there is high chi-square value, then we can say that this is not interstellar originated. And for epsilon bar, we have checked that whether the polarization angle is nearly same in all the bands or not. So based on this, we calculated the polarization angle dispersion. And lambda max, so lambda max value generally lies from 0.4 to 0.8 microns. So if the lower value of lambda max also indicated the presence of intrinsic polarization. So this is the distribution. Yes.
Can you wrap up in 1 minute?
Oh, okay, yeah. So this is the distribution of lambda max in the galactic plane. That is this is L, galactic longitude and latitude. So mostly for the general diffused ISM, the value of lambda max lies around 0.55 micron. So also the information about the interstellar environment we can get from the Stokes plane analysis, and we know that the star clusters are forming from the same molecular cloud, hence share some of the properties. So for example, the member stars of the clusters lie at nearly same distance, so the polarization for those member stars would be similar. So based on this principle, we have differentiated between members and non-members, and also we used this information to derive the membership probability of a star. So here this plot shows the membership probability for NGC 2345 stars, which is in well agreement with the proper notion membership technique. So this is the average polarizing efficiency. So the polarizing efficiency is found to be similar to the average efficiency, and here we have seen that with the increasing polarizing efficiency, lambda max decreases, which is well in agreement with this with the arity theory. And this shows the distribution of polarization and polarization vectors in galactic anti-center direction. I took the cluster data from all the clusters which have been observed in this particular direction, and I took other data from the Helios catalog. And these are the number of dust layers that are present in front of the clusters at the distances. So we noticed that the clusters which are located in galactic plane, only those clusters have shown the indication of the dust layer. And the other clusters which are located below and above, they haven't shown any indication for the dust layer. So this is the summary of this project. So with this, I would like to stop here. So
Wonderful.
thank you. Yeah, thank you for
Thank
the
you, Ms.
opportunity.
Okay, so we can have a couple questions.
Yeah.
So, yeah.
Thanks for a nice talk. Can I have a comment? Can you go back to the slide where you compare between the classical DCF and Stylidis?
Yeah. Yes.
The two figures in the left corner, to me, they don't bring any new information. Because it's is just mathematical sequence of the same parameters with two different functions. So if you plot any values, then you can get that. Doesn't bring anything. If you go back to the previous slide, you see that.
Yeah, so only the difference
They are just
related to sigma theta.
Same parameters, and then you plot for any it will be different. The difference.
Yeah.
So,
Yeah.
do you agree with that?
Yeah, actually, because in these equations, only the difference is with respect to the sigma theta, and also it was means for the ST method, it was means said that the DSF method is basically overestimate towards the low sonic Mach number. So that's why I plotted the differences as a function of sigma theta. So sigma theta means indirectly related with this with the alpha and Mach number. So means to see that whether towards this low value of Mach number we get the highest difference or not. So this is the similar things behind the assumptions of HT method over the DCF method.
Thank you. So any question?
So, Sahana, Cham here. So I have the very interested in your starlight polarization. So I have two questions maybe related. How can you remove the foreground star along a line of sight? Same question like how can you determine the dust layer? Do you use Gaia or something?
Okay, so first question. So your first question is, did I remove the foreground stars for the intrinsic polarized star? Okay, so means I differentiated based on this, and then I I gave the value of average value of polarization, P max and lambda max only after removing the intrinsically polarized star. However, I haven't removed the foreground dust concentration from all the stars. And regarding the second, I used the data. Yes, I cross-checked with the all the observed stars with the Gaia data, and I took the distance from the Gaia data as well as the extension also from the Enders paper. So based on that, I plotted this PV and distance, and then I get the information of foreground dust concentration.
Okay, so you use Gaia.
Yes, I used Gaia.
Thank you.
For the distance. Yeah. Thank you.
Yes, again.
Thank you so much.
Yes, I'll stop sharing.
Yes, yes, I'm.
Okay, so let's welcome our next speaker, Professor Archana Som. So she will be talking about observational studies of magnetic fields and dust properties into dust polarization towards star-forming region. So Archana, can you show in the presentation mode? So you will be speaking for 25 minutes and leaving 5 minutes for question and answer. Yeah. So please.
No. Please unmute me. Hello. Can you hear me now?
Yeah, we can.
Oh, perfect. Because I was not able to unmute myself. Okay, now it's fine. Okay. Can you see my screen well?
Yeah, but it's not in the presentation mode. So we'll show.
I will do it.
Okay, good.
How about now?
Wonderful.
All right. Okay. I'll try to be on time because it's a 25 plus 5 minutes talk. So I want to remove this thing. Okay. Anyways, so yeah. So this talk is not about a particular result or particular region, polarimetry in one region or so. This talk I'm giving here is about kind of what we did in last few years or last many years in understanding magnetic fields in the ISM using dust polarimetry in different wavelengths. So, and thanks for inviting me for this talk because I enjoyed it last year also, and thank you for inviting me again this year. In the talk, I have divided my content into 3 portions. One is about getting magnetic fields in dust using dust polarimetry in different regions, and those regions are molecular clouds, cores, PDRs, the photo dissociation regions, which are embedded in H2 regions, filaments. The second part will be magnetic fields these days probed with a new tool called VGT. I used to not keep this thing in my talk earlier, but recently we have published a paper on getting magnetic fields using VGT in one of the star forming region, NGC 1333. That's why I kept this portion here and I wanted to show those results. And the third portion will be about grain alignment using dust polarimeter. This is all about what we can do with the dust polarimetry and observations, spectroscopic observations. We all know by far that locations of star formation are molecular clouds, and those clouds are enriched with molecular gas. These are cold, dense regions which have capability of making cores, and cores get gravitationally collapsed, gravitationally unstable, and then star formation happens. So the regions which have all these capabilities are the locations where stars form. But why I'm interested in these regions, because I want to understand the roles of magnetic fields in these regions. So this slide, I think you guys have seen so many times, but I always love to show it here because we know that 75% of the star forming cores are embedded in the filament. So star formation actually happens in the cores, and which are mostly 70 to 75% time found embedded in the filamentary regions. And this is very nice example of torus B211 and 213. The left one is the Herschel 250 micron emission image of torus, and the right one is the zoomed in image of the protostellar cores embedded in a filamentary structure, and the image is taken with 1.2 millimeter wavelength using NICA. So talking about magnetic fields, because this is going to be a short talk, so I should start first. I should soon start about the magnetic field's importance. So this plot here shows the effects of turbulence and magnetic fields in the star formation. So this is also a very famous plot. Like people try to use it for understanding what happens if there is only gravity, as you can see in the red dash dot line. If there is gravity and turbulence, the green dashed line. If there is gravity, turbulence plus magnetic field, the blue dotted line. And if there is effect from the feedback also from jets, so that is black solid line. You can see that the star formation rate, which supposed to be high if you just include gravity, it goes down when you start including more factors like turbulence, magnetic field, feedback, and all. So the most of the star formation rate observationally is found in this shaded region. That is from in this shaded region you can see. And so in this region you can see the effect of the magnetic fields and the turbulence. So details, I'm not going into the details of this plot, but I'm showing that the magnetic fields, turbulence, feedback, and other factors, they have effect on the star formation. So star formation rate is not ideally what we thought of with gravity only. So when we talk about star formation rate, we should also talk about the virial balance in the cores, and that we can get from the virial parameter alpha. So earlier alpha, there were results where alpha was found to be greater than 2, but recently many results are there now which shows alpha is less than 2. Alpha is nothing but the ratio of mass to mass of the core to the virial mass. And if we can calculate the virial mass using non-thermal velocity dispersion and the sound velocity, and the virial mass with the effect of magnetic field can be calculated if I include this third term, Alfvénic velocity here, and the sound speed can be calculated from the temperature of the core, and Alfvénic velocity can be calculated from the magnetic field strength. And if you incorporate all these things and calculate alpha, alpha is found to be less than 2 in many regions. So actually, this means that the constraints on the star formation physics based on the assumption of alpha is greater than 2 should be reconsidered or should be reshaped or should be rethink about. So there are many results now which shows alpha is less than 2. So magnetic fields, many talks are going to be here and many people have already talked about it, how we interpret magnetic fields. In very brief, I'm showing these two pictures here. Magnetic fields can be interpreted. I'm talking about plane of the sky magnetic field here only, using polarized thermal dust emission and using starlight polarization. So these are very famous pictures of the above one is Planck dust polarization and the below one is the starlight polarization in the galaxy. So these are two famous methods which we have been using to interpret the plane of the sky magnetic fields in the ISM. And the method, I think Sadhana also and many people have also showed it earlier and will show that how we interpret magnetic field. Yes, we understand magnetic field because we are able to interpret it with the help of aligned dust grains, which are aligned with the help of interstellar magnetic fields. The grains are aligned in such a way that their minor axes are perpendicular to the magnetic field. And the theory behind this is, so far, the most successful theory behind it is the radiative torque alignment. And this whole story of now after that, if we have magnetic field orientations, we are able to estimate the magnetic field strengths also using the equipartition between non-thermal motions and the magnetic fields. And if we know the deviations in the position angles because of the turbulence and because of the small scale non-thermal turbulence, then we can also calculate the plane of the sky magnetic field strength. So this is just a simple picture how we interpret plane of the sky magnetic field orientation and how we calculate the strength. So using these information, whatever was available in theory and the dust polarimetric observations in different wavelengths also from different telescopes, we did a lot of studies for mapping magnetic fields in different regions, and those regions include filaments, cores, and H2 regions. So these are just some pictures from the studies which we published. The left one is the G34 infrared dark cloud, where we mapped magnetic fields using 850 micron dust polarization observations using from JCMT. And the famous core what we published in 2019 was LDN 1521F, which is a VELO core, the core with a very low luminosity source. And we were the first, we could go to the sub-parsec scales, from parsec scales to map the magnetic fields from JCMT 850 micron polarization observations. And the third rightmost panel shows the magnetic field orientations in the H2 regions. Actually, these are important studies because we were the first to publish and to say in many of our studies that the magnetized evolution of H2 regions is different from the non-magnetized evolution of the H2 region. So there were only a couple of simulations available where magnetic fields were not incorporated in the evolution of H2 regions, but some of the simulations like from McKay et al. 2011 and Hannay et al. 2009, they were predicting that if magnetic field information is there or if magnetic fields are incorporated in the evolution of H2 regions, then the picture is completely different. So sometimes these clouds are shaped by the magnetic fields and sometimes the magnetic fields are shaped by the cloud evolution. So these were the studies, like I'm just categorizing here that these were the attempts we made in understanding magnetic fields using dust polarimetry. So I'll just highlight a couple of results here. First, clouds to cores. So this was the first time we were zooming in the magnetic fields from the parsec scales taken from the Planck and optical, which you can see in the upper left and upper right, Planck and optical, and then we zoomed in the magnetic fields inside this core using JCMT Pole 2 at the subparsec scale. We actually proposed this for the ALMA observations also, but the core kind of was so faint that the emission got resolved out and we were not able to get any polarization signal. So this was the best we could do in zooming in the magnetic fields in this very low mass core. And we found that the magnetic fields are kind of intact at parsec scale, but when we go to the subparsec scale, there is a kind of intact on the parsec scale, but if we go to the subparsec scale, there is a kind of bend in the magnetic fields. And these double-headed arrows shows the direction of outflows from the very low luminosity source. So there is one thing to notice here. I'm telling you, velos have outflows. They are like class 0 sources, but their outflows are so low energetic that they are not able to disturb or do anything to the surroundings. So whatever magnetic fields we are seeing from the parsec scale to subparsec scales are the inherited parental magnetic fields. There is no any change from the turbulence caused by or feedback caused by the outflows. So similarly, another attempt we did in the similar core L328, which is a core with velo, again the very low mass core, and my student Shivani Gupta, she did the similar study. She found the magnetic field orientations from parsec scales using Planck and optical, and then we zoomed into using near infrared, and then finally we got JCMT submillimeter polarimetry data, and we got the core scale magnetic field. Nicely, we can see that the magnetic field in the core are kind of wrapping around the shoulder of this core, and because the sample is not very good, so we can't say much, but we could do a lot of analysis on this core, and I think Shivani can show in her talk. So these were the attempts, these were the cores which were attempted to get magnetic fields from subparsec to subparsec scale. And this is a table taken from Shivani's work, and where we know the mass to flux ratios were estimated, calculated, and the cores were identified as either magnetically subcritical or supercritical. So using polarimetry in the cores, we could classify them to subcritical, supercritical, or at what stage possibly that core will be. But it was not an easy task, because getting polarimetry data at different scales from different in different wavelengths from different facilities is a huge task. So I am just highlighting the results of our H2 regions, where we saw the interesting magnetic field morphologies and the modifications in the cloud shape itself. So this was the IC1396 region, and there were 4 BRCs or 4 clouds sitting on the periphery of the H2 region. We selected them and we did optical polarimetry. And in this cartoon, in this figure, I show that the center star HD206267, which is a O-type star, is responsible for the formation and the expansion of this H2 region. So this radiation effect coming from the H2 from this O star should have some effect on the magnetic field morphologies, but it is not necessary. It is not always necessary. So we have to do some kind of radiation and radiation pressure budget and overall pressure budget and the energy budget. But I'm just showing the shapes here. So this is okay. This was the one. So I'm not showing all the 4 results here, but I will show some interesting results on the very nearby, like the nearest H2 region, H2 region, which has 2 BRCs, IC59 and IC63, where we did optical polarization and the infrared also. Magnetic field morphologies we found, and in IC63, in the lower left one, we can see that the magnetic fields are mostly along the direction of the radiation. But in IC59, it is clear that there is a kind of curvature on the side which is facing the high energy radiation. So does it mean that the radiation is pushing the material away, and the magnetic fields which are frozen in the material are going along with the magnetic field line? So all the details, all this discussion we have given in our published paper. Similarly, recently my student Siddharth Kumar did the magnetic field morphology on the 3 cometry globules, L328, 331, and 323 in optical and Planck. And the interesting thing about this region is that they are affected by the by number of O and B types number of B stars in the left-hand side. So it looks like all the clouds are looking towards the ionizing source. Another example I took from the literature is M16, very well known, 30 Doradus from Tram's work, and this Rosette Nebula. So this M16 shows very nice distribution of magnetic fields along the pillars and these fingers, and 30 Doradus shows a very nice convex and convexy shape, which is like magnetic fields are kind of modified in both the sides of the ionizing source. And this rosette shows a very nice distribution of magnetic fields, kind of following the spherical shape of the cloud. Third thing is filament. So let's see what happens in the filaments. I will not show many examples because I don't have much time, but I'll show some famous ones. So this is the case of NGC 63331, where magnetic fields were mapped using JCMT Pole 2 observation. So the data was really good. We had very high sample measurements, and we found that the magnetic fields are very well ordered if you see on the larger scale. But if you go to the smaller scale and see the magnetic fields in different clumps, you definitely see a change in the magnetic field orientations. And all these panels show that the change in the magnetic field orientation is clear. So from large to small scale, the magnetic fields are changing orientation. Large scale means where the filament is forming. But small scale is where the cores are forming and where exactly the stars are forming. So there are many examples now published actually, but I'm showing this one because this is the one where we started this. And the one we published in 2019 was a famous infrared dark cloud G3443. The leftmost panel here shows the Planck image, where we see the magnetic field from northeast to southwest. And then we zoomed in using the JCMT 850 micron polarization observations at 14 arcs again. We find that the three regions, which were north, center, and south in the filament, have kind of little different morphologies. But we were more interested in central region because the sample was high, and this was the region which has highest density and the most active star formation ongoing there. And we found that the magnetic fields are quite ordered here. But if you zoom in, the magnetic fields in these two clumpy regions in the rightmost panels, which are taken from Chet Hull's work using Karma 1.3 millimeter, which are shown in the green line segments, and the 870 micron SMA observations shown as the white line segments, and the red ones are the JCMT. So you definitely see a change in the magnetic field morphology at 1.3 millimeter and SMA. So there is a deviation in magnetic fields when we go from 14 arcsecond resolution to 2.5 arcsecond resolution to 1.5 arcsecond resolution. So definitely a change in magnetic field morphologies as we saw in NGC 16334. And this is also another example of bones in the sky, So this was the first very beautiful result published by Ian Steven. Luckily, I was also part of this study. So these are the long bones where they measured magnetic field properties using SOFIA observations at far infrared, and where they found that the magnetic fields are mostly perpendicular to the higher density regions, which is not surprise because it has been seen in many examples, especially in Planck observations. But it also has been, but in this study we found that most of the time the lambda lies below 1, which suggests that the mass to flux ratio is most of the time low. This means the magnetic fields are supporting against the collapse in the regions which are high density, where core and star formation is ongoing. So this was one good example of this bones in the sky project. There are many others now which will be published soon. So overview of these images which I just showed. I think I will run out of time. So I think I should better go to the next part of my talk. VGT, yes, we all know about VGT now. So can molecular line intensity be used for, or spectroscopy be used for the magnetic field interpretation? Answer is yes. We have a very nice tool, VGT, these days, and the tool is a new method for estimation of high resolution spectral estimation of magnetic field properties, which are orientations as well as strength using high resolution spectral line observations. based on two facts. We should always keep that in mind. Those two facts are ISM is magnetized and turbulent, and MHD turbulence tends to create anisotropic arrays. And there are a number of papers and number of studies already available on VGT, the main theory behind it, and lots of examples. So I'm just citing some of them here, but there are many, many more. So we dared actually to use this technique in NGC 1333 because we had lots of nice data from Karma, the line data, and also SOFIA data from Ian's project. So we used SOFIA data, and JCMT data also was published as a part of Bistro. So these colors here shows the emissions. The blue one is N2H plus and CO is the red one. And the red and blue lines shows the 214 micron polarization vectors taken from SOFIA and 850 micron W1 from the JCMT. And we divided this region into blob, hinge, and filamentary portions. So I'm just highlighting what we saw. So the green and black vectors here are the observations, and these striations behind, or this the patterns behind are the LIC patterns, which are showing the VGT magnetic fields using different lines. So this was using CO, and these are 3 using 13 CO, C18 on N2H plus. Actually, we are not seeing any correlation between VGT magnetic fields and the observed magnetic field orientation, especially in the denser part. There was some nice correlation in the less density regions, but in the denser parts where blob and filament is there, we were not seeing any correlation. So I think we need more examples such examples to say something conclusive on these studies. Third and the last portion of the talk, ISM dusk grain alignment. Yes, everybody shows this slide that why dusk grains get aligned. Red is the successful theory to answer our question. But what we need for that, asymmetric dusk grains, which should be aligned with the magnetic fields. So can observations help in understanding this alignment, this grain alignment? Answer is yes, but we have to do different type of studies it's not that easy. So first we started understanding how gas-dust collisions, can dust-gas collisions drop polarization, and can that affect the aligned grains? And in our 2021 results, which we published in IC59, IC63, we found that yes, the drop in polarization, which are shown by red and blue dots here, and lines are fitted there, is directly proportional is to the intensity of the gas. So higher the intensity, more will be the chances of the gas dust collision, and more will be the chances of the disalignment of the grains, and hence the drop in the polarization. So this was the example we published first time in one of the regions. Second, polarization hole. Yes, polarization hole is the successful experiment these days people are doing using polarization observations. And when we plot the amount of polarization or polarization efficiency with the extinction as well as intensities, we do find that drop in polarization is found in different wavelengths. So these colors here shows the different wavelength data. All the wavelengths are showing drop in polarization with the intensity or extinction. These are the observation examples we published 1521 FNL328, which are the low mass cores, and they are showing very beautiful drop in polarization with the intensities with a slope of around 0.9 actually. And last but not least, actually, polarization versus other properties in the filaments. So this is a very recent initiative taken by Thiem and his group. So they started this investigation called Ballard poll, and it was already told in one of the talks earlier. So Ballard poll 1 was published by Nogok et al. 2023, G11.11 minus 0.12, and I saw that paper on AstroPage. I was really excited, and I thought that these kind of work should be done. And G11.11 was the one where it was found that the alignment size is kind of showing direct proportional to the intensity, and then the other properties of the cloud were actually, it has already been told in the previous talk, so I'm not going into the details. So this was the first filament under Ballard poll initiative, where the magnetic field observations were used, and different properties like alignment size, the polarization angle dispersion function, intensity, temperature, all these properties were try to understand and try to correlate with each other. Then Ballard poll 2 was showing very beautiful results of OMC1 and Musca cloud. Again by Nagok et al. 2025, they plotted polarization with column density, temperature, and polarization dispersion function. In the same series, I asked my student Pravas to do the similar investigations, and he took up G3443 IRDC, and thanks to Thiem Diep and Nagok for helping him when he visited Vietnam, and he published these results in his 2025 paper where he plotted P with alignment size, polarization dispersion function with alignment size, and other properties. So I'm not going into the detail because there are talks on these regions separately. So overall here, overall idea here in the grain alignment is that dust, grain, and gas collisions affect the polarization efficiency. We have observational evidence for that. Polarization fraction, P decreases with intensity, increasing polarization angle dispersion function, and increasing column density, and it was consistent with the rat alignment theory. So these Ballard poll 1, 2, 3 are the good examples where they are trying to understand whether the drop in polarization is because of the magnetic field tangling or because of the weakening of rat or because of the rat D. So with stronger B field variations and higher temperature models, they can produce the observed polarization in temperature and polarization column density variations, which we see in the observations. So evidence of grain growth is also seen in G11.11 cloud filament. And G34.43 observations support the magnetically enhanced rat alignment mechanism. So these Ballard poll is actually a very nice initiative to understand rat, rat D, MRAT, and also some ongoing discussions on grain alignment theories. So we do need actually more such examples in this initiative, and I think there will be many more. I know I know my student is working on a couple of them, so I think there will be many more examples published soon. And with this, I want to thank you to the Vietnamese team. We started this collaboration a few years back, and happy collaborating. And here I would end my talk and take the questions. Thank you. I hope I did not take much time.
Thank you very much, Ashchana, for being on time. I really appreciate that. Okay.
Thank you.
5 minutes for Q&A. Okay. Okay, so Chi-hee.
I can't hear anything, TM.
Oh, okay. Can you hear me? Can you hear?
Yeah, I can hear you very well.
Oh, but how about Chi-hee?
No, nothing.
Archana, are you hearing me?
Oh God, it's very difficult to hear you. Sorry, but TM is completely audible, but clearly audible.
Oh, hello, Archana.
Perfect now. Yes. Hi.
Thank you for the nice talk. So I have a comment and opinion about the VGT, so velocity gradient technique.
Okay. VGT. Yes.
Yeah, in the case VGT technique, we used the CO or anyway molecular lines. In the case, I think it could be affected by optical depth, especially.
We have taken care of those things in the paper. Yeah, we have given statements there, but we have used CO as well as we have used other 3 lines: 13CO, which is optically thin, C18O, which is optically thin, and 2H plus, which is really optically thin. So we have done comparison using all the 4 tracers.
Yeah, and in case of molecular line data, it could have the multiple components on the.
No, we took the single component. So actually, yeah. So that is, I'm not showing all those results here. That is in the paper, but we have taken so there were 3 components. We have done, we have separated all the 3 components. Different velocity components were there, and we did comparison with different velocity components. So we found the magnetic field orientations for different velocity components, and then compared those with the observations. That is there in the paper.
Yeah. In case of molecular data, anyway, I'm thinking it is trace just the specific density region, critical density. So it could be different with the dust polarization. in case of those two, optical thin and integrated all emission, but in case of the molecular line data, it has traced, in case of NTH plus just traced the high density region like that.
So GA, actually, as I said, that we have polarization observations from SOFIA 214 and 850 micron. So we have observations in little bit warmer region as well as colder region. So it is appropriate to compare the magnetic fields from SOFIA like 214 micron with the CO 13 CO. For N2H plus, we are mostly relying on 850 micron because N2H plus traces the more high density regions where we are getting magnetic fields in high density region using JCMT. So we have taken care of those things in the paper actually.
Okay, thank you.
Yeah, thanks.
Okay, so another question from John.
Okay, hi. Hi, Chana. Can you hear me?
Hi, Ram.
But I didn't see you.
Hey, sorry. Oh, okay, sorry. Yeah, for some time.
So that's the same VGT comment. No, not comment, but your conclusion here. You said no correlation between VGT and observed P field.
We are not getting anything in NGC 1333.
Yeah. So I think this is normal, right? We knew it because
Yeah. We have seen in many other results, but I am showing here NGC 1333, the one where I started trying to use VGT. I did not get any correlation.
Yeah, because in the dense region, probably, I mean, you need to check more, but usually in the dense region, we have the gravity dominant over, so you just...
Definitely, I totally agree with that.
Yeah.
I was very scared to write this paper and very scared to do this because I was the one like, no, it will never match the observations, but it is necessary to do the such samples, like we have to increase the sample to find the conclusions. So you're right, like in high density regions, we are not getting any comparison, like any correlation between two.
Yeah, I mean, but in diffuse, you show beautifully match between VGT and the infer magnetic field from dust polarization. And my next question is that how can you test in those dense region with...
Yeah, I proposed at JCMT at SOFIA. My proposal was, it was in a half filament region. My proposal was accepted, but unfortunately SOFIA was closed.
Okay, the problem from tax. Okay.
Yeah. Definitely, it's not a question for me. It's a question for whole community who are using VGT, that we should actually check it in high density regions. This was the question in my proposal, and that's how I proposed a half filament structure in L1478. Proposal was very nice, and Alex and his some of his students were also part of the proposal. So observations were scheduled, but SOFIA was not. SOFIA was like decommissioned before that. So sorry, we don't have much, but I think what I think is that they are trying their best to include more samples, more such studies. And Thiem also knows, and you also know that we are writing a big proposal for JCMT to increase the sample for such kind of comparison. That is necessary actually. We cannot say anything just based on VGT at the moment.
Okay, yeah, but in this target here about the inclination about 30 degrees, so maybe not feasible to JCMT, right? No.
Which one?
Sorry, it's good for JCMT. So are you trying the next cycle?
No. This one was already observed. JCMT, NGC 1333 JCMT data was there already in Bistro.
Okay.
Yeah. So I use that data, and I use SOFIA data, and I use the Karma data, all these data sets to do this comparison.
Okay.
So what I am saying is that half filament structure, which I proposed for high density regions, was in 1478, LDN 1478, and it was accepted, but what was not observed.
Okay. Maybe probably good luck for the next one.
Thank you. Maybe Prima. Yeah.
Okay, so I have two more questions.
All right.
Yep.
Hi, Achana. Nice to see you.
Thank you.
I would like to hear your comments on general comments on the multi-scale magnetic fields. I think that it's the current situation is rather chaotic. We don't know what we will observe if we go from low resolution to higher resolution. So do you think we can have something which is predictive in the future regarding multi-scale magnetic fields? Chia Wei is here, so he can comment. He's
yeah, definitely, he's expert. So, but what I mean, it was, as I said in my talk also, I'm saying it again, it was not easy to get this data, multi-scale, different wavelengths and on different densities like different telescopes. First of all, it is an intensive process to get the data at different scales. And multi-scale magnetic fields are very important actually to understand the formation of the core itself. Because if magnetic fields play an important role in accretion of the material and forming the core, forming the filament and the core, then that is the first thing we should understand, that multi-scales are most important thing. So from right now we have lots of Planck. Okay. We should, I think, make use of lots of Planck data, which we are doing. Then we should also make use of lots of infrared data. I know optical data is not too much available, but recently I think I should say it. So there's a huge catalog published by GINA in 2024, 2025. They have collected lots of optical infrared and all the studies done in star formation, and they have given a big catalog. So I think those catalogs should be used by the PhD students and take it as a problem that they use that data and they use the Planck data and find the multi-scale magnetic field orientations and strength in at least a number of nearby cores and regions. I know it is not easy to get JCMT time and get data, but there's a lot of JCMT Bistro data available now. So we can take that one. So first thing is that Planck. Second is take GINA's work, which is a huge catalog. And third thing is make use of Bistro, lots of Bistro published results. So at least we have these three scales. I know that ALMA polarization results are not, too many results are not available, but there are many results available in important regions. So take those. So at least we have 4 scales. So the thing is that data is there, but we should make it a systematic study. So some students should come up from the community to take this problem and collect this data and make the orientations and strength and other properties of magnetic fields at different scales. So this is important. I think understanding magnetic field systematically from parsec or to subparsec scales is the most important thing before we just go to any core and just map the magnetic field and just find the field strength. So my point is that multi-scale magnetic field properties are more important than just understanding 1 or 2 important cores.
Agreed.
And data are available now. So I think students can take this opportunity.
Okay, thank you. So the last question, so Zhang.
So thank you for your nice talks. So can you come back to the slide of 35 when you show about the polarization hole?
Oh, just a minute. Slide 35. Yeah, okay.
Yes. So in the right panels, in the right and lower panels,
Yeah.
so that the piece is decreasing with the intensity, but in very near the peak of the intensity, we have the rising trends. So do you have any comment why we have the increasing of the polarization degree with intensity in this area? Is that
Okay, so that's a very nice question. We did not say, we were a little bit scared of saying anything about this actually in the paper, but there was a Nature Astronomy paper published already on this thing, and I can comment on saying that maybe the rat is getting better there because of the radiation coming from the central source. So because red is getting better, little bit better there in the highest intensity region, so alignment is getting better and the polarization is a little bit increasing. This is my explanation for this little enhancement in the polarization.
So
because there is embedded source, there is embedded radiation source in the core.
I see, okay. But
Yeah.
maybe also the potential effect of grain growth, maybe
Yeah,
density.
there can be a grain growth in there. Yeah.
I think, but I think we need more data points, right? Because so far
We need more data points. We need more such examples to say something. But right now, my explanation is getting rat is getting better actually because of the radiation from the source. And as I said, L328, the central source is very low luminosity source. It is not affecting any orientation or anything of the magnetic field. It is not giving much feedback or much energy to the surroundings. So whatever it is giving is radiation, which is just getting used and helping in grain alignment and increasing the polarization. So this is my explanation for this increment.
Okay, yeah, thank you. Okay, so I think it's time now for the coffee break. So thank you everyone for the first section.
Thank you.
Thank you, Archana. Yeah.
Thank you. Bye.
So we will resume our section at 3:30. Okay, so we have about 20 minutes, 15 minutes for coffee break. Yeah. 15, yeah. Okay, everyone, please hurry. We are 5 minutes behind the schedule. Okay, wonderful. Okay, so let's restart our workshop. So I'm very pleased to introduce our next speaker, Dr. Chia Wei Wang. He's a postdoc fellow from East Asia Observatory. So he's going to talk about multi-scale magnetic fields from filament to the clouds to star-forming cores using dust polarization. So we will have 25 minutes for speaking and 5 minutes for Q&A. Okay, so let's welcome our speaker.
Okay, so first I would like to thank for the organizer to invite me to give this talk. And in this talk, I will continue to discuss the multi-scale magnetic field, but I will mainly focus on the combination of the single fish and the interparameter data. And I will mainly report our new AMA ECA plus 12-meter array precision data that we just obtained this year. And that will be shown as the representative case that what we can learn from the single fish plus interparameter precision data. So here I will just show what's the main science equation. So in the past, people think that the magnetic field could be dynamically important in star formation. And in like 20 years ago, people just suggest this classical star formation model, which expect that the magnetic field is strong enough to support the collapse to support the core from gravitational collapse. And so the magnetic field can support the core and to lower down the star formation efficiency. And the magnetic field will be slowly bended by the gravity, by the nuclear diffusion, and become this kind of hourglass morphology. So in the past 20 years, people are trying to find observational evidence to support these classical pictures. And one of the most famous sources is the NGC 33 IRAS-4A. So this shows the sample that we can see a very textbook hourglass shape from the observations. But after 10 years, people find that the hourglass magnetic field morphology is actually not really common. So here shows another very different case. This is the Cerium B8, and this shows that this shows the magnetic field by AMA. And in this map, we can see that it is nothing similar to hourglass, and it's more likely a random morphology. So in the past, people find that the classical picture may not be always correct. So we are trying to seeking more observations using AMA, and this shows the example. We actually find a lot of different magnetic field morphology from AMA observations. For example, here we can see this is one clear spiraling structures that is toward the massive star-forming region taken by the magma survey. And we can, in some cases, we also see this kind of we can still see hourglass magnetic field in some of the cases. And actually, recently we have a magnetic field survey toward the protostars in Orion, and they have observed about around 50 samples in Orion, and from their samples they find they classify the morphology could be either classical hourglass, they can be rotated hourglass, they can be spiral, and they could also be complex shape. So here comes the question: why we have such diverse magnetic field morphology on the core scales? And this is important because we observe so many cases that is not consistent with our standard picture. And we need to know why and how to modify the subformation model. So here shows our very classical picture of subformation. The subformation can start from a very large scale, from the dark cloud, and the dark cloud will start to collapse, and the forms in the condensed region of the cloud it could form protostar cores, and gradually evolve to protostar and the premium sequence star and the stars. So in order to know why we have such diverse magnetic field, we need to know what is we need to go back to a large scale. We need to find out what's the initial condition and what mechanism determines the magnetic field we observe in the small scale. So that's why we really need to know how the magnetic field evolves from large scale to small scale. So from large scale, from observation actually already have a very nice magnetic field measurements over 10 to 10. Have a much magnetic field measurements over 10 or even higher magnetic field, 10 or even higher per second scale. And from the map, they find that we often see this kind of filamentary. We often see this kind of filamentary shape in the molecular clouds. And the Planck shows that the magnetic field is actually perpendicular to this kind of magnetic field when the low density is still low, but it's parallel to the filament when the density is still low, but it will gradually become perpendicular to the filament when density increase. And later we are trying to go further toward the parsec to sub-parsec scale. So people are using the CCNT to measure the magnetic field on parsec and sub-parsec scale. And on this scale, we start to see that there could be a diverse magnetic field. For example, we could also see the spiral magnetic field in MONG-R2 that is published by Zhi Hui, and we also have this kind of semi-hourglass, the pinch magnetic field that looks like a semi-hourglass, and we can also see something like a classical hourglass. But I will notice that this is a morphology at parsec scale, so it is very different from what we said before, because the one I just mentioned for the classical subformation model is within the core scale. So the question is how we connect the morphology we measured at the parsec scale to what we see in the core scale. And the one way is to try to measure magnetic field at multi-scale. So there actually are several studies that are trying to capture the magnetic field at a different scale. So here we show the example that so the next one is the CCNT-PO2 data that measure magnetic field on parsec to sub-parsec scale. And the right part here shows the famous source that show a random magnetic field. So if we want to try to compare these two scales, we can zoom in, and this is the part of this source with the CCNT data. We can see the magnetic field here is somehow slightly random, but not really random. But when we move on to the small scale, we can see that it's nothing similar to the magnetic field measured by PO2. So I think this is the main question. This is also the main challenge for this kind of multi-scale magnetic field studies, because when we are comparing the observation from two instruments, we often have a very big gap between the two scales. So in the past studies, we can, in most of the cases, we can only say the small scale and the large scale are consistent or they are not consistent, but we don't really know what's going on between these two scales. So this is also my comments on what will be the next focus of the multi-scale magnetic field studies, is that I think if we want to really know the comprehensive story of what's going on from large scale to small scale, then what we need is a complete scale coverage without any gap. So we can really know how the magnetic field is really evolving from a large to small scale, from large to small scale. So thanks to ELMA, we are now able to use the ACA, that is a 7-meter array, to do the precision observations. And this just shows the property of the 7-meter array. So this array has a baseline between 9 meter and 45 meter, and it can provide the resolution that is between the current ELMA 12-meter array and the ZCNT. And if you really check the baseline, this is 4 to 45 meter, and because the ZCNT has a diameter of 15 meter, so the ZCNT can really connect to the 7-meter array with no gap in the baseline. So that's why this is important so this is why it's important to get the ACA precision data, because with this data we can have a complete spatial coverage from ZCNT for the ACA that is around 4 to 3 parsec, and we can further go down to the ELMA resolution that is from 1 to 0.1 parsec. So to demonstrate what we can learn from the AMA plus the ZCNT data, so here we shows our pilot project that is trying to obtain the ELMA and the ZCNT precision data toward this half-Feynman system G33.92 plus 0.11. And here I just shows the very brief introduction. So this source is a ultra-compact H2 region that hosts brighter massive protoclusters. So this is the partial view of this map. You can see they are a very basic clump with some streamers likely converging to the clump. And if we zoom into the AMA view, we can see that here the A1 and A2 is 2 massive protoclusters. And in the AMA view, we can see there are some spiraling arms that is converging toward the central protoclusters. So back in 2020, we first used the ZCNT to map the magnetic field structure in this region. So we could see that in the ZCNT that we can roughly see they are also a big clump, but it also shows some elongated structures. And here I just label that here the protocluster is located at the very center of this region. So in order to know what's the role of magnetic field in these regions, we are trying to first identify the filaments in this region. So here we identify the filaments using the disperse algorithm based on ZCNT continue, and we find that the magnetic field is more or less following the convergent filament. And they also try to estimate the gravitational force in this region, and because it's clearly a condensed region at the center, so the gravity is simply converged to the center along with the filament. And to understand the case kinematics, so here we show the CXL channel map, and we can more or less see that there are some filamentary structure that is likely flowing along this magnetic field and converging toward the central protocluster. So based on this analysis, we propose a scenario that this G33 is actually a gravity-dominated case on parsec scale, and because this one is dominated by gravity, so here the filaments are all converging to the major gravitational potential well, and the gas is flowing along this filament, which also drags the magnetic field. So this is the classical case of weak magnetic field case. But so we are further trying to get the ACF precision data, which has a resolution of 4.5 per second. So we can further resolve the magnetic field within the filament that we cannot see by the ZCNT. So here is the comparison between the ZCNT precision. So ZCNT is magenta here, and the ACF precision data is the yellow segments here. So from ZCNT data, you could see that there are clearly some U-shaped curvature in the magnetic field. And if we compare to the ZCNT data, we can find out that this curvature is already slightly shown in the ZCNT data, but it's very difficult to identify without the further ACF precision data. And here I also try to overlay the ACF precision data onto the 12-meter high resolution continuum map. And you could see that there are here. So here are the 3 spiral arms that is shown in the continuum map. And the 3 spiral arm is actually more or less following the shape of this U-shaped magnetic field. So in order to know whether this curved magnetic field is caused by the gas kinematics, so we first revisit the C18O channel map taken by the single dish. And I will highlight the 2 regions in the blue and the magenta contour. So you could see that there are likely 2 eccentric geometry-like structure that are convergent toward the center. And actually, this curved magnetic field pattern is at the conjunction of these two filaments. So we could further zoom into the central region, and here shows the C18O channel map that is taken simultaneously with the ACF precision data. And we could see that there are some curvature structures that is more or less aligned with the curved magnetic field. And we can also see there are some elongated structure that is following this line and connecting to the massive protocluster in this region. So here we show that there are 2 different gas kinematics. One is pointing toward the tip of the U-shaped magnetic field, and the other is along the U-shaped magnetic field. So in order to understand what is the physical mechanism to cause this kind of magnetic field, we are trying to use the scenario proposed by our previous paper in our paper. So here shows another sample in the SPT13 IRBC, and in this region we also see this kind of U-shaped magnetic field that is along the outskirt of this dense clump, and we also see that there are strong velocity gradient that is flowing from this filament toward the center, and the U-shaped magnetic field is also located at the conjunction of these 2 filaments. So we are trying to use this scenario to explain this feature that so this is the cloud collision scenario proposed by this paper, and let's expect that when the 2 clouds collide together, the shock from the dense flow that will bend the magnetic field, and the compression shock will form a condensed clump that will further become the massive star-forming regions. So also I will note that this object and this scenario happens on cloud scale that is different from what we see in the G33. But we are speculating maybe there are some similar physical process. But to interpret this, we need to further show that if there are any evidence that they are something collide together. So we are trying to use the SL line to trace the shock. And here is the SL emission line. We find that there are some strong shock activities that is elongated, and that is along the tip of the U shape toward the main synchronous cluster. So it shows that it's possible that this U-shaped magnetic field is originally by the push of the accretion filaments from a large scale. So with further high resolution data, we can further zoom into the forming cause within this U-shaped magnetic field. So here is the zoom in, and we could see that this is the 12-meter precision data and continue. And we can see there are even more condensed U-shaped magnetic field all distributed all over the layer that is likely compressed by the large scale accreting filament. And we can also it says no power. Okay, so we can see that there are several dense cores that are forming in the conjunction of the two layers that is at the peak of each U-shaped magnetic field. So it's like it's consistent with the previous scenario that the compression of the accretion filament will compress the region and also bend the magnetic field, and finally forming the condensed holes. So here is just a channel map of 13CS, which tracks the dust continue. And here just showed you that the gas is actually flowing along the local magnetic field and converge to the forming dense cores at the peak of the U-shaped magnetic field. So here we can further show the even high resolution 12-meter precision data, that is the side segments. So we can really see that what's the magnetic field within these cores and compared to the large scale. So here we show two different types. One is the first one is the B and C, where we can see that the side magnetic field is more or less similar to the green segments, which means the magnetic field within these two cores are directly inherited from a large scale magnetic field. But for the core A, it's quite different. We can more or less see that there are probably some fragmentation. There are two peaks in this region, so there could be some local fragmentation process. And the magnetic field is more complex, and we have some we can see some magnetic precision hole. It's partly because the magnetic field is complex. So in the case A, we can see that the magnetic field within this cores can also be dominated by the local fragmentation process, and there is a couple of what we see from a larger scale. So here I will just use a cartoon to demonstrate what's our current picture. We have on large scale we have the filament that is accretion guided by the gravitational force. And at the center of this region, the convergent filaments will collide to each other and bend the local magnetic field, and also cause the condensation to form a softening cores. And toward the smaller scale, we can see the gas is gradually accreting toward these condensed cores and to form a Young-Siller object. And we can see these two cases. And if we move on to see the magnetic field with these two cores, we can see in some cases the magnetic field is consistent with the condensed magnetic field. But in some cases, if there are some strong local fragmentation, then the local magnetic field can still be biased. So this is our current picture. But because this is a preliminary result, and there are still remain work to do. So hereby this some of the remaining work that we are still planning to do to further confirm our pictures. So I will stop here and take questions. Thank you.
Okay, thank you very much. Okay, so we have a time for question and comments. So who wants to ask the first question? Okay, so if nobody, so I think it gives us people some time to think about question, and let me ask the first question. So can you go back to the previous slide about it? Yeah, so this is a current picture about the hub filament system. I am quite curious about the picture here. So basically from the gas kinematics, you can learn about the gas motion and the direction. But the gas kinematics here is just about the gas motion along the layup side, right?
Yes.
But the magnetic fields are actually the projected magnetic fields. So you are comparing the projected magnetic fields in the planetary sky with the velocity along the layup side.
Yeah.
So it's some sense it's not really self-consistent.
Yes, but here we are actually comparing to the gradient of the velocity.
Mhm.
So the gradient is actually calculated by the different line of sight from T at different position.
Mhm.
So the gradient is actually along the plane of sky, so it's consistent with the magnetic field.
Mhm. Oh, okay. So, but I think the more complete understanding would be only achieved when we know the three-dimension structures of magnetic fields.
Yeah, yes.
Because here we don't know how magnetic fields are bent and to what direction magnetic fields are.
Yes. So I think it is quite good to apply your method to try to construct the 3D magnetic field.
Mhm. Yeah,
also,
right.
it's also very difficult because they are strong exclusion at the center.
Yeah.
Maybe the situation is difficult to model.
Yeah, I think here because the magnetic fields seem to be very well ordered, so the deportation by magnetic field tangling would be minimal, and the major deportation would be caused by the loss of grain alignment and also the change in the magnetic field orientation.
It's actually region by region. So if you see this 12-meter cross-section data, you can see there are still some cross-section hole
Mhm.
in the
Yeah.
region and in the denser region.
Mhm.
So in some local region, the magnetic field can still be complex and the technical effect could be important. So yeah, I think the challenge is how to decouple this region from other simpler cases.
Yeah, so I think, yeah, good. Okay, thank you. So now, question from the audience. Yeah.
Yeah, very nice talk and beautiful data. So when you zoom in the scale of magnetic field, you see the last picture that you see that the disturbed magnetic field. That means the orientation is not well ordered anymore. You say the fragmentation, disturbed fragmentation of magnetic field is something. So do you know the cause of that fragmentation of magnetic field?
Well, in some of the cases, like the code A I show here, you could see there are still some region we have no precipitation that is probably due to the tangling. And in order to resolve this, then we should try to get higher resolution. And it's possible because we already have the interferometer data, we can try to increase the resolution by tuning the weighting. So we are still working on this part.
Okay, so we need to have a little bit statistic more data point, you mean, and in order to.
Yeah, we will try to improve the resolution.
Okay. Yeah, thank you.
Okay, so another question from Diep.
Maybe I missed you. Did you comment anything on the missing flux and going from low resolution to high resolution? There's missing flux. So is it important here, and how do you deal with that? Yeah.
Yes, it's important, but it's not always a bad thing because here when we are trying to zoom into the small scale, we want to focus on the compact objects. So the filtering effect can help us to remove the outskirt of this region, so we can really show this image that is focused on the compact objects. But if we want to really recover the total flux, it's also possible because we have full UV coverage from the ELMA to the single dish. So all the flux should be we should have no missing flux in the whole data set if we combine the single dish and the interferometer data.
Yeah. In a few words, what's next? What is the future plan? Yeah.
Yeah, so this is just a single source. So we want to know whether it is a common case or it's a special case. So I think the next step is to get more example for this kind of full scale coverage studies for more different types of objects.
Okay, so let's thank our speaker again. So our next speaker is PhD candidate Nguyễn Bích Ngọc, who is also the LOC member here. So she will be talking about investigating magnetic fields and dust physics in the massive star-forming region W51 using dust polarization. So you also have 25 minutes talking and 5 minutes for question and answer.
Good afternoon, everyone. I'm Nguyễn Bích Ngọc, and I'm from Vietnam National Space Center. And today I'm going to talk about the magnetic field and dust in star-forming region W51 through dust polarization. And first of all, I would like to thank all the persons who involved here, and I want to give a special thanks to Nguyễn Khang here, our former research assistant, and he now doing PhD in Liverpool, and he is a special case for after doing with us, so they get scholarship abroad. And yes, why do we need to study star formation and then magnetic field? Because in terms of high mass star formation, high mass star formation remain less understood and low mass star formation. And because of rapid evolution of high mass stars, so the observation is rare and challenging. But moreover, massive star also important because its impact their surrounding through intense radiation and feedback, and also influence the star formation process. And in addition, the magnetic field also play important role in collapse, fragmentation, and feedback. And that's why we need to study the magnetic field in the star forming region. And to observe the magnetic field, we have several ways, but the important way is using dust polarizations. But because all of in this room we know this process, so I can skip this. And during this study, we use the data from JCT and SOFIA. And why do we need to study W51? Because W51 is the one of the most active high mass star forming region in the Milky Way, and it's located at about 5.4 km/s, and it's home to massive protocluster in the north and in the south. And it's cluster with mass about 10^4 solar masses. And there are also the feedback light structure here. And this package is an idea for study massive star formation and feedback. And moreover, we have multi-wavelength data from JCT and SOFIA, and I saw the map in the magnetic field orientation from JCT Puntu with SOFIA Hubble footprint overlay. So we have 5 wavelengths so far, and from that we can study the magnetic field morphology in W51 and the magnetic field strength and the importance of magnetic field in comparison with other factors like gravity or turbulence. Another question is that also it can tell us about the dust physics. Firstly, about the magnetic field morphology in W51, and I show here is 2 examples of shortest and longest the wavelength, and you can see that the morphology is quite consistent across wavelength, and also they also have a different resolution, but we can see that the magnetic field is quite similar. They also see the X shape, the magnetic field line follow the X shape, and we also see the curve in core due to the gravity, but there are several places different like display. And in data from JCT, we can see the filament structure, and the magnetic field is perpendicular to the filament. To calculate the magnetic field strength, we use David Chandrasekhar Fermi method, and it's based on the assumption that gas turbulence motion is the driving of magnetic field disruption. And after calculate the magnetic field strength, we can calculate the relative importance, like gravity versus magnetic field or turbulence versus magnetic field. And to calculate the magnetic field strength, we want to build a map of magnetic field strength. So we firstly we need to have a tree map of volume density, velocity dispersion, and polarization angle dispersion. For volume density, we use volume density SED15, and we assume that they have the depth about 1 parsec, and we calculate it from the using atomic depth by the Holden method. And for velocity dispersion, we use C13O from GCMT, and for polarization angle dispersion, we apply the method of GPY. And for the magnetic field strength, we can see that the magnetic field strength vary from about 100 microgauss in outer region to about 500 microgauss in depth region. And in some case, like we have the magnetic field also go up to 1 microgauss. For the magnetic mass to growth ratio, it tells us about the importance between the gravity and magnetic field, and it shows us that the supercritical, in the protocluster is supercritical. It means that the magnetic field in the gravity is dominant over the magnetic, and it's consistent with very active star formation there. And for the max, for the appendix max number, we do the math here, and you can see that for the region of protocluster, we also see that this region in the non-universal, there are also super appendix max number. It means that the turbulence dominate over magnetic field, and it's maybe the condition for gravitational collapse and star formation. And lastly, what the multi-wavelength polarization can tell us, and like Chapman presented in this morning, you can see that the average polarization spectrum of W51 have a V shape. This is the average. And to remind you that there are two kinds of dust model: it's separate dust model and composite dust model. We have a different spectrum of this kind of model, the state spectrum and class spectrum, and we need two layers just to explain the V shape. But for study the multi-wavelength polarization in detail, this is the map of the slope, spectrum slope in the range of this wavelength, and you can see that in the north and in the south region surrounding the cluster, we see that positive slope is mean that the slope is rising in this wavelength. For the blue region, it means that the negative slope, it means that in parallel spectrum. And I show here two examples of two kinds of slope, and you can see that in the E1, E2 region around the protostar cluster, we see the V shape, and it can explain by the two dust layers, the hot dust surrounding the protostar cluster and the cold dust in the outer layer. And for the short region, this region, for example, we see that the E-point length spectrum, and it can explain by the separate dust model, and it's inconsistent with, we know that in the short, the dust can destroy, the carbon dust can easily destroy the silicate dust, so we still have a silicate dust here, so it can make this kind of polarization spectrum. And for the next step, I also want to do what did with OMC1, and this is really mean preliminary result of one dust layer model. And the next step, I want to do it more. And yes, this is my conclusions. We see that from the multi-wood plane data, we see that the magnetic field morphology is set by stellar feedback, and it's remain consistent across wavelength. And we also see that the magnetic field is weak compared to gravity and turbulence. It's consistent with the very active star formation in W51. And from the dust polarization spectrum is right to the dust physics and dust alignment. And for lastly, I have the open question to discussion today that we also have the different data from different wavelength. But in OMC1, we see that in the shorter wavelength, we see the hourglass state of magnetic field. But in the longer wavelength, we don't see it. Maybe it's very different dust layer. But in W51, we see the magnetic field is consistent over wavelength and over the scale. And maybe this magnetic field in W51 may trade same dust layer or different dust layer, but the dust layer have the same morphology of magnetic field. So question. Like we know that the OMC1 is the nearby cloud, but W51 is distant. So the difference between the physical scale is maybe 10 times. And another question, maybe we can discuss it, what we can constrain about dust physics. If we have more data, maybe from Swapie, GCMP or Iran, so what we can constrain. Thank you for your explanation.
Okay, thank you. Now, yeah, I think for W51, we also have a data from SMA and ALMA. So we can even push towards the much smaller scales. Yeah. And then if you zoom in smaller scales, maybe we'll see the magnetic fields different from. Yeah. So, okay. So, I mean, yeah, but for OMC1 and W51, because they are located in different distances. So even for the same wavelength, but OMC, you are zooming on much smaller scale than W51. So I think it's quite difficult to compare if you have a different spatial resolution. Yeah, dust layers. Yeah, right. But, Okay, so how about the dust temperatures? Can you estimate the dust temperature from W51 and OMC1? That is a key thing, yeah. Okay, that is quite reasonable because you have a higher, lower spatial resolution. So you are just tracing dust in the lower temperature. Yes, okay. But it's good to have the map of dust temperature when you want to study the alignment. Oh, okay. Can you show us that? Okay, map of temperature. Okay, good. Yeah. So did you analyze the correlation between dust polarization fraction and dust temperature? Oh. Yeah, so maybe can you show us now? Okay. Is this ongoing work? Okay, thank you. Okay, so now question. Other questions? Yeah, Shiva.
Thank you, very interesting work. So as you show, there's a V shape suggesting there are two different dust layers. I'm curious, in such case, the B field strength derived, do they correspond to different dust layer? Or when you derive density or temperature, how to account for this effect?
Because in this case, we didn't see the difference between the wavelength, right? So maybe the dust layer is the same morphology in the host layer and in the
I think one common. So here I think I prefer to use a cold and warm dust, because hot is something when you touch it, it's really burns your skin. And here's a dust temperature you found is below 50 Kelvin. So I think it's reasonable to call it warm. Warm is nicer than hot.
So Ngọc, we discussed about that. I still found it very interesting that you show clearly that when we have the shock, so we cannot have the composite structure. That means silicate and carbon must be separated. And then we see the decrease in trend. Whereas when we have like star forming region like E1, E2 and north, where you have the star forming region activity, you show the V shape, which means you have the warm and the coldest cover each other. I think this is still very interesting, but I just wonder the fraction, polarization fraction here is just 0.7%. What's the error of what's the error bar of the data?
Here, but yeah, but I was also surprised that the W51 they have a very low polarization fraction. Yes, but everywhere maybe something. Yes, first of all, it's the error bar of the one of them.
2% is fine.
Yeah.
In this case, 2%, but the
This one, you see the polarization fraction.
yeah, but 0.7% is very small.
Yeah, I think the polarization level here is really low. So I think if we look at the polarization by SMA and ALMA towards W51, I think the polarization level is even much higher. Oh, okay. Yeah, so so in the shock here, what is the shock velocities? Because in order here, yes, so in the shock region, so we know we need to estimate the shock velocity. So because if the velocity is just slow shock, so the grain shattering may not happen. But if the relative velocity of dust grains are large, so and then the shattering can help to separate silicate from carbonaceous grains. So we have to estimate the shock velocity. Okay. Other questions? So if not, so let's thank Ngọc again.
Gilbert, I have a quick announcement.
Okay, good.
The deadline for registration for excursion. So I also send an email for you, but maybe you miss this email. Please check it. You can register by this email or send an email for me. Thank you so much. I think last week.
Okay. Yeah. So I think in this case, please remind us that. Thank you for reminding us about the excursion. Okay, so now we have the next speaker, Dr. Ngân Lê. So she will be talking about magnetic fields and the dynamical roles in the massive filament DR21 using both gas kinematics and dust polarization, right? Okay, so good. You have only 15 minutes talking and 5 minutes for Q&A.
Hello, everyone. Hi, everyone. So today I will present some initial results about the project where we study the magnetic fields and their dynamic roles in the DR21 filamentary molecular cloud. And in the figure on the right side, you can see briefly the magnetic field pattern toward this filament at the far infrared wavelength from Sophia Hawk-Plus. So to start, I So I will start with some quick introduction. So far we know that the stars are formed in the cold and dense part of the molecular cloud, which have many structures inside. For example, the filaments or the clump, and the dense core inside that the clouds can be formed. And from this map on the left here, it is showing an example of the star forming region cloud. And we know that the star formation is quite efficient. So why? I think you have seen this the figure on the left already from the talk of Archana Schwam, and I just want to remind you that if in that figure we see that if we consider the impact of on gravity, turbulence, and magnetic fields, and also the stellar feedback. For example, the jet or the outflow impact from the star forming the star. So in that such combination, so we look at the white curve there. So we can see like the star formation rate is quite lower compared to the other case when it's considered, and it's close to the result from the observation. And from the right side, it is just a simulation where we can see like when we consider as much as factors, so we can see like how it will near to the realistic star formation scenario. So we can state that with the gravity, magnetic fields, turbulence, and stellar feedback, they are like the key agent that can regulate the star formation activity. Among those agents, the magnetic fields are the key ingredient for the star formation. So in this project, we focus on the magnetic fields and also other factors. But first, we want to focus on the magnetic fields and how to measure the magnetic fields. This morning, so Trump have give you some idea like there's some method to measure the magnetic fields. So for the morphology, so for a long time, we use the dust polarization observation to infer the morphology of magnetic fields, both with the absorption polarization and thermal dust polarization emission. For the strength, the traditional way is using the DCF method, but so far there are several developing the method so that we can confront the limit of the DCF method. And back to the dust polarization observation. So there are, until now, there's a lot of polarimetry technique. So I'm back to a slide from Tim. So this morning, and we can see like there's a bunch of instruments that we can use to trace the dust polarization from the near infrared, from the near to 5 infrared up to sub-millimeter or in radio. And here I'm showing some example of the magnetic field morphologies map towards some star forming region or from the large scale to the smaller scale using the various polarization. Using various instruments. For example, we can use the Ponto polarimetry from the JCMT in the sub-millimeter or with the 5 infrared wavelength with the SOFIA Hawk Plus, with the pretty high resolution from the ANMA, we can trace down to the smaller scale of the protostar or of the protostar. And just remind you a bit about the talk from the at the beginning of this afternoon about the ballast bond series. So this is stand for the B-fuel and dust interstellar filament using the dust polarization. And again, the goals of this project is to measure the magnetic fields and also the dust physics in the filamentary star forming region. So here I'm listening so far the project that is related to the ballast bond. I hope that I don't miss any project. And coming up with that idea, because we have heard from this morning that there is some relation between the dust and also the magnetic field. So I was interested to join in this project. So we were thinking about doing the next ballast bond. So why not? So from that, we start with the idea of measure the magnetic fields and dust physics in the DR21 filaments. And here is a map of this filament. It's showing in the red block here, if you can notice. And why I choose this filament? Because it's like massive filaments belong to the nearby high mass star forming region. The Cygnus, this is the whole region. And also with the distance around 1.4 kiloparsec from us, so it's like we consider it's like one of the best sites to study the interaction between the UV radiation and the interstellar medium. The reason for that is, as I mentioned, this is the filamentary high mass star forming region, and there are some a lot of identification of the cores inside the filaments. So there are not only we have the agent of gravity, turbulence, magnetic field, of course, and now we are looking for the stellar feedback in this region. So the main goals of this project is to we want to measure the magnetic fields and also want to investigate their roles in the evolution and formation of these filaments, as well as to study the star formation activity inside the filaments. And then we want to test how dust can evolve and align with the magnetic field in this beautiful filaments. So to start with that, we might use the data from dust polarization observation at far infrared wavelength from SOFIA Hawk Plus. And here I'm showing like one of our first results of the maps of magnetic field morphology at 3 different wavelengths. And let me show you a bit about the morphology map. So the first one from the right side is the map of morphology to the entire filament at the longest wavelength in band E, and in the white, the yellow box here is associated with the map of the morphology magnetic field at the it should be here at the shorter wavelength in band C. So this map is smaller a bit than the entire map here. And lastly, in the white box This is showing the map of magnetic field morphology in the shortest wavelength in band E around 50 microns. And these magnetic field vector are inferred by simply rotating the polarization vector by 90 degrees. After that, we make the comparison with what we have from the previous study with the JCMT PON2. And because the map from the JCMT PON2 is smaller, so I'm trying to make the comparison here. And again, I mentioned that there are so many core inside the filament, but I can highlight three most massive core are the DR21 at the south, and the DR21OH in the middle, and the last one here at the middle north a bit. And if we can look briefly, we can see like there is a similar pattern. There's a similar pattern of magnetic field vector between the JCMT PON2 and the SOFIA Hawk Plus at the longest wavelength. Like the magnetic field line are perpendicular with the rig of the filament. But when we move to the shorter wavelength, we see some difference. So it can tell us like the reason is because different wavelength of polarization can trace different layer of material. And it also mark a question about the dust physics or the mechanism of how dust align with the magnetic field at different wavelengths. As a next step, we want to measure the magnetic field strength, but now in 3D. But for that, we need first the 2D information, and I think most of us are familiar with the scheme here. So we plan to measure the 2D magnetic field using the DCF method, and to get the 3D information of magnetic field strength, so we need the inclination angle. And because this is, I served this for Bao Zhong, so we can wait a bit until tomorrow, so he will talk more how to derive the inclination angle. And just a hint, because this work is still in the progressing. So from this study, so not only we can measure the 3D magnetic field, but we can constrain also the dust physics, for example, grain size or elongation or the dust grain alignment in the filament. So we can test how dust can evolve and align with the magnetic field in various scales. And after all, when we have the information both of morphology and the strength of magnetic field, we will start to study the role of magnetic field as well as other factors in the evolution and formation of filaments and also in star formation. So thank you for your attention.
Well, thank you. Okay, good. So we have plenty of time for questions. Okay, so any question? Okay, so I have one question. So can you go back to the comparison between the map? Yeah, so this is two wavelengths, right? So you are saying that the polarization angles are quite similar at two wavelengths, right? And how about the polarization fraction? Do you analyze the polarization fraction as a function of wavelengths?
So until now, I have not done that yet because I am still in the process of getting the map of dust temperature and
the dust temperature. So do you have the map of dust temperature?
Not yet. I have some the result from other study, but I wanted to make my own calculation. polarization, and till now it's not ready to show yet.
Oh,
Yeah.
okay. This is.
But you are right, because the polarization fraction is important to study, to test about the dust polarization spectrum. But at this step, because I consider like the maps are more important, so I just want.
So which maps are more important?
Not more important, but it's needed to start the make the correlation between the gas and the dust polarization info.
Okay, so you want to focus on something more important first? Why not just focus on what you have right now first? Because if you already have a pollution fraction, you have a different wavelength. Just plot the pollution fraction as a function wavelength. Just everything you have in your hand right now, right?
I see what you mean, but somehow from my point of view, I want to prepare some ingredients first, and then I will start with the analyze. But I know what you mean.
Okay, good. Okay, John.
So, from your title, you say you can use the VGT or gas dynamics. So, have you done anything with your gas tracer, and what kind of gas tracer you are using?
So indeed, I prepare some slide for using the gas kinematic to derive the magnetic field morphology, and but I skip it at the end. So one of the strategy from this project is that we want to constrain the magnetic field morphology using the gas kinematic with the velocity gradient technique. And so I hope I have 2 minutes to explain about this technique. So basically, the velocity gradient or the velocity gradient, somehow it's expected to perpendicular. This vector is expected to perpendicular with the magnetic field vector. But if in some medium there are like strong there are some perturbation, either come from the movement of the material or the turbulence or whatever. So it will change the alignment between the velocity gradient and the magnetic fields. So if we can detect any such deep misalignment, so we can expect that different come from the perturbation of the star formation. For example, the outflow coming from the outflow of the Z coming from the young star. So based on that, the velocity gradient technique is using the gas kinematic information to derive the morphology of the magnetic field, and then we will come from the result of the velocity gradient technique. We will compare with other results from the dust polarization, and if we see any difference between the two, so we can guess. We can identify the star from the different side, and this might associate with the star forming region, because it's related to the inflow or outflow from the young star. And this is the idea. And from that, we can study the relation between the magnetic field and the other factor. Indeed, I have one result from the velocity gradient technique, but for the for this, it's just like some of my first runs using the velocity gradient technique, and I did not show it in the presentation because, honestly, I found something not correct, and I need to check. but we are still working on that. So it's quite, I think it's quite promising to do the application of the BGP.
Okay, so here one more question from Bao.
Yeah, hi. So thank you for nice talk. I just don't have question. I just have comment because that you mentioned about my talk tomorrow. So in fact, that when we apply to the inclination angle, not only we just derive from the 3D material strain, when we combine that with the plane of sky magnetic field that we measure from DCM method, but we also can use that inclination angle combined with the 2D vector that we can have from a plane of sky in order to reconstruct the 3D morphology of the magnetic field. So that is the one another comment that we can derive both the strain and also the morphology as well. So in this case for the DR21, also really exciting case for derive that reconstructible 3D morphology. Yeah, so that only just my comment. Yeah.
Thank you.
Very short comment that we can talk afterward, but I don't recommend you to use optically thick TLCO here. You try to use optically thin tracers.
I agree with you. That's why I said like I'm just trying to do the best by my own. But I agree that it would be good to use the optically thin line. So for such study, so I have a set of the thinner line like 13CO or C18O of the same emission transition. So yeah.
Okay. Okay, thank you, Nguyen. So any other question? So if not, let's thank our speaker again. Okay, so the next speaker is a very young, promising student. So he's a bachelor student, right, from University of Science and Technology in Hanoi, Cho Chen Quang Anh. So he will be talking about grain alignment and dust evolution physics using dust sploration. He focused on a study score named L1512. Okay, so you have a 12 minutes speaking and 3 minutes for question and comments.
Okay, good afternoon, everyone. My name is Chen Wang from UC of Science and Technology of Hanoi, and today I would like to present about the second project of WIPO. It's on the project, on the object is study score L112. So here I have the outline of this talk today. First, about overview what I do in this study. Second is introduce about our numerical modeling. I will study about again the version of the study called L1512, the arm modeling applied, the conclusion and the abnormal. And first for the overview, I would like to remind again our first project of the WIPO on the object is by 109. As here we have the very beautiful graph of the AB map from the different place X, Y, and XS, and also have and we also have the graph I already have mentioned on the WCM talk this morning about we have the observed data and we have a lot of the curve created by our model. And for the previous research of the study called 152, they apply the RAIN model to study about the RAIN alignment of the dust, and also have the observation data of the column and the AB map. And what I do in this study, I will combine them. I will using the numerical, the dust phobia model to study again the dust variation in and I will select this. We will create a map of AB, study the dust variation in the both region of the tumulus and the variation region. And first about the numerical modeling. So I have the image here. So we are the observer from this direction. Here is the X direction. So this one is the Y direction. We have the sphere. So I hope you can understand this. And we extend 35 point again along the Z direction, 70 point along the Z direction. That's the direction that we observe. And here we also have the ABO, AB 1, 2, 3 something, the R in, and the gas balloon is defined by this function with the maximum, the inter outer radius, right? And this and our model is also very give the key parameter to study about the property of the star modeling and about we will representing the dust variation of the cycle of this cycle. So first I have the visual map of this object, and the region in the center very small here. We're going to thermal dust region. The outside is the star variation, and we apply two constituent different for two region here. And then we create the model of the AB. First, all right. So first, I convert the column density to the AB map by using this equation, and two is the RV4. And here we have the map of the observation AB. This region will be look quite weird, but it's from the inducement, so it not affect to the physics profile here, so we don't need to worry about this. And for the model, we use this parameter for our model to create the map like this. And we can see it's quite look the same with the observation model. And for the random alignment, we apply again the recent model. And here I have the curve, the black line. So this orange range with the slope is the -1, and the red curve here is the Riemann model with the slope of the -0.5, and two vertical line here. The first one here is the asymptotic slope, and the second one is the critical intensity. There are two tests to show us where we have the alignment and where the alignment is so very clearly. From this one, we can see most of the range get the alignment, but there are some field data is still this alignment here, right here. And now we study about the thermal regression. And for this, we keep the two terrible line, the red and the black here, one with the alignment and one with noise. The data of observation with some dot here, and to model curve, one with the blue one, showing the alignment data, and the green one is this alignment data. And we can see the parameter I show here. The S is the range axis ratio, and the AMAS is the maximum variation. Yes, and we can see for the alignment data, we can say that's the value of it is longer than this alignment. So it's correct with the right theory, because with the longer range, we have more easier to become alignment. And for the star variation reason, actually we have something wrong with this. We have to estimate again the AV map, so that's why I cannot show the result today. But the idea is in the thermal reason. That means we still keep the two teruguli, the data, and we will bridge to model curve to showing this. And we expect that the S and the A map will be lower because this reason is in the outside. For the conclusion, so first we already studied again about the version of the cell of the called L1.12 by using the Riemann model. The second one, we applied the dust guy for the AV map and the thermal dust reason. But for the star version, we didn't have the result, so that's why I cannot show it today. And the last I want to say thank you to my main supervisor, Dr. Cheng here, Dr. Sadun Lam, Dr. Simi Lai from Taiwan, and the other member from Vietnam to help me work in this project. And that's all of my presentation today. Thank you for listening.
Okay, thank you. Yes. All right. So now question. So we should give him some motivation.
Yeah, really funny talk. Yeah. Okay. Can you go back to slide number 7? I have 2 questions.
2 questions in 2 marks.
I don't understand why you choose this from going the
going
Yes,
from 2 to 3?
they consider this the best for tourism here, and it's also mentioned in the Dr. Lin paper. And I just
Why
applied
not
quickly.
going higher than 3? Why do you?
Because higher than 3 is they are not enough data for that. They're too much.
Strange. Okay. Next, slide number 10.
Way too much. All right. It's not me.
Okay. So you have, I'm interested in 2 lines, blue and green.
Blue and green, yes.
Yeah. The difference is coming from S and A max.
Yes.
So what is the basis of choosing these 2 parameters? These, as I understand, these 2 parameters going in the same way. If you increase S, it means it's more, those grains are more elongated, and then the polarization is higher, and then A max is the same if we're supposed to have the same A line, right? So how do you choose? Why don't you keep one parameter fixed and vary the other one? And
I not do this by hand. I just create a very set of parameter, and we create about almost 300 set of parameter like this, and I run the chi-square to see the best fit for this, and the result show with the 2 curves like this. So it means I run this for all of the data we have, run the chi-quest, and they get the like this. They are 2.
So you did do the fitting.
Yeah, we did.
Yeah, so here I think he did the 15, but first of thing, this is the first ever presentation that Quang An did, so it will be better in future. But here is he vary 3 parameters. So the maximum alignment by rad F max, the grand shape S, between the ratio between the major axis and minor axis, and the A max 3 at once at the same time, and I don't know, you say 300 models.
Almost 300 because we run the image from railway 1 to 3 microMesh with the Savit over 1.
Yeah.
So like for proportionality we have like 30, and we multiply it like we have about 280 around this. I didn't count.
And he do the chi-square, but I don't remember the value of chi-square. Maybe
it's close to 1.S1 around this.
Close 1. But one thing we don't understand here, here we understand that when the lambda max higher, S max seem a little bit higher. That means more elongated grains, but not too much. But when he did a little bit with starlight polarization, we see the degeneracy. Yeah, you show that the S is higher than in the starlight polarization. So that
we display that.
Yeah, so I think we need to do again for starlight.
Okay, so Bao, you have a question?
Oh no. What?
Okay, so thank you for the nice talk. Okay, I just want to ask this this figure. So which means like you apply the chi-square fitting for the lower limit of this polarization data to the upper limit of this polarization data, isn't it?
I apply this for both of theory.
Yeah,
for both theory line.
Yeah, because I saw like you apply for upper limit and you apply for within the Ryzen within the Ryzen fitting. But I also saw that there are more data above that Ryzen fitting. So do you have plan to apply that for that kind of upper limit? Yeah, because the range of data is more above to that Ryzen fitting.
Yes, I apply for both of this.
Higher one.
Higher one?
Yeah. In the data point higher one.
I did. Yeah. I should do that, right?
Yeah.
Okay. So I see.
And that is the first question. The second is I just want to go back to the slide that you mentioned about the line of sight gas density.
This one?
No. Go back on.
This one?
Back.
Oh no.
Back. Yeah, that's one. So I just wondering like how you can calculate the line of sight average volume density in this from this NH2 line of sight map, and it's also correlate to the Airbus bonosphere that you assume in the dust profile.
This is from the observation data in the Dr. Lin paper. Yes.
But how you can calculate? But it's already calculated from the Dr. Lin data.
It's already in his paper. Yeah, you're right.
Okay, I see. Yeah. Thank you for making it clear. Yeah.
You're not my friends.
Thank you for a nice talk. Can you return to slide 9? And just more question about the Richian model. I'm quite unsure about the term L1/2. It's the likelihood or something else?
Yeah, it's the how to spell it, the language.
Likelihood?
Language with the 1/2.
Okay, I see. Okay.
Right. That's all. Everybody get hungry or something?
Okay, any question? Okay, so if not, let's thank our speaker again. Okay, so the next speaker is Dr. Pravash Singh. Oh, PhD candidate. Oh, I see. Okay, PhD candidate Pravash Singh. I cannot pronounce his first word in his name. Oh, Saikom Pravash Singh. Okay, so Pravash.
Okay, sir. Am I audible, sir?
Okay, good. So you have also 15 minutes in total. So 12 minutes speaking and 3 minutes for Q&A. Yeah, you can go ahead. Pravash.
Okay, sir. Thanks. Okay. Today, first of all, good afternoon, and I am very thankful to the organizers for giving this opportunity. So today I will be talking about the dust grain alignment and disruption mechanisms in a massive infrared dark cloud G34 using dust polarization observations from JCMT Pole 2. So the outline of my talk will include a brief introduction about the physics of grain alignment and disruption mechanisms. And then we'll go on to our observational study about the data, and then our analysis and discussions of the results. And then I will present the conclusions of the overall work. So first of all, as mentioned by Satyam also in the morning talk about the importance of dust grains in various astrophysical processes, dust grain is a cosmic is a very crucial element. It takes part in process like star, planet formation, formation of water and other molecules, and for the beginning of life. Usually, dust grains are available in two types of compositions: one silicates, which are pyramidal in nature, and carbonaceous, which are diamagnetic in nature. So when we talk about this grain alignment, it came to be revealed from the observation of dust polarization. The star-like polarization was first observed by Hall and Hilton in 1949, and from that it was revealed that it's due to the aligned non-spherical dust grains that due to the dichroic extinction by aligned non-spherical dust grains. Also, these dust grains also re-emit polarized radiation at longer wavelengths from this aligned grains that we call as the thermal dust polarization. In our study, we will be studying about the thermal dust polarization in that infrared dark clouds. So briefly mentioning about the grain alignment physics. How the grains align? Usually grains, for their alignment, they undergo two types of alignment. One called internal alignment, where an irregular shaped grain rotates, the angular momentum tries to precess around the axis of maximum moment of inertia, which is the minor axis of the grain. And then J aligns with the minor axis A1, known as the internal alignment. So this particular grain can give polarization. But however, when we observe along a line of sight for an ensemble of grains to get a measurable polarization, net polarization, all these grains, they need to align along a common direction. For that, they undergo through external alignment. Mostly silicate grains, when they rotate, they become magnetized by Barnett effect.
and induce magnetic moment, and that makes the angular momentum to precess around the external interstellar magnetic field and gets aligned with the magnetic field. This is known as the external alignment. Particularly, silicate grains are aligned along the magnetic field with their minor axis parallel to the magnetic field. So in silicate grains, their minor axis parallel to B field and longer axis perpendicular to B field. So many theories were proposed since the observation of this polarization. However, the most accepted theory is the alignment induced by relative torques, known as the relative torque alignment. And here in the modern grain alignment, I think all these have been explained by Satyam in the review talk in the morning. I'm just reminding the theories that will be that will explain my results in my study. So red A, and then M reds when the grains have magnetic grains have iron inclusion as clusters, they become supermagnetic nature, and magnetically enhanced magnetic relation can increase red alignment efficiency and higher polarization. Also, higher relative torques, in strong relative torques, the grains can rotate very fast, such that centrifugal stress greater than tensile strength that can result in the disruption of grains, known as the relative torque disruption. So all this have been explained by Satyam in the morning talk. So after reminding this brief introduction, let's go to our observational data. We use JCMT Pol2 data to observe the thermal dust polarization emission in this G34 region at 50 micron. There's a beam resolution of around 14.1 arcsecond. And for the gas column density dust temperature, we use the Herschel PAX sphere data, and using SED fitting, we create the temperature, dust temperature, and column density map. So this is the filamentary structure G34 region. It's an active star forming region at distance of about 3.7 kiloparsec. This is the H2 volume density map, and this is the dust temperature map, and this is the total intensity Stokes I map observed by JCMT, and this is the intensity map overlaid with polarization vectors. This shows the magnetic field orientations. So here we see that in the here this G34 region hosts around nine cores, out of which 3 cores, MM1, MM2, and MM3 are the active star forming region hosting protostars. So here in this MM1, MM2, MM3 regions, we see higher dust temperatures, which is due to the presence of the massive and luminous protostars inside. So we divide the filament into 3 parts: northern, central, and southern regions, and we study in each of the regions our grain alignment mechanisms. So first we check the relation between polarization and total intensity, as well as the gas column density for each of these 3 regions. Here we find polarization decreases with increasing intensity and column density, which is popularly known as the polarization hole. So interestingly, in the center region, which is shown by magenta color, and here we fit by gray solid line, here we see up to around 850 millijansky per beam. Polarization decreases, but at 850 we see an increment in the polarization, and then as the intensity increases, decreases. This part is interesting one, which we'll explain later, but I will come to this part and explain again. Again, we check the relation between polarization with dust temperature. Here we see the polarization increases with increasing dust temperature in nodes, but we see some part with decreasing part also after 19.8 K in north region. But south region shows only monotonically increasing. Center region shows overall an increase up to around 19.8 K. After that, it shows a decrement. And this plot, NS2 versus TD, tells us about their correlation. It tells us information about the presence of bright embedded sources. In starless course, it should be anti-correlation perfectly, but here we see an increment in the north and center due to the presence of the protostars embedded. So this part here, increment is, we identify this region before 850 millijansky per beam as the region outside the cores, and above this intensity value is the region inside the cores MM1, MM2. In the cores, in the outer part of the core, the intensity from the central protostars can be favorable for alignment of the grains, which may increase the grain alignment efficiency. But as we go more towards the protostars, or as we go in the higher intensity regions, the relative torques will be stronger and stronger. It can start disruption of the grains, thereby decreasing the polarization. From here also we see at higher dust temperature, which is about 19.8 K, which is the region we identify as the core regions. Here we also polarization decreases. The increase in polarization with dust temperature in expectation of red alignment theory, but the decrease in the polarization at the higher temperature is an indication of the relative torque disruption. So however, the decrease in this polarization hole can be caused by two factors, either decrease in grain alignment efficiency in denser regions, or due to magnetic field tangling, or a combination of both. To disentangle the effect of field tangling, we estimate the polarization angle dispersion function, and we see the relation between P, S is the polarization angle dispersion function, P with S. Here we, in the north and the center region, we don't see much significant correlation, but in the south region, we see some slight decrease in the polarization at the higher S value. And we study the P cross S, which gives information on the average grain alignment efficiency after removing the field tangling effect as a function of intensity and gas column density. We see similar kind of variation with our previous P with I and P with NS2 plots, except the south region where we see a nearly flat distribution. From there, we came to know that the field tangling is not significant in the north and the center regions to cause the depolarization or polarization hole, but in the south region, field tangling has some contribution to cause the polarization hole. So further this part, we plot we further see whether this decrease in the polarization with higher temperature is due to field tangling. We remove the field tangling effect and plot P crosses with TD. Still, we see the grain alignment efficiency decreases at these temperatures. This from here, this increasing part is an expectation of red alignment mechanism, and this decreasing part gives us an hints for the possibility of disruption of grains, which decrease the polarization, grain alignment efficiency, and hence lower polarization. So further, to test whether our red paradigm, red and red theory can reproduce these observational results, we estimate minimum alignment and minimum disruption size of grains using the analytical relation as established in Hong et al. 2021. And this is the map of minimum alignment size and the minimum disruption size. Here, this MM1, MM2 cores host protostars of around 10 over solar luminosity and mass of around 400, 500 solar mass. And this MM3 core has around 10 to the power 3 solar luminosity protostar embedded and mass of 1,000 solar mass. So in this massive and luminous protostellar cores, we see decrease in the alignment size as well as the minimum disruption size significantly. So in the red paradigm theory, when those grains which are above A align, if we don't consider a distribution is there, then A align to A max, those grains in this range are participated in the alignment of grains in the giving polarization. But however, if a disruption size decreases and somewhere in between this, then those grains from A max to a disruption part are disrupted and not contribute are not aligned and not contribute in polarization, and only this part A aligned to A disruption are give polarization. So a decrease in the A disruption size can decrease the polarization due to narrowing of the grain size distribution of aligned grains. So then we check the A align as a function of the intensity. Here we see in the north and center, in the north up to 350 millijansky per beam, it increases, after that it decreases, and in the center up to 850 millijansky per beam increases, and then so overall decreases, but south region only monotonically increases. So this part as mentioned earlier in the notes, below 350 millijoules per beam, and in the center below 850 millijoules per beam are the regions outside the cores. And after this intensity values are the regions going towards this protostellar cores. Because of this alignment size decreases. Then this is an increase in the alignment with eyes and expectation of red alignment. But this decreasing is against the red alignment theory. We plot a P versus A line and P cross S versus A line. Here we see as the A line increases or as we go to the denser regions, the polarization is found to be decreased. Here the fitting is done only for the below the outside the cores. For the region of cores shown by the black, its color, the data points. Here we see at the lower A line values, the polarization is expected to increase, and polarization grain alignment efficiency is expected to increase. However, we saw it's still decreased, it's still small, and this gives us another signature for the relative torque disruption of grains. So this is the histogram distribution of the minimum alignment size and the minimum disruption size. Here we plot the grain size with dust temperature. In after 19.8 K, we see in the nodes the a disruption significantly decreases around 0.86 micron, and in the center region, especially after 25 K, the disruption size reaches up to around 0.64 micron. So this gives us an evidence for the possibility of happening disruption of grains, which can explain the decrease in the polarization in these denser regions. Also, we also find high polarization fraction above 8%, up to 20%, mostly in the outer parts of this filament. For that, we check whether it is purely due to red alignment or is there importance of the magnetic relaxation strain. So we estimate the magnetic relaxation strain considering the superparametric nature of grains in these dense regions, and we see that especially in the outer regions, in the node and center regions, this vector show the polarization vector above 8%. These gray vectors, we see in the outer regions, the regions where the polarizations are above 8% are coincident with the higher delta mag values, and this gives us an means very above 10, because in the Hong and Lazar in 2016, they saw that if it's greater than 10, superparametric grains can achieve a perfect alignment, giving higher polarization. So our study finds possible implications for the possibility of magnetically enhanced red mechanism or M-red mechanism to explain the observed high polarization fraction in the outer parts of the node and center regions. But in the south region, the delta mag value is very smaller than 10, so it's not much favorable in the south region. So the main conclusions of this work is, first we find the well-known phenomenon called polarization hole, decrease in polarization with fraction with increase in total intensity gas column density, and we find that the magnetic field tangling effect on this observed polarization hole is minor in the node and center regions, but it's significant in the south region. Again, the polarization hole in the nodes in the region below 350 millijoules per beam and center below 850 millijoules per beam, which are the regions outside the cores. This is here the polarization hole is due to decrease in grain alignment efficiency in denser regions, as expected by red mechanism. And in these core regions, above these intensity values, we find evidence for relative torque disruption mechanism. Also, we find this potential hints about the M-red alignment mechanism that can explain the observed high P values in the outer regions of the filament. So this work is a part of the Balat paper which Sardiev was introducing in the morning talk, and this is a third in the Balat series, and this work has been published recently in the Astrophysical Journal. Okay, thank you.
Pravas. So we have now several minutes for questions, comments.
Yes, sir.
Yesterday, very nice. So that you have evidence for the question, right? Toward the star formation activity.
Sorry, sir, I could not hear.
So even you plan to pixel by pixel degree polarization in your observation.
Hello, sir, I could not hear, sir.
Okay, I changed the mic.
Oh, okay, okay. Now I can hear.
Come again on the mic. You show the evidence of the Raddi mechanism toward the star forming region, right? And
Yes, sir.
that the magnetic field variation or tangling is not very
Significant.
significant.
Mm.
The future work, do you plan to model or predict pixel by pixel the degree of polarization and compare to your observation?
Yeah, that we plan. Yeah, we plan to do in future.
Okay.
Okay, any other questions? So Pravas, I think Chum also was curious about the estimates of magnetic relaxation strength. So what is the value of iron cluster did you assume for the estimates you show?
It was yeah, it was I think it was 0.3. It's around 3% of iron evidence as clusters.
So 3%, that is a volume filling factor, but N cluster is, do you assume like 100 iron atoms per cluster?
Oh, yes. Sorry. NCL, I took 100.
Okay, good. Oh yeah, there's also one question from Sarhana. You can go ahead. Sarhana, please speak up.
Hello.
Yeah.
Yes.
Yeah, so my question is regarding your second conclusion. So you told that magnetic field tangling is minor in the case of north and central region, while it is significant in south region. So means why it is so? Means why it is minor in case of north and central, and why it is significant in south region? So what is the difference between these regions? So one is regarding this core, embedded cores.
Yes.
So what could be the reason for that?
Here we saw that the relation between the polarization as a function of the polarization angle dispersion function.
Yeah.
Here in the north and central region, we don't see overall proper significant correlation. But in the south region, we see some slight decrement in the polarization with the increase in this S. Further, we check because earlier we saw the plot of P with I, P with NH2, and later we saw we removed the field tangling effect. P cross S gives the information on only on the average grain alignment efficiency. Here, in both cases, the variations in the north and the center are this whorl of hits are similar, almost similar. But in the south region, this black one, it shows decrement. However, in this it becomes nearly flat. So here this decrease has contributions from the magnetic field tangling.
Yeah, so means why the polarization is changing with S in case of south, in the south region?
It is due to
what is the physical, so what is the physical phenomenon behind that?
Yeah, it's because as we see in the map of here see it's due to the more unordered in the magnetic field, or we can say magnetic field fluctuations, as we can see in the south region. Many are but in the north and the center regions, overall almost nearly ordered magnetic field
orientations.
Okay, so generally we expect that in the higher denser region, they there will be larger dispersion, means non-ordered magnetic field, or there will be S will be larger. But here in the south region, it's not much denser with respect to north or the central region, right?
This is somewhat less denser compared to others.
Less denser. Yeah.
Okay, thank you. So,
Yeah, okay, thank you.
so
Yeah, thank you.
from the audience. Okay, so if not, so let's thank our speaker again.
Okay, thank you, sir.
Yeah, so now we have a discussion section. So the leader of the discussion section is Dr. Lee Ngọc Chom. So now I move.
Okay, so I can send it. So today we have the long day with the very, very interesting talk, but I didn't have time to take a note or something. So let me summarize what we learned from this morning until now. Okay, that's a very hard exercise for me. So we start off with the Alex, the theorist, and then we know about the turbulence. Okay, we know about something that we apply later on called the VGT technique. Okay, so in the turbulence picture, the velocity gradient, that means the variation in the velocity is perpendicular to the ambient magnetic field. So that's why when you have the spectral lines, you calculate the difference of velocity or gradient of velocity. You rotate it by 90 degrees, like the dust polarization, you can infer the magnetic field. But it doesn't work in some cases where, like Akchana and also other people show, or Ngan, so that when we have the dense structure or we have the outflow or inflow, the magnetic field will follow, or the gas will follow basically parallel to the ambient magnetic field. In this case, the velocity gradient now turns to parallel to the magnetic field. So if you turn that 90 degrees, you have misalignment. So that's the indication where the gravity dominant or you have the inflow, outflow interact to the process. The next thing that we know from the team review talk that about the rad theory. And that, as you know, that can explain quite nicely most of the, every cases. And today we didn't have any talk about the extra galaxy, but we can use the thermal dust polarization in extra galaxy beyond our Milky Way. So we can use the thermal dust polarization to infer the magnetic field as well, and have a lot of works on that. And so they use ALMA and high redshift, and they can use the same theory. Sorry, I speak too much today. And because in the high redshift, you have the redshift problem that we observe here at radio at when they emit the far infrared. So the same physics here, and Enrique did done a lot of work about that. And then recently, Tim said that they have to tend to call the general. I don't know, what do you name the general? You say that the general theory of rad, or do you have any other names?
Yeah, so the idea that the GMRAD or general MRAD is that we want to make the alignment theory to be applicable to a wide range of environments. So because the original rad theory we developed, we use a standard intermedium to test or to quantify the alignment degree and also the alignment disruption degree. But when we apply the theory to ISM and star forming region, the theory is quite successful. And then there's a problem so when we apply now the rad theory to the environment where the radiation is very strong. So you can see here. So the environment, actually dust is very warm and hot, and it including the region where we have a very strong feedback from stars, from supernova and kilonova, and so that. So the rat theory is successful in the ISCM star forming region. And then we discovered the disruption. So disruption of dust grains, we now call RADD. And it turns out that if we apply the theory from ISCM star forming region, the alignment is very efficient. Now, the disruption is also very efficient, so that large grains could be completely disrupted into smaller fragments. And then there is the tension, why we still have a large grains in our solar system. In other environments, like in supernova or evo star, we still have a large grains. So large grains can survive in such a very strong radiation environments. And one of the potential explanation for that is the disruption efficiency is not perfect. It has a lower degree of disruption. So how we can account for that? And then, yeah, that is a motivation for me to develop the general MRAT theory. Now, with the general MRAT theory, it is similar to what we developed before for ISCM star forming region. But for radiation-dominated region, we found the new effect, namely rat trapping. So the rat trapping now implies that the majority of dust grains are trapped at low rotation stage. Only a small fraction of grains can be alive at high J state. So of course the disruption still happens, but it has a lower efficiency. At the same time, the alignment is also lower because of the rat trapping. So that is the test, the prediction from the GMRAT theory. So I encourage us, all of you, to make proposal to observe or to test this prediction. And another environment is in the environments where the lifetime of dust is comparable to the gas damping time. So those environments, including the outflows, protostellar outflows, or the inflows, or streamers toward protostar, and galactic inflow and outflow. So in those environments, the dynamical time scale of alignment is comparable to the gas damping time. So the alignment now increasing with time. We don't see the perfect alignment as in the ISM or star forming region, but that is like a time-dependent alignment. So that is also the new prediction from the GMRAT theory.
Okay, so any questions, comment to Tim?
I asked him during lunch about the indicators of general MRAT theory in observations. So can you comment more specifically on what would we expect to have with the radiation-dominated regions? Yeah.
Okay, so the expectation, you mean what is the key observational testing? Yes, so first of all, about all three effects, rat trapping, fast alignment, and imperfect alignment. So the key observation signature is the polarization level would be much lower than the polarization of dust in ISM and star forming region. So in the ISM and star formation, the polarization level we usually observe is between 10 and 20%, or even lower than that. But in the radiation-dominated region, the polarization is expected to be a factor of 2 lower. That is from the calculation. So that is one thing. Another is because of in the radiation-dominated region, we also have a disruption effect. So most of large grains which are aligned at high J are disrupted. So there exists only large grains at low J. So for grains rotating at low J, now they could be aligned along the radiation direction rather than along magnetic fields. So we predict that the position angles are tracing radiation direction rather than magnetic fields. Of course, if large grains are rotating at high J, and then they align along magnetic fields, but at low J, the resection of radiation is faster than lack of resection. So we can estimate the alignment reduction based on the typical time scale. Yeah, so there are two key signatures. One is the correlation function, lower.
Maybe we should use only this one because the online participants cannot listen to.
Sorry about that. Yeah, so the question from DIAP is, what is the key signature, key observation signature for the radiation dominated region? Yeah, so my answer is there are two key signatures. So first, the polarization level in the radiation dominated region is at least a factor of 2 lower than in the ISM and star forming region. The second is because of relative torque disruption. So if some fraction of grains are aligned at high J, so they would be disrupted. So the contribution of polarization from grains at high J is now 0. So the major contribution to the dust polarization come from large grains at low J attractor. Now for grains rotating at low J in strong radiation, they could be aligned along the radiation direction rather than along magnetic fields. So we predict that the polarization angles are perpendicular to the radiation direction. So that are two key signatures.
Okay, thanks, Stephen. Any other questions on SciComm? Yeah, Pravash, sorry. Do you have any questions?
Okay, sir. Sir, I just want to discuss one thing instead regarding the RED-D, relative torque disruption. Is that suppose the last grain is rotated very fast and it's just started disruption, let's say, and it's fragmented into smaller grains. But can these smaller fragmented grains, can we get a condition in which these fragmented smaller grains, their sizes are above the A-aligned value, so that they can participate in, they can contribute again in the polarization? Usually in the red disruption, we say that due to fragmentation, polarization decreases. But the question is it also possible that these fragmented grains, their sizes, they're small but above the minimum alignment size value?
I understand. I got your point. Yeah. So the smaller grains, yeah, if their size larger than the alignment size, they could be aligned. And those smaller grains could be aligned along the magnetic field direction. But large grains, which are rotating at low J, they could be aligned along radiation. So it results in the polarization dependence on the wavelengths. So at longer wavelength, which are dominated by larger grains, they could be the polarization could be tracing radiation direction. But at shorter wavelengths, the polarization would be dominated by smaller grains, and then we still can use the data to trace magnetic fields. So we expect that not only the polarization degree varying with the wavelength, but also the polarization angles would be also varying with the wavelengths.
Okay. Okay, sir. Thanks.
Yeah, just one more point that we didn't show anything, or we didn't say anything. The disruption already affect like the upper cutoff of the grain size distribution. So if you're working on a nanoparticle, for example, if grain size lower than 100 angstrom, the goal alignment is very important. If you have the supersonic drift between gas and dust, you can rotate the nanoparticle very fast. Due to the random torque, it's not really torque anymore because nanoparticle. So because the random stochastic collision with the gas can rotate the nanoparticle very fast. And if the grain is composite again, they can destroy the lower limit of grain size distribution. So that's another effect, but we didn't cover in this series in here. And the next thing that we show is not the GMRAD here. It's just the RAD and MRAD that we show that the theory can be predictive so far, right? So we can model, even though it's a numerical model, so some things, we can be predictive and we do forward modeling. It's not reverse modeling, but forward modeling. And we test in many, many cases with different physical parameters, with different things, and we found that the coil consistent with the data. Not perfect, but kind of explain the phenomena. And then the section of the afternoon, we're talking a lot about the magnetic field. The first thing about the multiple wavelength, multiple scale. So we see that the magnetic field vary from the large scale to small scales due to a lot of things like the streamer, like the hub system, and like also star formation activities. And also they show the very good collaboration between India and Vietnam in case of science. That means we have the visitor from from India came here and become collaborator to each other, and then we publish interesting works together. And we're talking about magnetic field. We use dot polarimetry to work on the magnetic field. And the big problem with the magnetic field right now, the first thing that we working on the plane of the sky magnetic field, because we use dust polarimetry. We don't know another direction, so maybe the tomorrow problem. But talking about on the plane of the sky magnetic field, we use the DCF method. You know, the DCF method developed in the 50s, the last century, by very famous physicists. No, 3, if not 2. And the assumption, the very basic assumption of DCF, that we have the equipartition, the energy of the kinetic energy, non-thermal kinetic energy equal to the magnetic energy, okay? From that, you can infer the magnetic field. And back to the time, that method used to estimate the magnetic field in a galactic scale, okay? And now we still use the DCF method to estimate the magnetic field in Coulomb, in filaments, and very, very small scales. The question is that how reliable that the DCF method still, I mean, any idea, anything? So Alex, so in his presentation said that he have a new idea on they call the DMA, or the DMA, right? And Scalidis as well, they have another method to do it. And whatever method we try, we found a different value of magnetic field strength. A lot, right? I don't remember how much, but sometimes a factor of 4, a factor of 10, something different. And then you calculate the ratio between gravity and magnetic field, you call the mass to flux ratio, and you calculate the alphanic Mach number between the turbulence and magnetic field. And then you conclude a lot of things, how the magnetic field interact, or play the role. And if we estimate magnetic field strength wrong, and everything just follow up could not be correct. And in your expertise, your science, do you found anything about that to contribute to, and how to improve that kind of things? Okay, so Sadhana, you have any idea?
Okay, so I reached out in previous section. So yeah, so my question was regarding this MRT mechanism. Can I ask the question from the previous section?
Yes, please.
Okay, so my question was that in the MRT mechanism, so that is the combined effect of RAT plus magnetic relaxation. So for example, in RAT, when the angle is 90 degrees between radiation and field strength, and if there is a strong anisotropic radiation, then the alignment can be with respect to the radiation direction. So in case of grains have magnetic inclusion also, and if the condition of this is satisfied, that radiation and field, the angle between radiation direction and field direction, magnetic field direction in 90 degree. So in that case, what will happen to grain alignment, means how they will be aligned with respect to magnetic field or with respect to radiation, or it will depend upon that how which one is strong, whether magnetic relaxation or RAT.
You're talking about the radiation field and magnetic field?
Yeah, so I'm talking about if these, for example, if the grains have magnetic inclusion and the direction of radiation and the magnetic field direction, and the angle between the direction of radiation and field is 90 degrees, then the grain alignment will be of means will be along the magnetic field or along the radiation direction,
Okay, first maybe.
or it will depend upon which one is stronger.
Yes. Okay. So we're talking about what we call the K-rad or P-rad.
Yeah, MRT.
Yeah, in the story. So first thing, if you have a magnetic, also support magnetic iron inclusion, very likely you have P-rad alignment. But we have paper with that if you zoom, for example, ALMA, you zoom very close to the set like protostellar force. Remember where when the grain size is 10 micron or so, 10, 15 micron. K-rad might become more important than the P-rad. Yeah, we saw very dense case and the grain size is big. Sometimes you can see K-rad. I mean, when you zoom very dense region about density, volume density about 7, 8 particle per cubic centimeter in grain size. But if we use a single dish something, I don't think if we have the iron conclusion, I think we will be good.
Okay. Yeah. So.
Yeah.
Okay. Thank you.
Talk a little bit about the K-rad and P-rad you mentioned about in the core. So I wonder what scale you are talking about, 100 AU or 1000 AUs? Because yes, we agree that inside the protostellar core, so the K-rad may be activated inside the protostellar outflows. Because inside the protostellar outflows, so the density is low and the radiation field is strong, so some grains in the hydrate ejector can be destroyed, and remaining in the granular low J's, and granular low J's can be aligned with the radiation fields instead of the magnetic fields. But the problem is that when we perform the modelings, so the grains at low J's, usually they have the very individual internal alignments. And because they have the individual internal alignments and they align low J's, so we expect the polarization degree from radiatives, from K-rad of grain at low J inside the outflows will be subdominant compared with the emissions of magnetically gliders grains in the foreground envelopes. So we expect that we might not see the size of the K-rad even inside the protostellar core. But currently I'm working on the core of lower intermediate mass with the luminosities up to the 100 solar luminosities. But maybe in case of the massive star, with the luminosity can reach up to the 10 to 3 or 10 to 4. So maybe the description may be stronger and they can affect reduce more or less grain surrounding. So maybe we can detect the sign of K-rad here. Yes.
Yeah, okay. So I think first of all, K-rad doesn't happen in collision-dominated region. K-rad only happen in the radiation-dominated region. Okay, so in protostellar cores and this, so some earlier study by Tazaki et al., they expect that the K-rad could happen in the disk, but their analysis is based on the wrong model. So when they estimate the radiation precession time scale, they just consider that grains are aligned at low J. So that's why the radiative precession is very fast. But in fact, in the radiation, in the high density region, so you can see here, for example, when the grains are aligned at low J, so the low J grains are not stable. So all grains will be kicked and will be transported to high J. Okay, so that when we estimate the alignment time scale along radiation or along magnetic fields, we have to consider the states in which grain alignment happens. So if grains are aligned at high J, and then the time scale for radiation precession is much longer than along magnetic field. So the only environments where we expect the alignment along K-rad is the radiation-dominated region. So you can see here, because grains are trapped at low J. So only a small fraction grains align at high J. So if grains are aligned at low J here, and then if you increase the radiation intensity, the radiative precession is much shorter than Langmuir precession. So we have a KRAT. So the environments where we expect KRAT would be these environments. So in all these ISM star forming region, it is in the regime of collision dominated region. So we would not be able to observe a KRAT, but in radiation dominated region, we expect to observe KRAT. Yeah, it's close to the central source, to the star. Yeah, right.
Which are the best sources to test the GMRAT with the current sensitivity and
so with the current observational facilities, especially ALMA, so the best targets to test is AGB stars and decreased disk. So for AGB stars, we can recently with Houston here, we propose to observe polarization towards oxygen-rich and carbon-rich AGB stars. So if we see the polarization morphology and polarization fractions are totally different in two objects, it would be very important to constrain the GMRAT. Another target is the exoplanetary system, the decreased disk. So they are have a very low density of gas, but high radiation field. So the radiation pressure is much higher than gas pressure. So we expect that this is no, there are dust, lots of dust. ALMA already detected many decreased disk. Yeah, it's faint, but it's detectable. The most challenging thing is the polarization fraction is low. So I talked to Haifeng, and he said that the observation time must be very long. Yeah, but it's a very unique test. So we should invest in the observation.
Hello, can you hear us, the online participants?
Probably not.
That's
So Pravash?
Yes, sir. Yes. Sir.
Yeah, Pravash?
Okay. Yes, sir. Sir, I just want to ask one thing that regarding the MRAT theory, suppose let's say in some dense star forming region, the external magnetic field is less, let's say it's not much strong. Usually for our magnetic relaxation strength, it depends on the total magnetic field strength, external magnetic field strength. Suppose the magnetic field strength is not that much strong, and we observe high polarization fraction of, let's say, around 20%. So in that case, can we how we will explain whether is MRAT theory will be able to explain, or will we explain it as purely due to RAT theory, because the interstellar radiation field may not be able to achieve that much high polarization, 20% in dense star forming region.
Okay, your question is that when you say the magnetic field strength is not strong enough?
Yes.
I think you are referring to the diffuse gas, right? Because the magnetic field strength is related to the gas. Yeah.
Yes.
So if you have the dense gas, for sure you have the higher magnetic field. So if you have diffuse gas, and usually in diffuse gas, Planck measure the maximum about 15-20 degree maximum.
Yes.
So if you have higher than that, the things that the first thing that for me, I think the alignment should be very efficient. And how the alignment is very efficient, it depends on many things. One of those is the MRAT. That's exactly my question. My next question, basically. So in order to have MRAT, you need to have iron inclusion inside the dust grain. The next question is how much iron inside the dust grains. So that in the community, we're talking about a team also have the idea, because it's so, I think we have the evidence for the asteroid or something, right?
Well, so the question now goes into how much iron is depleted from the gas. So basically, from observation, more than 90% of cosmic iron abundance locked in the dust. Okay, so we don't have any debate at all about whether dust contain iron or not. We know that more than 90% of iron is locked in the dust. Okay, so that is already established. But the remaining question is how iron atoms are distributed inside dust, whether they are in clusters or they are just diffusely distributed. And that is very hard question. So from the analysis of meteorite, so people found that many iron clusters are present inside the dust grains from meteorite. So if we understand that the meteorite is a fragments of asteroids and comets, so they would be formed from protostellar environments or even in molecular clouds. So yeah, so iron clusters are present in the meteorite. That means somehow iron clusters must be formed in dust grains, whether though dust grains are in protostellar environments or in molecular cloud. Yeah. So, but from the that is a one outstanding question about the distribution of iron cluster inside dust.
Okay, so then we back to the magnetic field. Do you have any idea, any question, or anything about the magnetic field industry here? So, Robert Chin Hee, you did yeah. So maybe close to the end. So you do not a lot of analysis to the magnetic field strength in the star forming region, star forming areas, right? You use the DCF or other things, and how does it work?
Yeah, so I agree that there is a big uncertainty in the DCF method. So I think we need to try the Zeeman measurement instead of the dust polarization. I believe that the Zeeman is the only method to directly measure manifold accurately compared to the DCF method. And another one, we needed to compare with the simulation data and try to the DCF method toward the simulation data. And already Junao suggested that tried that 11 simulation data and applied the DCF method, and he suggested the new fraction factor as the different size scales or like masses like that. So we need more the simulation and such kind of works for believe this method. I think so, like that.
Okay, maybe that one of the last point that's we show, I mean, maybe Ngọc show and myself show that we see the V-shape, a shock spectrum in the multiple wavelengths. So we think that the multiple wavelength parametry is very important. Single is perfect, and multiple is I mean, more. Because if we working on one single wavelength, we have so many free parameters, right? And then somehow we can fit to the data, no whatever. And if we have the multiple wavelength, the physics or something phenomena will be different. Like you see the monotonic increasing, decreasing. Now we have the V-shape or something. And the next question of that, because multiple wavelength, we use multiple different instruments to measure dust polarimetry. And different instruments, the data from different instruments go through different pipeline reduction, and they don't talk to each other. Okay. For example, JCMT use different pipeline, Hopplus use different pipeline, and we combine them both to each other. We introduce bias for sure. And the next million question is that how we can have more or less the tool or something common to pipeline to reduce the data from multiple different, right? If you SMA, also ACA, we have different pipeline reduction things, and how sure we are when we combine different data from different instruments together. Maybe V-shape will not be the V-shape anymore. We have the correct pipeline, or it does. We don't know. So that is the thing that for me, I don't know how to have combine the data from different instruments in the correct way. And do you have any idea, question, something? Yeah, okay, no, so let's talk about simulation. So the last question. Yang, in your multiple wavelength with Polaris, do you see the V-shape?
Actually, from the simulation size, I only work on the protostellar core scales, and I work with the multi-wavelength one times, and we see the V shapes when we change the wavelength from 250 to 850, and the reason they causing the V shapes is because of the changing from the discrete extinctions into the discrete emissions. But we have not yet tried perform the synthetic modeling in the large scale, like the filaments or molecular clouds. So I think maybe it's a good task. We can try to perform the synthetic modeling in this area to see, because usually we said that when we measure the dust polarization, the short wavelength, which is the hot region, hot dust layer, and the long wavelength, which is the coarse areas. But we actually don't know exactly what layer they are tracing and whether this is correct or not. So I think if we can, if we can perform the synthetic modeling in larger scales, so we can maybe see that whether we can we can claim that's whether we can use the multi-wavelength dust polarization to check the different layer and whether the vision is really caused by the two dust layer or other reasons. And another thing is that not only for the V-shapes, but if we can prove that the multi-wavelength dust polarization, they trade different layer, so maybe we know the magnetic field on the plane of skies. So maybe based on the polarization function, we can also infer again the inclination angles at each layer. Maybe we can trace back again how the 3D magnetic field they change across different layers. So that can be tested with the synthetic modeling.
Yeah, I also agree with your point of view. Like if we have like multiple wavelength, and also we can trace for different layer of the star forming region, so we can apply our new technique in order to get the inclination angle from the polarization fraction, and then we can get like multi-scale structure of the 3D morphology, and not only just using for the tumulus polarization, we also can use that for the starlight polarization, so that we can have a more larger scale structure, and that is how we can combine both starlight and tumulus to get all of the information about 3D morphology and their impact from large scale to smaller scale.
Okay, thanks, Bob. I think that's a very, very good introduction for tomorrow's section. And because tomorrow we talk about 3D magnetic field. So for the end today, okay, once again, thank you very much for all the speakers. And yeah. So LOC, do you have any announcement or any instruction? LOC, do you have anything to say? LOC, where we meet and how we go. Okay, 60 seconds, please.